Welcome to C Sharp Design Patterns. I'm Keith Welch, and I'm the instructor for this course. This course is all about writing better code, helping you create better structure for your code and create more readable and maintainable code. In that I mean, we're going to show you patterns and techniques that allow you to create simpler code, but not lose, of course, the complexity and features that you need. But the code itself will be simple because it will follow known patterns. And it'll also be simple because you'll be breaking things up that normally you would put in really complex classes if you didn't know about design patterns. So your code will be simpler, more readable, and thus more maintainable. So we're going to look at design patterns, and we're going to do them in C Sharp, but the book itself was written in 1995, before C Sharp, of course. But the patterns themselves are language agnostic. They do require an object-oriented language, which conveniently we have, but the patterns themselves can apply to any number of object-oriented languages, and they've really stood the test of time. We'll, of course, introduce you to what the design patterns really are and what the intention is, and we'll go through 23 different patterns, and we'll take a look in depth on each pattern, first at a perhaps more academic level, and then with actual real code examples. And the patterns themselves are grouped into three basic areas: creational patterns, that are, as you might guess, patterns for creating objects, and then structural patterns, which of course are structures of objects, and then behavioral patterns, what they actually do and how they go about doing it. Design patterns really focus on the interaction between classes, not so much the overall application architecture, nor are they really concerned about the inner workings of a class. They're really focused on the overall structure within the application with regards to how the classes interact with each other and how they relate. And inheritance and interfaces are used quite a lot. We'll go from the design patterns and move on to another pattern called the Model View Controller, or MVC pattern. Now, MVC is more of an architectural pattern in that it really affects the overall application or the design of the overall application as opposed to the relationship between classes. It's really talking about layers when you're talking about models, views, and controllers. So we'll talk about the MVC pattern, and then we'll use ASP.NET MVC and run through a number of examples to show you the different layers within ASP.NET and how it's implemented. We'll also use the MVC app with the database so you can see how the database is created as a model layer. Let's start at the beginning and talk about design patterns and who the heck are the gang of four. Many years ago, I went to a course about designing software. This was back in the Windows 3.1 days, and Windows had a tremendous selection of colors. It had black and white and gray. It also had certain important design standards. The File menu was on the left, the Help menu was on the right. It also had some other standards. The OK button was on the left, the Cancel button was on the right, at the bottom of the screen. And if you think back to those old Windows apps, if you've ever seen one, they're really pretty simple and they follow very simple basic patterns. But yet the first line of the course was designing software is hard. And they showed all sorts of examples of people who had messed up usability in Windows 3.1 apps. Well, since that time, we've had the web. And the web broke all of those interesting user interface design rules that I had learned. It used colors, and Mac and Windows can't agree as to which side the OK button should be on, and websites can't agree either. So now we have design patterns, and design patterns aren't used particularly for user interface designs. I use that as an example. Designing reusable object-oriented software is also hard. As software has grown in complexity, it's also gotten harder to write good software. Design patterns help us write good software because what we're going to be using are patterns that have demonstrated a proven success over the years. So our software designs should address our immediate problem, obviously. We hope that they should also be flexible for future problems or expansions or features, or at least they won't inhibit those future expansions because we've designed ourselves into a box. We would also like to reuse things that have been proven to work. And these are the patterns that we're talking about. They're effectively building blocks of code. Now, we're not talking about copying and pasting our favorite pieces of code. We're talking about the patterns that build that kind of successful code. and we don't really need to reinvent the wheel. If someone has created a pattern that solves a problem that we have, then we don't really need to create our own solution, unless, of course, their pattern just isn't any good. The design patterns that we're going to talk about in this course have been proven over time, and they also solve really common architecture problems in software. A pattern addresses a common problem. So if we have, for instance, a problem that we have complex objects to create, and we don't want to spread all of that complex construction all over our application, that's a pattern. It's called the builder pattern, and we'll be taking a look at it. It's a template or a guide. It's not a final design. So when I talk about a builder pattern, we're going to be talking in general terms. We'll give you concrete examples, but the builder pattern can be applied to all sorts of different kinds of software. It can be applied to mobile. It can be applied to web or desktop. It can be applied to different languages as well. We're going to focus on C#, but these patterns were written prior to the existence of C#. They're really design patterns as opposed to language patterns. We're going to do some C# implementations of those patterns, but the ideas behind the patterns are the same. The pattern doesn't describe classes. It actually describes relationships, interactions between classes. The classes that you create are going to be particular to the application that you're creating. You may have customer classes. You may have measurement classes or graph classes or document classes. Patterns don't talk about those kinds of things and the specifics within the classes. It talks about how the classes relate and work with each other. The patterns aren't architectural either, so it's not an entire application architecture. For instance, you might be familiar with 3-tier architecture or MVC architecture. The patterns that we're going to talk about in design patterns are smaller in scope than that. They're actually little pieces of that overall architecture. Now, later on in the course, we will talk about more global architecture issues as well, and including we'll spend some time on MVC. The design pattern has 4 elements. It has a name. I hope that's self-explanatory. It also describes the problem to be addressed. And when we talk about each one of these patterns, we're going to start with what's the problem, because that's really what's going to happen in your practical usage. You're going to be presented with an application or part of an application that you have to build, essentially a problem. So you want to be able to recognize within that application what patterns, if any, that you should use. So we'll start with the problem, and then we'll talk about the pattern that may address that problem. So after we've talked about the problem, we'll talk about the pattern that provides a solution. And then we'll talk a bit about the consequences of that. Hopefully most of the consequences are positive. For instance, it makes our application much more readable and simple to use. There may be some performance consequences here and there as well. So a quick example. Here's our problem. We need to support multiple database types. Sure, we're going to start out with a little bit of a MySQL database for this application, but we expect it to grow like gangbusters. And we know that we're going to need to be able to expand it to something that uses a huge server farm and probably Oracle servers. So we don't want MySQL classes spread all over the code, because when we expand to Oracle, and that's going to happen quick because we're going to go viral, when we expand to Oracle, we're going to need to make the change really quickly. So we don't want MySQL classes spread all over the application. We want them isolated into one particular area. So we can use a pattern called an abstract factory. And what that does is it provides an abstract database class. It's not a MySQL database class. It's not an Oracle database class. It's not a SQL Server database class. It's really kind of a generic database class. And then our factory will create an instance of the particular database type that we need. So today, we'll create an instance of a MySQL database. But in the future, we'll be able to create an instance of an Oracle database, and both of those classes will descend from this abstract database class. And the entire rest of the application won't change a bit, because they won't know anything about MySQL or Oracle. They'll only know about our abstract database class. So that's the kind of pattern that we're talking about. We've presented a problem, and then we come up with a pattern that has already been proven out that solves that problem. What's this gang of 4 thing that we keep on hearing about? The gang of 4 are Eric Gamma, Richard Helm, Ralph Johnson, and John Vlasides. And they wrote a classic text called Design Patterns, Elements of Reusable Object-Oriented Software in 1995. So it's about a 20-year-old book. but yet it's still a classic and still well used. And of course, you can get it at that Amazon link. And it describes 23 different design patterns that are commonly used in building software. And we're going to go through each one of those 23 patterns in this course. And we'll first describe the problems and solutions and a little bit about the pattern and the class diagram to show you the interactions between classes. And then we'll do some code examples of each one of the patterns in C# so you can actually see them in use. The first pattern we're going to look at is the abstract factory pattern. I'm really happy that this is the first pattern we'll be doing because it's one of the ones that I use the most, and I find it extremely useful. In fact, when I was hiring people, it would be one of the questions I would ask them if they could give me an example of a factory pattern or at least understood what it was. We're going to talk about first the problem that we're trying to solve, and then we'll actually talk about the solution by using the pattern. So we have a number of different problems that an abstract factory pattern solves. One of the most common is that an application needs to support multiple database types. For instance, we may start the application and use SQL Server. Later on, it has to be changed to some reason to Oracle or maybe MySQL. And we just want to be able to do that without having to change all of the different pieces in the application that deal with the database. We don't want the application as a whole to understand anything about the database type. We only want just a piece of the data layer to understand that. I also came from the measurement world, and in the measurement world, we often use serial ports and Ethernet and other device drivers to acquire data. Now, of course, our application doesn't really want all of that serial port code spread out throughout the application. Most of the application wants to deal with the data. It wants to acquire the data and then process it and present it in some way. So in measurement data, we want to isolate the data source from the rest of the application so that the application only has to deal with the data and doesn't actually know anything about where the data came from. Another example is we need to be able to create different report types. We might have some sort of application that exports data or graphs or charts to different kinds of documents. Now, of course, we also don't want the application to know throughout the application that it's creating a Word document or a PDF document or any of that. For the most part, we want the application to create the data that the document uses and then pass it to something that creates the document itself. So we're going to be using an abstract factory pattern to solve this problem of isolating these different types of either database types or data sources or document types from the rest of the application. So what does the abstract factory do? It provides an abstract class that the rest of the application can use. It will provide a generalized interface. So in the case of a database, it might provide an interface for the connection and command objects. But it would not provide an interface for a SQL Server connection object. It would just provide a generalized interface for a DB connection. So we'll hide the details of the type of database or the type of data source from the rest of the application. The rest of the application doesn't need to know. The factory class will create an instance of a class that inherits or implements an abstract class. So the classic form is to have an abstract class. You can also use a factory that implements an interface. So we're going to demonstrate, in this case, using an abstract class, but later on we'll also show you how to use interfaces. Another cool thing is we can use the abstract factory in conjunction with the factory method pattern, and we'll show that to you later as well. In fact, we can also use it in conjunction with the builder pattern as well. So a number of these patterns can go together as well as stand alone. So let's go back to our problem and we'll give it a little bit of a solution. We have that problem of we want to be able to work with different database types. So in our abstract factory, we're going to create an abstract class called database. Let's say it has two properties, one for the connection, which will be of type system.data.common.db connection. Note that there's no kind of database type in that type. The command property would also descend from system.data.common, and it would be of DB command type. So again, it doesn't specify whether it's SQL Server, Oracle, or OLADB. So that's the abstract class that we'll be passing throughout the application. So the application only knows about DB connection and DB command type. Now, an abstract class cannot be instantiated. So instance classes must inherit from it. So anything that we create is going to be an instance class and not strictly a database class. It will be a class that inherits from our abstract database class. So we would like a SQL Server instance class. It'll inherit from the database class. It'll have a connection property. In that connection property, although it is of type DB connection in our abstract class, for our SQL Server class, we'll return a SQL connection. SQL connection inherits from DB connection, so it obeys the rules in terms of obeying the interface for the abstract database class. Likewise, our command property will return a SQL command. And of course, SQL command inherits from DB command. So that again honors the contract of the abstract database class. And let's say we want to do an OLEDB server as well. So again, OLEDB server will also inherit from our abstract database class. And then the connection property will return an OLEDB connection, which also inherits from DB connection. The command property will return type OLEDB command. And that, of course, inherits from DB command. So essentially the same thing that we did in the SQL Server instance, it's just we used OLEDB instead of SQL Server. But note that both of these hide the implementation details from the rest of the application because the application is dealing with the abstract class's interface, not the actual instance class interface. And here's our class diagram, and you can see that we have the abstract class database, and it has the properties command and connection. And then we have our SQL Server database class, which inherits from that. And it, of course, has the command and connection properties, as well as some internal private fields for underscore command and underscore connection. And of course, those are going to be the underlying fields that are associated with the properties command and connection. We also have OLEDB database, which also inherits from our abstract database class. And it has the command and connection properties as well. So that's the idea behind a database abstract factory. In our next lesson, we'll take a look at an actual code example of implementing this for real. Let's take a look at a code example of the abstract factory pattern. Our application needs to support both SQL Server and OLEDB databases. But we don't want the entire application to have to deal with the different kinds of commands and connection objects that are used for those databases. We actually don't even want our data layer to support that either. We simply want the factory pattern to be able to give us the right database class, and the rest of the app doesn't have to know anything about the underlying technology of the database. So we get a nice separation of concerns that way. This is our class diagram. We have an abstract class called database. It has two properties, a command property and a connection property. We're going to have two classes that inherit from database. One is a SQL Server database, and of course, it implements command and connection. And we have our OLEDB database, and it implements command and connection. In both cases, we have corresponding private fields as well. The rest of the class diagram consists of the things that we have in this Windows Form app, which doesn't add up to much, and I'll show you that later. So let's take a deeper look at what the factory pattern classes look like. The database class is very simple. It simply has our two properties, connection, which is a DB connection type, and command, which is a DB command type. And both are just empty virtual properties. Note that we're using DB connection and DB command. These are abstract versions of connection and command objects for .NET that can be found in system.data.common. These are the objects that the rest of the application is going to be working with, but they don't expose the database technology. In our implementations, we have a SQL Server database class, which descends from database. It uses system.data.SQL client and does not use system.data.common. We also have a using system.configuration, and I'll talk about that in a little bit. We have our private members of DB connection and DB command type, and we initialize them to be equal to null. I like to do this explicitly just to make sure that it's clear. And then we have our property. We have a public override of DB connection type for our connection property. If our member is equal to null, we're going to create a new connection object. Note that if the member has already been set, then we don't go through the process of creating a new connection. This is called lazy loading. So we haven't created the connection until we actually need it because someone has requested it, and we don't recreate it all the time that they request it. We're going to get the connection string from the configuration manager, its connection strings object, and we have SQL Server connection string as the name of the connection string for the SQL Server database. And we'll get the connection string property from that. So this is information that's stored in app config, and if this was a web application, it would be in web config. So if I open up app config, I have connection strings for both SQL Server and OLEDB. This sample code is going to be in your work files, and you'll obviously have to change the connection strings for whatever system you're working with. But the SQL Server connection string has a data source, an initial catalog, integrated security equal to true, and most importantly, its provider name is SQL Client. And you can see that the provider name for the OLEDB connection is system.data.oledb. So that's what our configuration looks like, and that's where we're going to get the connection string property. The one other thing we need to do in order to use the configuration manager, in our references, we have to add system.configuration. That doesn't come for free. So now we have our connection string, and then we can simply create a new SQL connection object, passing in the connection string as the parameter. We'll set our connection member and return it. Now note that I've created a SQL connection, but the return type is DB connection. And that's simply because SQL connection inherits from DB connection. The other property we have is the DB command type command property. And it follows the same sort of pattern. Again, if the member is equal to null, we'll create a new SQL command, and we'll set its connection property equal to the connection that we've created. So from the application's perspective, when it asks for a command object, we actually create the underlying connection object and set the command's connection. So the application only has to actually ask for command. So that's the SQL Server implementation. The OLEDB, as you might expect, is very similar. The only real change is that we're using system.data.oledb. We're getting our connection string in the same way, except of course we're passing in the OLEDB connection string name. And we're creating an OLEDB connection as opposed to a SQL Server connection. The process is the same, however. And for the command, we're creating an OLEDB command as opposed to a SQL Server command. So these are the classes that comprise the abstract factory pattern. Now let's see how we actually use them. In our form, we've got a very simple form design. We have a radio group that asks to use SQL Server or OLEDB, and a simple Get Database button. That button click handler is going to create our database object. And if our radio button for SQL Server is checked, we'll create a SQL Server database. Otherwise, we'll create an OLEDB database. Now note my variable for database is of database type, so it's of that abstract class type. So after we choose the type of database based on the radio button selection, the rest of it is all generic. The rest of the application doesn't know anything about it being SQL Server OLEDB. All it knows is that it has a database, and there's a command object on that database. And you can see we take that command object, and it's of type DB command. It's not SQL Server OLEDB command. And then when we have that command object, we can run our database operations. So I've commented those out here, but just to give you an example of what you might be able to do, you can set your command type on that command object. In this case, I set it to text. And then you can set your command text. So I've typed in some SQL. In best practices, we'll do this a little bit differently. Then I can call connection open on that command, create a DB data reader, and do an execute reader on the command. Finally, I can close the reader and close the connection object. Obviously, in between creating the reader and closing it, we might actually want to read some of those customer records. But note that none of these calls know anything about SQL Server or OLEDB. So the rest of the application is completely isolated from that database technology. So we could expand this factory if we wanted to include MySQL or Oracle or any .NET supported database technology. So if you had a database application that you wanted to switch over from SQL Server to Oracle, if you use a factory pattern, you wouldn't have to rewrite the entire application to change all of those SQL client objects. You would only have to add the Oracle implementation to the factory, and then just change the code that calls out which factory to use. So you'll get the Oracle factory instead of the SQL Server factory, and then everything would be using the standard abstract DB commands and DB connection objects. So in that way, you could actually make a shift from one database type to another fairly simply. Now, this is a pretty basic example, and you might actually want to go a bit further so that you don't actually have DB commands and DB connection objects in your application code. You probably actually want to hide those in a data layer to provide more isolation for the rest of your application. But the abstract factory is a start at least isolating the database technology. Sometimes we have to create objects that have a lot of properties or settings that we need to set, or perhaps they actually have sub-objects as well that we have to deal with. So the process of creating these objects is really long. The builder pattern is a pattern that we can use to help with that problem. So we need to construct multiple type classes, meaning that they have complicated construction methods, they may set a lot of properties, they may have sub-objects, they may have arrays that we have to go through and initialize multiple instances. So the object has a number of different things that we need to do to construct it. For instance, if we were working with a database, we may need to build up our connection string, and then build up a command type and a command object, and then set timeout properties. And perhaps if we're going into a data layer, we may need to go a little bit further, and the construction process is that much more complicated. For measurement data sources, we might have a serial port. And if you've ever set up a serial port, it has a number of different properties. Port number, baud rate, parity, all that kind of thing that we have to handle to set up the serial port. We might also have an Ethernet connection, and it has an IP address and a port and a timeout and other things that we need in order to set up our data source. If we're talking about perhaps a business object, like maybe an order will have a number of properties, a customer property, order date property, and then it might also have order details, which have a number of different items, and each one of those items would have to be constructed. So that could be a very lengthy construction process. What we don't want is we don't want all of these lengthy constructors sprinkled out throughout our application. We want in our application to simply be able to call a single method that builds these things up out of our application code, so that it's clear in our application code that we're building a database or a measurement data source or a business object. But we don't want the application code to have 20 lines of methods that actually do that building. We would like that to just be as very simple and clean as possible, so it doesn't clog up our application code and make it that much more difficult to read. So the builder pattern helps us in this. It'll create a builder interface or an abstract class, and that will be a generalized object construction interface. In that interface, we'll provide methods for each object's construction step. So if we're working with a database, it'll provide methods to create the connection string, then the connection object, and then the command object, and whatever else we need further from there to create our database object. We then create builder classes that implement the builder interface for each object type. So if we're building up SQL Server database objects, we would have a corresponding SQL Server builder class that inherits from our more generalized abstract builder class. And it would implement the methods in each step that was required to build up our SQL Server database. Once we have our builder class that presents those methods, we have a director class. And the director class will use the builder class to create the object. And once it uses the builder class, it'll present the object to the application code. So it'll hide all of those messy creation details from the rest of the application. So if we're going to construct a database class, we might have SQL Server and OLADB options. And we might have methods for creating connection and command objects. And we might want to also set command parameters. This is actually a relatively simple example of using a builder pattern. So for our classes, we would have a database abstract factory class. And if you haven't looked at the abstract factory pattern, you might want to take a look at that. We're going to be using it in the code example. So in that abstract factory, we would have an abstract database class, and then SQL Server database classes, and then an OLADB database class. And both SQL Server and OLADB would inherit from our abstract database class. So that's a quick overview of our factory classes, and those are the classes that we actually are going to want to build. To build them, we're going to use an iDatabase Builder interface. And on that interface, we're going to have a build connection method, a build command method, and a set settings method. We'll also have a database property, and that's the database object that we want to build. So we'll have instance classes of type SQL Server Database Builder and OLEDDB Database Builder. And those will implement iDatabase Builder. Now, if you're not familiar with interfaces, you probably ought to study those because we'll use them a lot when we're using patterns. But the important thing of an interface is it presents a contract. So when we pass an interface to the application, it's going to know that it can call the methods that are called out on the interface and the properties that are called out on the interface as well. And it might handle the events. So an interface can declare the properties, methods, and events of an object. However, an interface is not an object in itself. It's basically just a contract. So there is no implementation in the actual interface. So iDatabase Builder doesn't have any implementation for build connection or build command or the database property. It's just saying this is the method signature, this is the property type, and here are the names of the methods and the properties. Any class that implements the interface has to implement those methods and those properties that are declared in the interface. So that's the contract part. Our SQL Server Database Builder and our OLEDDB Database Builder classes will implement iDatabase Builder, which means that they must implement build connection, build command, set settings, and the database property. The director class will have a method called build. It doesn't have to be called build, but it should be named something clear and obvious to the application code that an object is being built or created, something like that. So in our case, we're just going to call the method build. It'll take an iDatabase Builder parameter. So it'll use its parameter, which implements the iDatabase Builder interface, to call the methods that actually construct the object. Then after the build method is done, the builder will have a database property, which will return our fully constructed database instance. So here are our class diagrams. On the left, we have our director class, and it simply has a build method. And as we just said, that build method will have a parameter of type iDatabase Builder. And that's right below there. An iDatabase Builder has the three methods, build command, build connection, and set settings, and the property database, which is ultimately going to be what we return in the whole point of the builder. Then next to the builder and the director, we have the abstract factory classes. So we have our database abstract class and the OLEDDB database and SQL Server database that inherit from them. And then further to the right, we have the classes that implement the iDatabase Builder. So we have a SQL Server Database Builder, and it has an internal field, _database, and that's what it's going to use as we call the build methods. And then it has a property database, which of course is required by the interface, and then the three methods that are required by the interface as well: build command, build connection, and set settings. It also has a constructor. In the constructor, it'll build up a new database object, and then as each method is called, it'll build up that database object so that when the final set settings method is called, the database will be fully rounded out and it will be able to return it. The OLEDDB Database Builder does the same thing, except it's going to create an OLEDDB database instead of a SQL Server database. So that's the idea of the builder pattern. And the whole point of the builder pattern is to take a complex construction and to hide all of those implementation details from the application code. The builder pattern is intended to isolate the application code from complicated object construction. So if we have objects that require multiple steps, we don't want to repeat that code in our application. We'd prefer to have it in a separate class where we can deal with it there, and it doesn't overly complicate the rest of our application code. One of the ways you can make your code more supportable is effectively isolate areas so that the code is not so long that it's overwhelming. The builder pattern helps in that area. In this example, we're going to use a builder pattern in conjunction with an abstract factory pattern. So if you haven't taken a look at the abstract factory pattern, I urge you to take a look at that. Our abstract factory that we're going to be building consists of a database class. So we have an abstract class for database, the command, and a connection property. And then we have concrete implementations of the database class for OLEDDB and SQL Server. And of course, they also have the command and connection properties. We have an iDatabase Builder interface. And iDatabase Builder defines the methods that are going to be used to build up our database object and a property for its return. So we have a database property that we're going to be returning, and methods for building the command, the connection, and setting settings. We have classes that implement iDatabase Builder for both SQL Server and OLEDB. They return the database object and have the build command, build connection, and set settings method, as well as a constructor. And the same pattern is followed in OLEDB Database Builder. And at the top of it all, we have a director class. It has one simple method called build. And what build will do is it will call the builder, and the builder will run the rest of the commands. So let's take a look at our database abstract class. It's very simple. It has two properties of type dbConnection for the connection property and of type dbCommand for the command property. Our implementation of database for the SQL Server database returns that dbConnection object and has corresponding members for that connection object, as well as the command object. If you remember in the Abstract Factory class, we did a little bit of work in the gets for both the connection and the command properties. We're not doing that here. It's actually going to be done in the builder. So we've actually simplified these classes as well. At this point, the database classes are basic storage classes. They don't really have any active code that's doing anything. So the command also just gets and returns the command member. The OLEDB database class is the same way. It has members for dbConnection and dbCommand, and then properties for the connection and the command, and it just simply returns them. Now let's take a look at iDatabase Builder. The interface calls out the three methods that we're interested in: build connection, build command, and set settings, and has a property of type database that is a read-only, so it only implements the get. So we're using an interface, which means any classes that implement this interface must implement these methods and this property. And these methods are the steps that we're going to be using to create the database. So our SQL Server Database Builder class implements iDatabase Builder. We have a private member of type database, and in our constructor for SQL Server Database Builder, we create a new SQL Server database and set our member equal to it. So now we have a database that we can work with, and now we're going to call the methods to set that database up for use for the application. The first method that should be called is called build connection. And we're going to get the connection string by calling configuration manager and getting the connection strings array. And we'll look for the SQL Server connection string in the connection strings collection. And when we get it, we'll get its connection string property. These connection strings are stored in app-config under connection strings, and I've put one in for SQL Server connection and OLEDB. And you can see that the provider name is SQL Client for the SQL Server connection string and OLEDB for the OLEDB connection string. In order to use Configuration Manager, I need to add a reference to system.configuration. This is a Windows app, so those connection strings are stored in app-config. If it was a web application, they would be stored in web-config. So now we've got our connection string. With that, we'll create a new SQL connection, and on our database, we'll set the connection property of the database equal to that new SQL connection that we created with our connection string. Now we're on to the next step called build command. We'll first create a new SQL command object and set our database's command property to that object. And then we'll go into that command object that we just created and set its connection property equal to our database's connection that we built in this first step. So you can see that these steps need to be executed sequentially. The last step in this construction is setting the settings. So I go into my database's command object and set the command timeout. As you can see, I'm expecting some fairly lengthy execution. Then I also go into the command and set its command type equal to text. So we're only allowing ourselves to write SQL right in code. Your mileage may vary on that approach, and again, we'll be talking about writing SQL in code as opposed to using LINQ in best practices. And finally, in our public database property, we return our database member. And obviously, we want to go through all the methods to build the database member before we actually call for the get. So that's the SQL Server Database Builder. The OLEDB Database Builder is effectively the same, except that it's going to create an OLEDB database. It'll build an OLEDB connection, an OLEDB command, and from there, set the command timeout and the command type, just as we did before in SQL Server. So there's no real differences there, except that it's calling out the OLADB objects instead of the SQL Server objects. So those are our builders. And the important thing with the builders is they've laid out the methods for construction of the object. So now we have our director class. And the director class has one simple method. It's called build, and we're going to pass in an iDatabase builder. Note that we're typing the parameter using the interface as opposed to specific SQL Server or OLADB builders. So we have an iDatabase builder object for a parameter, and when we call build, on that builder object, we're going to build the connection first, then the command, and then set the settings. So this is the class that will isolate the application code for multi-step object creation. Now this isn't too bad because there's only 3 steps, and of course the steps had some more steps to them within their methods. So if you flatten this out and said, okay, I'm going to have one method that's going to create my SQL Server command object, then you would run the build connection, which would have to go out to the configuration manager, get the connection string, build the new connection, then you'd actually go through the steps to build the command and set the settings. So instead of these 3 methods, you'd have maybe 10 lines of code instead of 3. And those 10 lines of code would be repeated in your application anytime you actually needed a command object. You really don't want that in your application. So what the director allows you to do is just create a builder, and anytime you want the command, call one simple method called build on the director object. So that keeps your application code nice and clean. So let's see that clean application code. Here's our form, and it's very simple. We have 2 radio buttons, one to use SQL Server and one to use OLADB. And then we have a button to get our database object. When we click the button, we create a director object. And we get an iDatabase builder interface. And depending on which radio button was checked, we either create a SQL Server builder or an OLADB database builder. Once we've typed that builder object, we take the director and we call build using the builder. And then from there, we just get the database property off of the builder, and we have our database, and we can use it in our application code however we want. Here I've just shown a little example of grabbing the DB command, running some command text on it, and I don't actually need to set that command text property in this case. Opening the connection, creating a data reader. I would obviously do some reading in here, and then close the data reader, and the connection. The important part of this is that this code is the application code. It knows nothing about the process of building up the database connection and command objects. It knows nothing about SQL Server or OLADB or any of that. It only needs to know, I want to run commands, and here's the commands I want to run. So it cleans up the application code and gets it away from some of those lower level details that it shouldn't be concerned with. So the builder can be used to isolate application code from more complicated construction that shouldn't be in the application code. And we also use the abstract factory to isolate our database type from the application code. So again, we're simplifying the application. Our next creation pattern is the factory method pattern. We have essentially the same problem statement that we had for an abstract factory pattern. And in fact, the factory method pattern and the abstract factory pattern can be used in conjunction with each other, and we'll see that in the example. Our basic problem is that our app needs to support multiple database types. Maybe SQL Server, or Oracle, or MySQL, or maybe we're just setting the app up so that it can expand to a different database type in the future. For instance, we might be using MySQL now, but we expect great things and we're going to scale to a huge Oracle data farm later on. We don't want our app to know anything about the database type throughout the application code, so we don't want to have a bunch of switches that say, if it's a SQL Server command, do this. If it's a Oracle command, do that. We don't want all of that if-then kind of stuff in the app itself. We want to isolate that. In measurement, data can come from a lot of different sources. It might be a serial port source, or an Ethernet source, or a device driver, perhaps Modbus or OPC. There are a number of different places the data can come in. Measurement apps often have different data sources that combine. So you may have pressure sensors in one place and temperature sensors in another, and they're all coming in on different buses and different ports. We need to be able to manage that. But again, we don't want the data to be tangled up with the actual source type. And we don't want the code to deal with the source type to be spread throughout the application. And another possibility is we might need to create a different report type. The user may want to select a PDF type or a Word or maybe an Excel doc, and we'll need to be able to support those different report types. But again, we don't want the application and the report generator to really know anything about that. We want that area to understand about creating the data that they need. The actual formatting into a document should be done elsewhere. So what a factory method does is it provides a method to create class instances. If you remember in the abstract factory, we had different classes that inherited from an abstract class that presented a more generic interface that the application used. That was great, but what we didn't have was the creation part. In our application code, we had this if-then section. If it's SQL Server, create the SQL Server database class. Else, if it's Oracle, create the Oracle database class. And you can imagine, if we're going to do that throughout the application, that that's going to be messy. So we don't really want that. So the factory method provides us a nice way of creating those classes and isolating that from the application code. So we use this a lot with the abstract factory, and it provides us a nice single method for creating those applications. And again, it hides the details of creating objects from the rest of the application. And we did a similar kind of thing with the builder pattern. And in fact, when we get through this, you may see how you could use the abstract factory, the builder, and the factory method all in conjunction with each other to create a lot of different types of classes that have complicated construction methods. So the factory class will create an instance of a class that inherits or implements the abstract class. So as a basic example, we have an abstract factory that has our database abstract class, and it again has a connection property and a command property. And this is the same thing that we talked about in the abstract factory. Then we'll have SQL Server and OLADB derived classes. We could have Oracle classes or MySQL classes as well. Just more different types of database classes, and they're specific and they actually have implementation, where the abstract class does not have any particular implementation. And then we have an enum for the database type. And this is where we're starting to get into the factory method pattern. The enum will tell the factory method what type of database we want to create, whether it be SQL Server or OLADB or whatever. And then we'll have a database factory class for the actual database class creation. And this is going to be a single static method. We also have some implementation choices. The abstract factory pattern, of course, uses an abstract class. But we could also instead use an interface rather than the abstract class. So we can use the interface for the command property and the connection property instead of the abstract class. In the abstract factory example, you could see how the abstract class didn't actually have any implementation, so it could have easily been done with an interface. Now your mileage may vary on that. You may have some code that's common to all the different types of factory classes that you're creating that you do indeed want to be in that base class. But if you don't, an interface might be a better choice because it enforces that contract on all of the classes that implement it. And that's one of the important distinctions. The interface does require implementation in the concrete classes. So any class that's going to implement this interface is required to implement all of the methods, properties, and events on the interface. So your application code knows that it's going to have a consistent, fully implemented interface. And of course, the interface doesn't have any implementation within its code itself, so there's no base interface code or implementation. If you want or need that, in that case, you actually should use the abstract class. So a factory can return an interface rather than a class, and the use of abstract class might be appropriate as well. So again, this is one of those choices that you can make. In our class diagram, we have our database factory, and the database factory will be the factory method. And it will have a static method called createDatabase. And the parameter in createDatabase will be an enum, and that'll be that database type. And in this case, we just have SQL Server OLADB. And then you can see our interface for iDatabase, which has the command and connection properties. And then the implementation classes for SQL Server Database have a command and a connection. And the command and connection properties on the interface are going to be the abstract type DB connection and DB command. Whereas the SQL Server database, they will probably be of type SQL command and SQL connection, but those of course inherit from DB connection and DB command. And then OLADB is the same thing. There'll be an OLADB command and an OLE DB connection, and they inherit from DB command and DB connection. So both SQL Server Database and OLE DB Database implement the iDatabase interface, and the database factory method, createDatabase, is going to return a type iDatabase. It won't be returning a SQL Server database or an OLE DB database. Its return signature will be iDatabase, so it could return either the SQL Server or the OLE DB. So in that way, the only thing the application code needs to know is iDatabase. And the only thing the application has to know to build the iDatabase object is the database factory method, createDatabase. So there's not a whole lot of extra construction information that it needs to know. In fact, that factory method doesn't necessarily have to have a parameter of that database enum type. So the application doesn't even necessarily have to know that. It could come from a configuration file, for instance. On this installation, we're using SQL Server. Therefore, the enum is SQL Server, and the database factory reads that out of the configuration information, and the application essentially doesn't know anything about the type whatsoever. It just calls the database factory and says, create me a database, and it gets an object that implements iDatabase, and it goes from there, and is able to use it throughout the application code. So this really can isolate the application from all of those construction details. And if these classes that implement iDatabase were really complicated to build and had multi-step construction processes, then we could use a builder pattern within the database factory method pattern in order to create the database object and keep all of that nasty code isolated from the application. So in that case, we'd actually be using the abstract factory pattern, the builder pattern, and the factory method pattern all in conjunction with each other to create multi-type complex objects and keep all of that code completely isolated from the application. All of these three patterns are in a group called Creation Patterns. So they're all about creating objects and keeping all of that complicated creation logic away from the rest of the application code. The application code just wants to use the objects. It doesn't want to know the gory details about creating them. So that's the factory method pattern. And we'll be moving on to a code example in the next lesson. Let's move on to a code example of the factory method pattern. In this example, we're actually going to use the abstract factory in conjunction with the factory method, and we'll also see how to work with interfaces with those patterns. The factory method pattern is about object creation, and what we're interested in doing is creating multiple different objects with different database types. And this is the same basic idea that we had for the abstract factory pattern as well. But our application code had to understand and manage those different database types up in the creation process. We'd like to isolate that from our application code, and that's what the factory method will do for us. In our class diagram, we have a database factory, and this has really got the factory method, which is called createDatabase. Then we have the iDatabase interface. It has two properties on it, command and connection. In the abstract factory, this was an abstract class. But in our abstract factory example, it also had no implementation in it. So in this case, I'm going to make it an interface. And I'm going to have two classes that implement that interface, the SQL Server Database class and the OLE DB Database class. And both of those will implement the command and connection properties. And of course, they'll have private fields that correspond to those properties. And finally, we'll have an enum for our database type. And we'll just be supporting SQL Server in OLE DB. And of course, this general pattern applies to all database types, and you can apply it to data sources as well. For instance, if you were creating a measurement app and you were getting data from a serial port or perhaps an Ethernet connection or some other device drivers, you could create this same pattern for those different types. And your enum would reflect those different types. So here's our iDatabase interface. And this is the interface that the application will actually be using. So we'll call it iDatabase, and we'll have a connection property and a command property. Note I also did one other different thing from the abstract factory. The abstract factory used a DB connection type for the connection and a DB command type for the command. In this case, I'm using the interfaces instead. And again, you could support either way, and it really wouldn't matter for this particular example. I just wanted to demonstrate that you could use interface types for your properties and return methods, as well as using abstract classes for those returns. For that matter, you could use concrete classes as well, so long as they were more basic classes as opposed to a SQL Server DB connection. We're talking more like an integer or a string on the interface. Again, you can use interface types on your properties within your interface, or you could use class types as well. The choice is yours. Our SQL Server database class implements iDatabase, and it has private members of SQL connection type and SQL command type. But of course, it implements an IDB connection type, and that's the implementation of the iDatabase interface. SQL connection does implement IDB connection, so that's the object I'm actually going to return. So I'm going to lazy load the connection, meaning that I'll check to see if my connection member is null, and if it is, I'll get my connection string from the configuration manager and the connection strings object, and these connection strings are stored in appconfig. Once I get the connection string, I'll create a new SQL connection, and I'll set my private member equal to that new connection. And finally, I'll return that private member. If I've already gone through this creation process, I don't recreate it. So that's the lazy load aspect of this approach. And for IDB command, we're doing effectively the same thing. We're lazy loading the command object, and we'll create the command and set its connection. The OLADB database has the same sort of logic as well, both for IDB connection and IDB command. And all that is basically the abstract factory pattern, except I used an interface as opposed to an abstract class. Now, I also have my enum for my database type, and I'm supporting SQL Server and OLADB. And finally, we get to the database factory, and it has a public static method, meaning that I don't actually have to create an instance of the database factory to call this method. I simply call database factory dot create database. It'll return my iDatabase interface, or actually an object that implements iDatabase, and it takes a parameter, a database enum type. And I do a switch on that enum type, and if it's an OLADB type, I return an OLADB database. If it's a SQL Server type, I return a SQL Server database. So that's all this factory does. Now here's where you can use a little bit of an imagination. If I had multiple steps in the construction of these various objects, this is the area that I would probably use a builder pattern to create the more complex construction steps. So again, I wouldn't be passing that off to the application. I would be using a builder pattern within this factory method to create a complicated object. These database objects kind of create themselves a little bit, because when I call the command property on the database object, it goes through, it lazy loads itself, and in the process, it also lazy loads the underlying connection object. So those steps are somewhat handled automatically through that lazy load process. But there are going to be other types of objects that doesn't apply at all. For instance, if you're creating business objects, you may have an order and then a bunch of order details underneath it, and there's a complicated way of creating the order with its customer, which may be a customer object, address, which may be an address object, and then all of the order details, all of which are individual objects put into a collection. That may be a fairly lengthy and complicated way of creating an object. In that case, you would use a builder to create that object within this factory method. So you would end up, instead of newing the object right here, you would call the builder build method and then return the output of that build. So that's how you could use that in conjunction with a factory method as well. So now we can use all three, the abstract factory, the factory method, and the builder pattern in conjunction with each other. Finally, we get to the application. And all we're doing on our getDatabaseClick method is we're creating an iDatabase interface object, and we just set our database type to a default of SQL Server. The form has a radio button, and if OLADB is checked, then we'll set that database type to OLADB. Then we'll use our database factory to create the database of the appropriate type. And this database object implements the iDatabase interface. And that iDatabase interface is all that the application code knows about this object. It's all it has to know, and it's all it really wants to know. So off of that interface, it knows that there's a command property, and that the command property is IDB command type. It doesn't know that it's a SQL Server command type or an OLADB command type. All it knows is IDB command, and again, that's all it needs to know. And from there, it can run its command. So it can set a command type, a command text, it can open the underlying connection on the command, create an iData reader, again, not a typed reader, not necessarily a SQL Server or an OLE just an iData reader. Do the read, close the reader, close the connection. So it can do all of the database operations that it needs to do. So now we've hid all of that relatively nasty object creation logic away from the application. Now this is just one method, and it would seem to be a little bit underwhelming that we're going to be saving a whole lot. But if you could imagine this as part of a data layer, and that every time we have some sort of method that calls querying for a customer, or querying for orders, or querying for product information, we have to open up the database and get the database command object every single time. Now, of course, we would like to call that in one method. This is the way of putting that into that method and then also offloading our data layer with all of that creation stuff that's really at a lower level than we'd like the data layer to know about. So that's how we can use the factory method pattern in conjunction with the abstract factory to hide from our application relatively complex object creation code. The next pattern I'd like to talk about is the prototype pattern. Now, why would we need a prototype pattern? Essentially, our app needs copies of objects. The objects may not have simple value types for properties. They may, in fact, have other objects that are properties, and those objects might include properties that are of other object types. So we can get complex objects that we need copies of for our application. For example, we might have a user object that we want to pass around from page to page or screen to screen in an application. Now, at the top level, the user object might have a name, a username, and password properties, and those are easy to copy. But then it may further have an address object property, or addresses, perhaps one for home and one for business. And then it might have an account property as well, or accounts. For instance, if we had credit card accounts associated with that user. So we can get deeper and deeper into the user object, and it makes the copy process more and more complex. Much like the builder pattern, we want to isolate all of that code from our application. We don't want to repeat all of this copy code that dives into objects and copies every property of objects and all that all over the place in our code. So the definition of a prototype pattern by the Gang of Four is to specify the kind of objects to create using a prototypical instance and create new objects by copying this prototype. So essentially what we're saying is we want to create a single object and an instance of that single object, and then create the new objects just by copying that, using it as a prototype or a template. In our implementation, we want to provide a method on the object to copy itself. In .NET, we use the iClonable interface, and the iClonable interface has a single method to it called clone, and clone will return a copy of a given object. And we also have to talk about deep and shallow copies. So as an example, we want to copy a user object. So we have a user abstract class that has the name, username, and password properties. It also has some address object properties. Because we're going to make it a prototype, we're going to provide a clone method, or two, depending upon the example. In actuality, you'll probably just have one clone method. And that clone method will be the implementation of the iClonable interface. Now, the user class is an abstract class, so we want to create some instances. So our application might have administrative users, guest users, customer users, different kinds of users. So let's just talk about an admin user. We're going to create an admin-derived class, and it's going to implement the iClonable and clone method. All of the other classes would actually probably have similar implementations, but they might have different properties depending upon their capabilities. For instance, an administrator class would probably have a few extra properties compared to a guest class. So a shallow copy might use the memberwise clone method. An object has a memberwise clone method. You get that for free in .NET. And what it does is it copies the properties of the object and essentially makes a copy of it. However, it copies references to the object properties. So in our case with the user, it will copy a reference of the address, not make a deep copy, which means that if I make changes to that clone, to that copy, the changes will also go back to the original. Now, this may be what you want, but it's often not the behavior you're expecting at all. In all likelihood, you'll want to provide a deep copy for your clone method. A deep copy will copy the values of all of the properties, including the properties of sub-objects. So in our user case, it will copy the username, the name, the password, but it will also go into the address property and copy the address, city, state, and zip, and make actual copies of that, as opposed to just copying a reference of the address object. So that's a really important distinction. So although memberwise clone is easy to use and doesn't take a whole lot of code, there is that nasty side effect that can really get you into trouble. So here's what our class diagram looks like. And it really isn't a whole lot in terms of the classes. We have our user abstract class, which we have a business address object and a home address object. Then we have first name, last name, password, and username. Some very simple user objects. Then it has two methods, clone and deep clone. And you'll note that up top there, it says we're implementing the iClonable interface. Clone is the method that implements that interface. I've provided both methods, and we'll see them in the example just to show you the difference between a shallow copy and a deep copy. For practical use, you're just going to want to provide a clone method and make that choice as to whether it's going to be shallow or deep, and not create a lot of confusion by providing multiple clone choices. In terms of class design, we really just want one method to accomplish that task. Then we have our derived admin class, and it has all the same properties, and then it implements the clone and deep clone methods. And then down below, you can see the address object. Simply address 1, address 2, city, state, and zip. So that's the pattern, and of course the really important detail is actually in the clone method. So we'll be taking a look at the details of that in our code example. So let's do some coding with the prototype pattern. Here's our class diagram, and we have an abstract class called user, and it has simple properties of first name, last name, password, and username. And it also has two properties, business address and home address, which are of address object type. And the address object simply has address 1, address 2, city, state, and zip. Then we have a derived class of user called admin, and it implements the clone and deep clone method. Now the prototype pattern is really not about the properties so much, but these clone methods. So our abstract class implements iClonable, and our clone method is on the iClonable interface. I've also added a deep clone method in order to show you the difference between a shallow copy and a deep copy. So it's really a pretty simple class diagram. The devil is in the details in the clone methods. So here's our user class, which again is an abstract class and implements iClonable. And our clone method is the implementation of that interface. And note that it returns an object. Because it's an interface and it's a generic interface that can be used on any object, it has to return an object as opposed to our specific type. We also have properties for first name, last name, username, password, etc., and then these address objects for home address and business address. And as I mentioned, the address class is a very simple storage class for address information. So our admin class derives from user, and the important part of the admin class are the two methods, clone and deep clone. Our clone method, that is the implementation of iClonable, simply calls memberwise clone. Memberwise clone can be called on any object. It will create, however, a shallow copy. So our address objects will be copied as references rather than going deep into the address objects and copying each individual property. And we'll see the effect of what that means when we actually run the example. So for our case, our clone method is just going to call a memberwise clone. I have another method called deep clone. In this case, I do the memberwise clone to get my base admin object, and then I turn around and I make deep copies for the home address. So I take the home address, create a new address object, rather than just copying the reference, and then set each individual property based on the home address value of this admin user. I do the same thing with the business address. And again, the important thing is that I'm creating a new address object rather than copying a reference. So here's our form design. We have a bunch of entry fields for the name information, the home address information, and the business address information. This is not a particularly user-friendly form, by the way. The important thing is that we'll demonstrate the different types of clones that we have. So we have a button that will actually create our user, and the two different clones. Then we have an edit button that will make a change to our original prototype. Over in this area, we have some labels, and we'll just use these in order to read the clone and the deep clone to see what happens after that edit. In our form code, we have an admin user, an admin clone, which is going to be a shallow copy, and an admin deep clone, which obviously is going to be a deep copy. On create, we're creating a new admin object, and just setting all of the properties to the entries that were made by the user. For our admin clone, we call the clone method on our original admin object. And for the deep clone, we call the deep clone method. So nothing earth-shattering there. Our edit button is even less earth-shattering. We simply go through all of those fields and set the properties on our original admin object. When I click the read clone button, I set the various label texts equal to the properties on the admin clone object. In the read deep clone button, we again set the label properties, but this time to, you guessed it, the admin deep clone object. So not really complicated code at all here. So let's give her a run. So here's our app with our pre-populated fields because you don't want to watch me type. So I've now created my objects, and let's read the clone, and we can see the properties are as expected. And we'll read the deep clone. Properties are exactly the same. So let's make a change to the name. We'll give them a middle name, and we'll edit that. And we'll read our clone, and nothing changed in the clone because I made the edit to the original admin object. And when I read my deep clone, again, nothing changed. Great, that's exactly what I would expect. Let's do something with the business address. Let's get rid of that address to line. And again, we'll click edit. Let's read the deep clone. Nothing changed. Great, exactly what I expect. How about the shallow copy? Whoops, there goes my address to line. That's because the shallow copy has a reference to the address object, and it didn't make a full deep copy of it. If you can imagine this, both the original and the clone are sharing the same address object instance. If anything happens to either one of those objects, it will affect the other. So if I'm intending to pass a customer object over to another form or page that really shouldn't be editing the original object, and I have it linked up to a database so that any edits that happen to that object get stored into the database, but that copy isn't really supposed to be editing the original, you can see that really bad things can happen and your database data can be completely corrupted. If we're doing this, for instance, with credit card accounts, and we're letting them add credit card accounts, and we're cloning the prototype because we want to use the same billing address that they've used previously. If the credit card information is on a sub-object, and they edit the credit card number, and we've made a shallow copy, we're going to edit the credit card number of the original card that we copied. In which case, both of their credit card numbers are going to be the same, so the information from that original card is going to be lost. So they won't actually have added anything at all. They'll basically have created two copies of the same information for their credit card, not what they would have expected at all. So it's really important to understand the difference between a shallow and a deep copy. When you're implementing the iClonable interface, it's really important to understand the difference between shallow and deep copies. And in all likelihood, you're probably going to choose deep. The only reason not to is because of any kind of performance hit if you're creating a really complicated object and there's a whole lot of sub-objects that you're looping through and copying properties, and you just don't need to because it's a read-only thing that you're going to be passing. But you have to be aware that that clone method may be used for other purposes that you didn't foresee later on. And the people who use the clone method are not necessarily going to be aware of the details. So they may clone that object, make it writable in some way, and fully expect that that's going to work as expected. If you've done a shallow copy, there might be a problem there. So that's something to consider when you're implementing a prototype pattern. You may well have heard of our next pattern, the Singleton pattern. The Singleton pattern is probably the most used single design pattern, and it's probably also the simplest. So our app needs a single instance of an object throughout the app. We might need it for an exception logging manager, so that we only have one class that deals with a single text file or whatever format we're logging into. We don't want to have a lot of conflicts in attempting to write to that logging manager through a multi-threaded app. We might have database or business layer managers that the rest of the application needs to use, but we certainly don't want to create a whole lot of instances of those. They could be very heavy, and there's no need for them to have different instances. We're only really talking to one database or one business layer. Also, if we're using hardware access, for instance, we're calling up a TCP socket or a serial port, well, there's only one of those, so we better not try to access it from multiple places. We'll end up with busy errors or collisions, basically bad stuff. So the singleton is a really simple pattern, and it's really commonly used, and you may well be aware of it already. It'll create us a single instance of an object, and only one instance of an object, and we can call that throughout our application. It does that by actually storing the single instance in a static private member. And it has a private constructor, so the rest of the application cannot call a constructor on it. Then it provides a public instance property that returns the static private instance. That could also be a getInstance method. I've seen it done both ways. I'm not sure that it makes a big difference in C# as to which you use. I kind of actually prefer the property just because of the way the code looks throughout the application in using that property. So in our example, we want an exception handler class. So anytime we have an exception during an application, we want to use this exception handler class. And for our example, we'll just write to a single log file. But there could be a lot of other things that an exception handler does as well. It could actually manage the display of the error to the user, do translations for error messages, write to log files, write to Windows event logs, write to the database if the logging is done there. There's a lot of things that you could do within an exception handler class. No matter, we need a singleton for that because we really only want one central area to handle our exceptions for our application. In our case, we're just going to write to the single log file, and as I mentioned before, we'll have a private static instance member, and that will be, of course, exception handler class type. We'll also have a private constructor, so it won't be able to be called throughout the application. And then we'll have our public instance property, which again will be of type exception handler. And the exception handler will have a single method, writeException, and that will, of course, be a public method, and that's what we'll be using within our application. And here's our class diagram. The exception handler is over on the left, and you can see the private fields. We have the instance field. We also have a lock object that we're going to use to make our instance property thread safe. And we have the stream writer that we're going to use to actually write the exception log. We have methods, and as you can see, the first is the exception handler constructor, and it's private. And we also have writeExceptionLog, which is public. Then in our example, we'll have a couple of forms, and they'll have buttons on each called Do Something Bad. So they'll throw an exception, and then we'll have the exception handler handle it. And then form 1 will be able to go to form 2, so we'll be able to see that both of these forms get the same instance of the exception handler, and it works just fine. So that's the singleton, probably the simplest pattern you'll ever see. This will be our code example for the singleton pattern. You may well have already created singletons, so this will probably be a little bit of a review, but there is one thing that we'll talk about that may be a little bit different than what you've done before. This is our class diagram, and we have a class exception handler, which we're going to use as a singleton. It has an instance field, and that's going to be a shared private. It also has a lock object that we'll talk about, and our exception handler is going to write to a log file. So we have a stream writer field to handle that writing. And we have a public property called instance, which will return our singleton exception handler. It's going to return that private instance field. Then we have a constructor, and it's going to be a private constructor. And then we'll have a public method for writing the exception log. And we'll have two forms, and we'll take a look at those. So here's our exception handler. There's our private static instance. And you'll note the constructor is private as well. In the constructor, we got our executable path, because we're going to log in the path of the executable. And then we create our stream writer, combining the executable path and a file name. Please excuse the hard-coded file name. Now the important thing here is that this is a private constructor, so the application cannot create instances of the exception handler by calling the constructor. The way it can get an instance of the exception handler is to call the property instance. And we'll take a look at this inner part first, and then we'll talk about the locks. We're going to lazy load the instance, so we'll check to see if it's null, and if it is, our private member will be created as a new exception handler. And then we'll return that private member. If it's already been created, we won't recreate it. So that's the lazy load aspect of that. And it is a static, so there's only going to be one instance of the exception handler instance property. So now let's talk about this lock. If I just use this code, this is not thread safe. So if I had a web application that probably has a lot of users and a lot of different threads, this one could cause me a bit of trouble because I could check the instance equal to null, and then someone else could be checking the instance equal to null right about the same time, and then we'd both be creating new instances of the exception handler and colliding on that variable. Not what we're really interested in doing. So what we do is create a static object called lock. And we lock on that object. Then we run our instance creation code, and then we return the instance outside of the lock. So this just creates a little bit of a block on the thread. There is a performance penalty in doing it this way, and you might be tempted to also put the lock within the instance equal to null check. And that works for the most part, but it's not truly thread safe. So your mileage may vary on how you want to approach this. You can also just simply create the instance right away up in this private static, and that way you don't have to check if it's null. So you'll never have to go through this lazy load code. Again, it depends on what you're creating. For this exception handler, I wouldn't have any problem in just creating it right up here. It's likely that we're going to want it. For some other implementation or some other object, we may not want to create it unless we truly actually need it and are going to be using it. We may just be wasting memory. So just remember the threads are something to consider when you're working with this. Finally, our exception handler actually does write to an exception log. So we have a method for that, and we get passed in an exception. We create a string builder object, and we first get the date time of now and format that. Put a little colon and a space in between that and our exception message. Once that's all appended, we write that line to our exception log file, and we flush so that it writes. So that's actually all that our exception handler does. Now we might, if we were going to program a really full-featured application, want to do a lot more in our exception handling. We might want to translate error messages for the user to give them a user-friendly error message while logging the technical details elsewhere. We may want to use the Windows event log as opposed to a text file. There are a number of things that we might want to do in an exception handler. But the point of this is just to make it a singleton class. And that logic is up here. So to prove it out, here's our very basic form. We have one button to do something bad. And with that, we're going to call the exception handler. Then we have another button to go to a second form. And that second form cleverly has a button to do something bad. In our first form, the do something bad button, when it's clicked, will throw a new exception, saying that form 1 did something bad. And of course, we're putting that in a try catch. So we catch our exception, and then we call our exception handler, get its instance, and write the exception, and pass in our exception parameter. I mentioned in the PowerPoint discussion about the singleton class that you can also use a getInstance method or something like that instead of an instance property. My personal preference is to use an instance property just because I think this looks a little bit better than having a method right in the middle of everything. Your mileage, again, may vary on that. And of course, when we go to Form 2, we just create our Form 2 object and show it as a dialog. In Form 2, our do something bad does exactly the same thing, except it just makes sure that it says Form 2 did something bad. So let's give this a run and see that we actually access the file properly. Here's our Form 1, and we're going to go and do something bad, and you can actually see on my application output that there was a first chance exception, which of course is what we were trying to create. We'll go to Form 2, and we'll do something bad again. And again, we got another first chance exception. We'll stop debugging, and we'll take a look at our exception log file. And there it is, with the date, time, and Form 1 did something bad, and again the date, time, and Form 2 did something bad. So that was what we were going for. The file was opened correctly, and I misspelled something. always make sure that you spell check things before you actually write them out, particularly to a public interface. However, we do have a properly functioning singleton object, and that's what we really wanted. Our first structural pattern is the adapter pattern. The classic physical analogy is when you have an electrical outlet and you've gone to a foreign country, and sometimes you need a converter or an adapter to fit in that foreign country's sockets, because some of them are 50 Hertz and the US is 60 Hertz. So depending on which way you're going, you may need to go from 50 to 60 or 60 to 50. The adapter pattern is similar in that respect, in that you need to adapt one type of class into another type of class. So you've got an object that needs converting, and needs converting to a different type because that's what the rest of your application needs. But the types are likely similar. Obviously, you're not going to be converting a cat to a fire hydrant. One example of this is data transfer objects, or DTOs, to business objects. A data transfer object is often some kind of data that comes from a web service, and it will need conversion into the business objects that the rest of your application uses. Another possibility are third-party objects. Your application may collect data from multiple sources. Perhaps you're collecting a lot of users or a lot of customer names, but all these third-party objects come in different forms, and they need to be converted into a common form so you can aggregate them and use them together. So the adapter pattern provides an interface that the application is going to use, and the interface has the methods that the adapter will implement. The adapter class that implements that interface does the conversion. So it will do the conversion of different object types. In our examples, we've kind of focused on data classes, but the object types can be methods as well. So it doesn't have to be just a data storage class that we're converting using the adapter. It can also be any kind of class, and that class can be more focused on method implementations than it is on data properties. It doesn't really matter in terms of what the adapter does. The adapter just needs to be able to convert from one class type to another. Here's our example. We need a customer business object, and that's what's used throughout our application. We have a customer data transfer object, and it comes from a web service. Its properties are different than our business object customer's properties. Not tremendously different, just different enough that we can't use the DTO throughout the application. And we may have other customer DTO types that come in from other sources that we have to aggregate and put together as a single customer type. So in our example, we'll have an iCustomer list. And this is going to be the interface that the application uses. It'll have a getCustomers method, and that will return a list of business object customers. It'll also have an addCustomer method, and that will take a customer DTO parameter. In the implementation of the addCustomer method, it'll convert the customer DTO to a customer and add it to the customers list that will end up being returned by getCustomers. So that interface essentially has two ends. On one end, the application is using getCustomers to get a list of business object customers. On the other end, we're using the addCustomer method to take a customer DTO and convert it over. So in our actual implementation classes, we'll just call that customer adapter. It implements getCustomers and addCustomer. In our class diagram, you can see on the left, we have our customer business object, and it has properties for address, city, customer ID, name, state, and zip. On the right, we have our customer DTO object, and it has properties for address, city, and then it has first name and last name as opposed to a single property for name. It has ID instead of customer ID, and it more correctly uses postal code as opposed to zip. So there are some differences, although those two objects are very similar. And the customer adapter class implements iCustomerList. It has an internal field, a list of customers, and those customers are of the business object customer type. And then it has the two methods that we talked about, addCustomer and getCustomers. So that's the adapter, and as you can see, structurally it's pretty simple. It's basically only going to be a single class that implements an interface. But of course, depending on the types of classes that it needs to adapt, and the complexity in terms of converting them from one to the other, the actual customer adapter class, or any adapter class, may be a little bit more complicated than it looks like on this diagram. This is our sample app for our adapter class. And what we're trying to do in this application is take a customer data transfer object that we might have gotten from a web service, and convert it over to a customer business object that the application likes to use. And we're going to use the adapter pattern to do that conversion. So we have our customer DTO, and it has properties, address, city, and it separates first name and last name, unlike our customer business object. It also has a property for postal code rather than zip code. Our customer business object has similar but different properties, and a different number of them. So our name actually implies that it has the first and last name combined, and we have a zip code as opposed to a postal code. A little bit of sloppiness there. We have an interface called iCustomerList, and that interface has two methods. One is addCustomer, and that will take a customer DTO as a parameter, and the intention is that it will convert that customer DTO into a business customer object and add it to a list. Then we have a getCustomers method, and it will return the list of business object customers. And we have our concrete implementation of that interface, and of course it has the two methods and an internal field for the list of customers. So very simply, here's our customer DTO object, and all it is a storage class. In a practical real world, it still would probably be a fairly simple class. That's the idea of DTOs, but it might come from another outside source. And our customer business object, again, a storage class. Nothing special here. And we see our interface for iCustomerList, and it was exactly as described in the class diagram. A method for getCustomers and a method for addCustomer. Finally, we get to our actual adapter implementation, and this is where the meat is. Our customer adapter implements iCustomerList. We have an internal member called Customers, which is a list of business object customers. Now we need to implement the two methods on the interface. So we have getCustomers, and again, it returns a list of business object customers. So all it does is returns our internal member. addCustomer isn't really all that hard either, but it comes to the whole root of what an adapter does. addCustomer, we're getting a customer DTO object, and we need to effectively adapt it into a business object customer. So we take our customer DTO and we create a new customer object out of it. And we simply new up a customer and then set the appropriate properties, including that name property that combines first name and last name. So there's nothing particularly tricky in this code. It's just the pattern that you follow. You may also see it implemented actually right in the customer object itself, where the customer object has a constructor that would take a customer DTO. That's a fairly tight coupling, and that might not be what you want to do, and it might put a little bit of weight on the customer object that is unnecessary. So to test this out, we've got our form, and we have a button for adding a customer, and then a button for getting customers, and a list to present them. And this form will show us how we use the adapter. So when we create the form, we have a private member called customer list, and it's of type iCustomerList. So again, it's looking at the interface type rather than the actual adapter type. Now we instantiate it as a customer adapter, but we're still, with the rest of the application, only looking at iCustomerList. I also just started a dummy integer counter for customer ID. So every time we click Add Customer, we're going to create a customer DTO. And we'll new that up with that dummy customer ID that I've created, give it a first name, and the last name, cleverly, will be the customer ID. And we'll just leave the address, city, and postal code blank for the example. It doesn't really matter. Of course, in a real-world example, this DTO data is going to come from a real data source, and your customers will probably have real names. Hopefully, anyway. Once we create the customer DTO, we call our customer list interface and call the add customer method on that interface and pass in our DTO. So we're just building up a list of customer objects in that customer list every time we click add, and we increment our customer ID. So if we click the button 10 times, we'll end up with 10 new customers in this list. When we click Get Customers, we're going to first clear our list, so it will be empty, and we'll reload all of the customers. Your mileage may vary in a real implementation on this, but that's not the point of the adapter pattern. Then we get a list of business customer objects by calling our customer list and the Get Customers method on that. So now you can see the adapter at work. This is the output of the adapter. I'm getting the customers, which are business object customer types. The add customer method on that adapter worked the other end and took an input of customer DTO types. So we're adapting that customer DTO to a business object customer. Once we have our list, we just loop through it and add each one of those customers to our display list. So let's just make sure we got that right. I'm going to add 5 customers. 1, 2, 3, 4, 5. And then I'll get them, and there they are. Of course, you'll have to trust me that all the types came out right, but if they didn't, we would have had compiler errors and all sorts of problems. So that's what the adapter pattern is for, to convert one type to another type. We'll continue with our structural patterns with the bridge pattern. And the bridge pattern is an interesting pattern, and it's going to share some similarities with some other patterns that we've seen before. The bridge pattern is for if you want to decouple the application from a feature implementation, or effectively decouple 2 classes, so that the 2 classes really don't know anything about each other, and if one of them changes, the other one doesn't have to adapt to that change. The intent is that the bridge in between those 2 classes will decouple them to the extent that neither one of them has to change. Now, it's kind of a bit of a perfect world, and actually in a perfect world, our classes would be so well written and encapsulated that implementation changes wouldn't affect any class that calls them. But in the real world, those changes may in fact affect other classes. So what our bridge does is it tries to isolate the impact of those changes. It also allows us to think about different types and future expansions. So for instance, we want to do some messaging in our application. And initially, we're going to implement SMS. But we know in the future, we're going to implement email and then all the other chat services and APIs, and that messaging interface is probably going to change a lot. We don't want the rest of the application to know anything about those changes. So we're going to put a bridge in between our application and the messaging service, so that effectively the application knows about messaging, but it doesn't necessarily have to adapt itself to what type of messaging service is being used. Social media is the same kind of concept. We may want to do posts to Twitter. Okay, so we can implement that easily enough, but then we want to expand and be able to post to Facebook and to other social media. And all of a sudden the interface starts to change with each one of those social networking outlets that we're choosing to post to. So again, we want to hide that from our application. The best way to do that is to put a bridge in between the two, so that when we've initially written the application, we've at least had to think about that to present a more generic interface to the application, and then the bridge will handle the details of interfacing with Twitter and Facebook and the like. We have the same kind of concept with logging. Again, we can log to files, databases, Windows, event viewers, so we have different types of logging, but we don't want the application necessarily know anything about that. We also can have different data sources. We may be pulling in data sources from web services, from a local database. Again, the application hopefully is decoupled from all of those classes, and the bridge helps enforce that. By the way, does that logging and data source stuff sound a little bit familiar? If it does, you may have seen the factory pattern lessons. And the bridge has similarities to the factory, but it's a little bit different in what it's intending to do. The factory patterns are creation patterns, so we're creating logging services and data sources. The bridge is really a bridge between classes and not a creation type of pattern. So it's slightly different, but some of the problems we're dealing with are similar. So you might guess that you might combine factory patterns and bridges together in order to isolate application code from these different kinds of features. So the idea behind a bridge is to decouple an abstraction from its implementation so that the two can vary independently. That's the definition out of the Gang of Four. What that means is the application is going to be written towards the abstraction, and the implementation is going to be written away from that, so that the actual application classes aren't talking to the specific implementation classes. There's a bridge in between them, and that in fact decouples them from each other and hopefully protects them from changes from each other. The idea is to provide an abstract class or an interface, and then feature classes will be concrete implementations of the abstract bridge class. And the abstraction class is used by the application. And please note, abstraction doesn't necessarily equal abstract class. An abstraction can actually be a concrete class in itself, or implement an interface. The terms don't mean quite the same thing in this pattern, and because the words are really close, there can be some confusion there. So for our example, we're going to do a messaging feature. We're going to implement SMS or email, and those are going to be the choices for our customers. In the future, we expect that we're going to want other types of messaging. And there's all sorts of APIs for messaging apps out there, and we know that there's all sorts of work that we're going to need to do, and all of those interfaces and implementations are all different, and we're going to have to work with all of that, and we don't want the application to have all of those changes filter through it. So we create an iMessage interface for our abstraction. This is not an abstract class, it's actually an interface that's being used as the abstraction that the application is going to talk to. And that iMessage interface has a send message method. Very simple, so that's all the application needs to know about. Then there will be concrete SMS message and email message classes, and those will implement the iMessage interface. So that should have sounded a little bit familiar, similar to a factory that has an interface that's presented to the application, and then a couple of underlying concrete types. But again, a factory pattern is a creational pattern, so we're talking about creating classes, whereas a bridge, classes are already somewhat assumed to be created, and we're actually talking about using them in the full implementation. Then we have a message controller class, and this is going to be an abstraction class, and it'll have that send message and set message type method, and it will decouple the iMessage and the concrete implementations from the rest of the application. So this is what's going to sit in between those two. So you can think of this as the actual bridge class, although the entire pattern is the relationship between all of these classes. So a picture hopefully covers 1,000 words. So we have our message controller class, and it's got a property of a message object, and that's actually going to have an iMessage implementation. And then it has the two methods, send message and set message type. And those are going to be used by the application. We have a little enum for message type. And as we grow, that enum will grow. Then we have the iMessage interface, and it has a send message method on it as well. Now the send message method for the message controller and the send message method for iMessage don't necessarily need to be the same signature. Message controller doesn't implement iMessage. It actually uses iMessage on that message property within it. So the send message can be completely different. And in fact, they don't have to share the same method name. They're completely different classes. And then we have SMS message and email message that implement iMessage. And of course, those send message methods do have to implement the signature of iMessage. So that's the idea behind the bridge. And I do encourage you to take a walk through the sample with me in the next lesson because that will help. This is our code example of the bridge pattern. And the basic idea behind this application is that we want to be able to send some sort of message. Now, initially, our application is just going to support SMS and email messages. But we expect great success, and with that great success, we expect to have to send all sorts of different kinds of message types. We'll probably have to use all sorts of different chat APIs and probably create our own API as well. So there's going to be a lot of things that go on with sending different messages and users being able to choose whatever message type or provider they like. So we expect a lot of churn and change in that area, but we don't want that change to have to filter through all of the application code. We want to try to isolate that. So we're going to use a bridge pattern to isolate all the details of that messaging away from the rest of the application. So in our application, we have an interface called iMessage. And at this point, it's very simple. It has one method in it called send message. We have two classes that are going to implement iMessage, the SMS message class and the email message class. And we'll have a message type enum. And at this point, it will just have the two options, SMS and email. Then we'll have our bridge class, which I've called message controller. It'll have a property for the message, which is actually an object that implements iMessage. And we also have two methods, one called setMessageType, which the client application can set the message type to be used, whether it be email or SMS. And then a second method called sendMessage. Now the sendMessage on the message controller is not necessarily the same signature as the sendMessage on iMessage. Message Controller does not implement the iMessage interface. It has that one message property that is of type iMessage, but the controller itself does not implement iMessage. And then we have our form, or our client, that will use the message controller. So the flow will be it wants to set the message type, and then it will send the message. We'll take a look at iMessage, which very simply has a send message method. And there's a string for a to and a string for the message. Obviously, as we expand, we'll probably want to expand this message signature as well, and we may need to put in some other things for authentication and the like. Our email message descends from iMessage and implements send message. As you can see, our implementation is a little bit lacking at this point. We've left that for you. The SMS message also implements iMessage. And the email message and the SMS message are known as concrete implementers in a bridge pattern. So that may be a piece of terminology that you'll see from time to time. So the SMS message implements iMessage by implementing the method sendMessage. And maybe we'll use Twilio for that implementation. Again, we're a little light on the implementation tonight. Then we have our message controller. And this is really the bridge class. It has our member for message, which is of type iMessage, meaning that any object that we have here will implement the iMessage interface. Then we have the method setMessageType, and depending on which message type, it'll create a message object of either email message or SMS message. So if the user tells us that they want to send an SMS message, we'll create a concrete implementation class of SMS message type. If they want to send email, we'll create an email message type. Then we also have a public method called sendMessage. And again, it takes parameters for to and message. And it will simply, on the message object that it has, call sendMessage. And note, the message controller does not implement iMessage. So here's our little messaging form that we're going to have. And we have radios for the user to choose what type of message, either SMS or email, and a to area, pre-populated with a bogus SMS phone number, and a message area. This is really a pretty poor user interface. And the reason is, SMS and email messages really have very different characteristics in terms of what they expect for a to and for a message. Obviously, an SMS expects a phone number for a to property, whereas email expects a valid email address. And we have a free-form entry for either one of those. We'd really like to hook this up to some sort of address book probably, so that we don't have users mistyping email addresses, which they do all the time, or attempting to remember phone numbers, because who actually remembers phone numbers anymore? Everybody uses address books. Also in the message area, it's a fairly large text box. And of course you're familiar, SMS is limited to the number of characters we can send, and I'll bet you this text box does not limit how many characters that can be sent for SMS. Of course, email doesn't have that limitation. So essentially, this form is ill-suited for either SMS or email because it makes compromises to support both. So just a little bit of a usability hint, you have to think about how the user will use the form and try to avoid allowing them to make errors when they use the form. So we do have this ugly messaging form, and on the send button, if the radio button SMS is checked, we'll call the message controller and we'll set the message type, and we'll set it to message type SMS. Otherwise, they're sending an email, so we'll call the message controller and set the message type to email. After we've set the message type, we'll send the message, and we'll read those nasty text fields for to and message. And again, we're calling send message on the message controller. And the message controller is the thing that actually calls send message on the iMessage interface. And that's really the whole point of the bridge pattern. The application will only know this end of it. It'll only know the send message and the set message methods of that message controller. It won't know the ins and outs of even iMessage, so that it won't have to worry about any of the changes that are going to occur on that end. For instance, we may need authentication, and probably do need authentication for email, but our application doesn't necessarily have to know anything about that. It may come from a database configuration for a user, or it may come from a config file, and the message controller can deal with that, or the email message class can deal with that. But our application doesn't want to know anything about that. And of course, when we go into other APIs, their authentication schemes may differ. So we don't want to have the application have to understand all of those different iterations and requirements of the different messaging schemes. The application really just wants to know, I'm going to send a message of this type, and here's the message, just send it. So that's really that division of concerns and that isolation that the bridge pattern gives us. I'm sure you've actually seen the composite pattern before, but you might have called it something else. You might be familiar with a tree view, or you might be familiar with nodes in XML documents. Those are all composite patterns. So the general problem that a composite pattern solves is that you have an object that is composed of similar child objects, and each of those children may have their own children, and so on, so you get a family tree. So you commonly see it in a tree view, as I said, and that's the visual representation. But you also see it in XML or HTML DOM docs as well, where you have nodes. The one subtle little difference there is that with a composite pattern, all of the objects within the tree are of a similar type. So a node and an element might be a little bit different in an XML doc and may not descend from the same type. A composite pattern tries to allow them to descend from the same type so they can all be treated the same way. Another example would, of course, be a file system folder. Or you can have supervisor employees, the notorious org chart. And yes, I did find an image of the Northwind database org chart. If you're doing a social networking app, users and followers. A user may have a bunch of followers who have a bunch of followers, and onward, onward, onward. It's the whole basis of LinkedIn and Facebook, of course. All of those relationships. And then if you're interested in actual hardware, manufacturing assemblies. So if you have a piece of hardware, perhaps a car, it consists of more assemblies. And those assemblies consist of assemblies. And then you finally get down to the individual nuts and bolts, the individual parts. So the formal definition is that the composite pattern composes objects into tree structures to represent part-whole hierarchies. And the composite lets clients treat individual objects and compositions of objects uniformly. And that's the part where all of the objects descend from the same class. I can treat a parent node the same as I would treat an individual element. So each one of those objects descends from an abstract class, or implements an interface. And that abstract class or interface is common to each one of the objects in the composite. And then, of course, the parent objects will have a collection of children objects. So for our example, instead of the classic org chart, I thought we might do a manufacturing parts list. So each of our end products contains a number of assemblies. For instance, that circuit board down there. If we're going to be building computers, we have a chassis, we have circuit boards, we have RAM, we have hard drives, DVDs if we're not Apple. So there are a number of different assemblies and individual parts that go into the making of a computer. And each one of those assemblies, of course, may contain parts. A power supply contains a transformer and cable, and each assembly may also contain other assemblies. So for example, the display can also contain a screen assembly. So for our example, we're going to have a base assembly abstract class. And it could be an interface, but for this example, we'll use an abstract class. And because all we're doing is creating the parts list, we're only going to have two members on that abstract class. The quantity, the number of parts we need, and the name, just the name of the assembly. Obviously, if we're going to do this in a real manufacturing facility, we'd probably want part numbers and manufacturer numbers and manufacturers and quality levels and all sorts of good stuff. But in order to just demonstrate the composite pattern, we'll simplify that part and just use quantity and name. Then we'll also have a write parts list method. And our client is going to ask all of the objects in the composite to write the parts list. And they'll essentially write themselves and any children they have. And then there will be add and remove methods in parent assemblies. So the parent assemblies will be able to add and remove child assemblies. So we'll have two different classes that will implement our abstract interface. The first will be an assembly implementation class, and that's effectively a parent. So it can have an internal collection of child assemblies. And the children are also base assembly types, which means that they can also be either a parent or a simple child object. The write parts list method, in addition to writing the information for this particular assembly, will also call the same method on all of the children of the assembly to get them to write their information to the parts list. The other concrete implementation we'll have is a part class, and the part will be a basic part like a nut or a bolt. It won't have any children objects, so it also will not implement add and remove. In the example, we're going to throw an exception. Now this is where it becomes a little bit interesting, and it gets to your choices of an abstract class or an interface. An interface would require this to be implemented. It could still throw the exception, but it would require that this method be implemented, and the implication is that the method would actually do something if it was on an interface. An interface could be considered to be a contract. So the client might expect, even on a part implementation, because it doesn't know the difference at its level, that the add or remove might actually do something. So the interface probably shouldn't have add and remove on it. We have a similar issue with the abstract class. It still has add and remove on its public interface that the client can call. And the implementation of an individual part doesn't have anything to add or remove. Because the client doesn't know that the add and remove are not implemented, throwing an exception might not be a good thing. Because of course the client doesn't know that it can't use those methods, so you may end up blowing up the application by mistake. The other side of that, however, is that if you allow them to call add and remove on an assembly that has no children, well, they're trying to add or remove something, so there's a logic error there. So throwing the exception might be a good thing. The compromise might be to use asserts so that you can see it in development and debug, but in release it's not going to throw. So a lot of interesting choices on what would seemingly be a relatively simple object. So here's our class diagram, and we have our base assembly abstract class, which has fields for name and quantity, and we have methods for add and remove, as we just discussed, and write parts list. And then our two descending classes are the assembly class that does indeed actually implement and do something with add and remove, and can have child objects, and the part class, which is simply just a single part. So that's what the composite looks like. And as you can see, if we have multiple assemblies with multiple children, we start walking that tree. For our composite example, we're going to build ourselves a computer, assembly by assembly, part by part. So we're going to create an assembly parts list. And we'll have an abstract class called base assembly. And all of the parts in our parts list are going to descend from this abstract class. So we'll have fields for name and quantity. Then we'll have methods to add any child parts to the assembly, to remove any child parts from the assembly, and then write itself to the parts list. We'll have two classes that descend from it, an assembly class and a part class. The assembly class will actually have children, or could have children, and the part class is a single part that cannot have children. So here's our base assembly class, and it is an abstract class, and it has those protected members name and quantity, and its constructor takes parameters for name and quantity. So when we construct this base assembly, we'll give it those parameters, and then it will also have methods for add, remove, and write parts list. And the write parts list is going to write to a list of strings. And note that the add and remove take a base assembly type. For our part class, we descend from base assembly, and we override the constructor. We don't have any particular implementation for that at this point. We also override the add and remove, but because we're just a part and we don't have any children, we throw an exception on both add and remove to indicate that this is a single part object and it doesn't have any children. So there's an error here. As we discussed in the PowerPoint, there's a number of choices to be made here as to whether this should be an abstract class or an interface, and what we should do on the add and remove methods for the part. This is fairly extreme in that if we actually did have some sort of logic error in the production version, it could cause the production version to crash if this exception wasn't handled elsewhere. Being as how it's probably a logic error, this exception was one of those things that might actually get through. You might be better served with an assert here so that you can see it in debug, but it doesn't crash it in a release mode. For the write parts list, we're going to take that list of strings and we're going to add our string, which consists of the quantity and the name. The assembly is the other class that descends from base assembly, and it is going to have a private member, which is a list of other base assemblies. And note that these are base assemblies rather than assembly classes, because this is a list of children. So it could be base assemblies, but it could also be parts as well. So we have the list, and we create a new list when we actually first create this class. So it will be available for additions. We have the constructor overridden as well, and then we have the add method to override. And all we do is we add the base assembly that's passed in as a parameter to our elements list. We also have remove overridden, and it obviously just removes the assembly from the elements collection. Note there's no try-catch on this one, so if that assembly is not actually in the collection, it's going to cause an unhandled exception. So beware of those kinds of things. And then we get to write parts list. And we'll write ourselves first, just writing the quantity and the name of this particular assembly. And then we'll go through each one of our child assemblies and ask them to write their parts list. So here's where we get to walk the tree. If one of our children assemblies also has children, then when this method is called on them, they will also have their children write to the parts list. So we'll walk through all of the children, grandchildren, and great-grandchildren of this assembly and have them all write themselves to the parts list. And that will continue along as long as the tree branches are there. So here's what our application that uses this is going to look like. Just a simple button for building the parts list and a list view for the parts. In the code, I'm going to create a bunch of assemblies. So I'm going to create a top widget assembly, and this is basically my root node. We'll just call that main assembly. So that's going to be my base computer. And we'll have a chassis assembly, a display assembly, and a power supply assembly. And note these are assemblies, so that means that they're going to have children. And our constructor takes the name and the quantity for the assembly. So we only have one chassis, one display, and one power supply in our widget. Then we get down to the individual parts. So we're going to have some bolts. We'll have a main case, a screen, a display electronics assembly, but it's only a part unto itself because it doesn't have children, a transformer, a power board, and of course, duct tape and bubble gum. We want this thing to work, you know. Then, at our top widget level, we add the chassis to the assembly collection of that top widget assembly. We also add the display and the power supply. So the top widget now has a child level with 3 children. Then in our chassis, we add a main case and a bolt. Actually, a quantity of 24 bolts, but it's a single bolt part class. For the display, we add the screen and the display electronics. And the power supply, we add the transformer and power board. And the top widget also gets duct tape and bubblegum. So the top widget has 3 assembly type classes and then 2 part type classes. And then each one of the children assemblies has some part classes as well. So this tree is going to go 3 deep, and you can see that a given assembly can also have different types of children. They can be either assemblies or parts or combinations thereof. Then we call display parts list and pass in the top widget. Our display parts list method creates the list of strings for the parts list that we're going to pass in. And we pass that into the top widget write parts list method. That's that method that all of the parts and assemblies implemented. And we only have to call it at the top level, because as you remember, any assembly that has children turns around and in turn calls the method on the children. So the whole parts list will write itself with a single call to this method. And then we get the actual list box on the form, we clear it, and then we add the parts list strings to that list for display. But this write parts list method is really the whole point of a composite object. We can treat each one of the individual objects in a composite the same. They all have the same basic interface that the application will use. And that's regardless of whether they have children or not. So we can treat them all the same and work with them in the same way. If we wanted, for instance, a sub-assembly parts list, like one for the power supply, we could, instead of topwidget.writePartsList, call writePartsList on the power supply assembly. And it would work exactly the same way. It would just give us only the power supply portion of the parts list. So let's make sure I'm not lying on this and that it runs right. So here's our app, and when we click on Build Parts List, there's our assembly parts list. And it did iterate through all of the children. So that's the composite pattern. And you've probably already seen it when you've worked with a tree view or an XML doc or maybe the HTML DOM. It's the same basic idea, The one little detail of the composite is that all of the items in the composite have the same interface that the application can use. So each one of the elements in the composite can be treated in the same way. The decorator pattern is a little bit more complex than some of the patterns we've been looking at so far. So let's dive right in. Our problem is we have a base object, but it may have a lot of options. Now we might think, okay, we'll create a whole bunch of subclasses that inherit from that base object. But then we just have a whole lot of subclasses. What we really want to be able to do is to add options to this base object dynamically. For instance, I may have some sort of product that I'm selling, and I can have options on that product. And there's just a whole lot of them. Or I may have some sort of class that I want to add capabilities to. For instance, I may have a stream that normally is not encrypted, but I want the ability to encrypt it and possibly choose different encryption styles. Or I may want to add media to a social post. So I have my base social networking post that just posts text, but I may want the ability to add either a video or an audio or a photo to that post. So I could use a decorator to add those capabilities. So a decorator allows us to add behavior to an individual object, either statically or dynamically, and it won't affect other objects from the same class. So if I have a given class that I've already created, and then I create another class and then start applying decorators to it, the first class isn't affected in any way. It still has the same definition of the class. What we'll be doing is we'll subclass the original component class into a decorator class. In the decorator class, we'll add a component member, and then we'll pass the component to the decorator constructor. And then in the decorator, we'll actually override any methods that need to be modified. And that's where we're going to add the capabilities to our base class. So we have our original base class that we're calling the component. And we'll be subclassing in that into a decorator. And then the decorator will actually have an instance of that component. We'll run through the decorator, and then the decorator is the actual object that we'll be passing into the application that will allow access to the added capabilities. So I have a computer ordering system that I've got to create. It's a build your own. Our customer is allowed to choose RAM options and storage options and even discount options. And of course, if we're really going to do this, as you know, there's all sorts of other things that they usually provide for options. So we'll have a computer-based class, and that's the class we're going to be decorating. It'll have a getPrice and a getOptionCode method. The computer decorator is going to be our abstract class for all of the decorators that we're going to create. And our computer base class is a member of that computer decorator class. And we get that in the constructor. It's going to be a parameter of the constructor. Then we'll have individual decorator classes that, of course, descend from our abstract decorator. So we'll have decorators for our memory for RAM, 8 and 16 gigabyte options, for our storage, 128, 256, 512 gigabyte options, and our discount option. And we'll override the getOptionCode, and we'll override the getPrice method. And we'll override getOptionCode by appending the option code to the base model number. And of course, we'll override getPrice by adding the option price to the base price. And the discount decorator overrides getPrice in a different way because, of course, it has to lower the price. So here's our class diagram. We have our abstract computer class, and it has properties for description and model, and then it has the methods getOptionCode and getPrice. Now, both our computer base class and our computer decorator descend from the computer abstract class. And then our computer decorator is an abstract class itself, and we have all of the different options that descend from it. So let's take a little bit closer look on the main decorator and computer base classes. So we have our abstract class, and the computer base class implements the getOptionCode and getPrice methods. And that's going to be our base computer with no options. We also have our computer decorator, and it has a field for the base computer, and that's where we get that in the constructor as a parameter. We also have fields for option code and price, and then we have methods for getOptionCode and getPrice that each one of the decorators that implement this abstract class will have to implement. So this is a little bit difficult to get in a theoretical sense, I think. So do please take a look at the next lesson that gives you a real code example. For our decorator example, we're going to be creating a computer ordering system. Here's our class diagram, and it starts with our computer abstract class. And our computer abstract class has properties for description and model, and then really important methods, get option code and get price. Descending from the abstract computer class, we have computer base, and this is going to be our base model computer. So when we implement get option code, it will have an empty string for the option codes because it's the base model. And for the method get price, it'll have the base model price. Then we have the computer decorator class, which again descends from the abstract class computer. So that's why the application can use the abstract class computer throughout the application, and it can be decorated and options can be added to it. And the application can still work with it in the same way it would work with a base computer. So the decorator class has a base computer field, and that's passed to us in the constructor. It also has fields for the option code and the price, and then it implements the get option code and get price, of course. And the decorator will implement those by adding the option code for the particular option that the decorator is creating, and get price will add the price of the decoration or the option to the base model computer. For our example, we're going to have a number of different options. We'll have an 8 gig memory option, a 16 gig memory option, and then hard drive options of 128, 256, and 512 gig. And then the most important one of all, the discount decorator. And each one of these classes descends from computer decorator, so each one of them implements the get option code and the get price methods. Going to our abstract computer class, it has the model and description fields, and then the definition for the get option code and get price methods. Our computer base class overrides the get option code, returns an empty string, and provides the base price of $4.99 for our base computer. Then we have an abstract class called computer decorator, and this is what all the other decorators are going to descend from. It has a member for its base computer, and also a string for the option code, and a price member. For the constructor, we're passed in a computer, and we'll set our base computer member to that computer parameter. We'll also set the model property to the computer model, so we'll have that available to us as we add option codes to it. For our get option code method, we'll simply take the base computer get option code and add our option code to it. For get price, we'll take the base price and add our price to it. These things can build upon each other. You'll note that we had options for RAM and storage, and we're going to want both. So we'll start with our base computer, and then we'll add some RAM. So our first decorator will be a RAM decorator, which will get our base computer in for the computer parameter in the constructor. But then we'll move forward with that, and we'll work to the storage decorators. And the storage decorators won't be taking the base computer object, they'll be taking the decorated computer object that has already gone through RAM. So we won't get the $4.99 version passed in the storage in this constructor. We'll actually get the $4.99 plus whatever RAM version. So the string for get option code will start with the base computer, what we're calling the base model, but it will also already have the information for RAM, and then we'll just be appending the information for the storage. Likewise, the get price method, the base computer will already have the extra price for the RAM built in, and we'll be adding the price for the storage. So these things will build on themselves, and you'll see how that works when we get to the form code. So I've got a single file that has all of the decorators in it. And as a best practice, please don't do this. But I wanted to just make it more concise for the purposes of the course. But each class should really have its own file. I have an 8 gig memory option, and it descends from computer decorator. And all we have to do in these various decorators is in their constructors, just set the option code and the price. So we have the option code of 8 RAM in this decorator, and the price is going to be $70. We have a 16 gig option. We set the option code and the price goes up. And then we get into our storage options. And they all follow the same pattern. Then we have the discount decorator. And the discount decorator is slightly different because it has a discount rate, and note this is hard-coded, again, not the best practice. It would be ideal if this was a property. But we have the discount rate, And then we have our constructor, and we set our option code as discount, and the price we're setting is 0. Doesn't really matter, we just need to do something with it. We override the option code because our option is going to be a little bit different. We're going to add discount and the number of the discount rate. And then on the get price, we're applying the discount. So we do a little bit of math to get it into percent and apply that to the total computer price. And again, these decorators build on each other so that the computer passed in to the discount decorator is the one that's been built up from the base model, gone through the RAM and the storage options, and whatever other options we add to it. So that's a full and complete total price that we're applying the discount to. Here's our form design, and our user gets to choose the memory option and the storage option and apply the discount. And as they make these changes, we're going to update the total price of the computer, and we'll also update the model number. And the model number is going to have all of the different options as dash options on the end of the model number. Now we'll see how this looks. We're going to call our display price method right on initialization so we get that base price going. And then every time an option is checked, we'll also update the price. So we'll call display price then as well. And here's what display price does. We start with our base computer. So we have our base $499 computer with no RAM and no storage. And we set its model name equal to Extreme XPC. It sounds good. Then we create our RAM decorator. And depending on which option is chosen, our RAM decorator can either be the memory 8 option or the memory 16 option. And when we create that RAM decorator, we pass in our base computer into the constructor. So that decorator has that base computer information and it adds to that. Then we have our next computer decorator, our SSD decorator, and that's going to handle the storage options. So for whichever radio button the user has checked, the radio 128, 256, or 512, we'll create the appropriate SSD option. And we'll pass in the RAM decorator, not the base computer model, but the RAM decorator. And note that the computer decorator and the computer base both descend from that abstract class computer. So we can indeed pass them into these decorators and treat them the same. And that's really one of the keys of the decorator pattern. So now we've built up our computer from the base model, added the RAM, and added the storage. And now it's time to apply the discount if appropriate. So we have yet another decorator. And if our applied discount checkbox is checked, we'll create a new discount decorator and pass in the end result of the storage decorator. If no discount is applied, we'll just use the storage decorator because they're paying full price. So finally, this last decorator is the one that has the complete model number and the complete option code and the complete price. And we'll set our label text appropriately for the model and the price. Okay, let's give this a run and see what it looks like. Here's our app, and we do have that base price. Now, of course, it wasn't $499 because that had no RAM and no storage. But as I click on a RAM upgrade, the price gets upgraded. As we go through the storage options, price goes up, and we can apply that discount. And you can see also the model number adjusts as well. So now I've got my Extreme XPC with 16 gig of RAM and a 512 gig solid-state storage drive. And I got my 5% discount. So life is good. We have our new dream machine. And that's how the decorator pattern works. The facade pattern is a really good pattern to use to simplify your application code. If you have a complex set of operations or objects that you want to interface with, but you don't want to clutter up the application code with all of those operations. Say you have some sort of series of methods that you have to go through. Within your actual application controller code. You'd like that to be separate. But the set of operations doesn't really fit into any particular class. So it's non-obvious as to where all of those operations should go. That's what the facade pattern helps you with. So for example, we might have a user registration process, and we need to do a few things when the user registers. We need to get their information and save it to the database. We need to send an email out to them to actually confirm that their email address is valid, and we need to get a validation email and receive that to confirm their registration and make them a truly live user. Where do all those methods go? Because some access the database, some deal with email, and some deal with a response object that comes from a web page. So it's not necessarily obvious that the user itself, as an object, should deal with all of that. Another example that can be even more complex is processing a purchase order. You need to get all of the different items on the purchase order, get the total, process the payment, send out a receipt, do a confirmation that you actually have the inventory, and process each one of the ship orders for each one of the items, and then manage the inventory upon shipping. So there's a whole lot of processes that need to be done in working with a purchase order, particularly if you're actually shipping some sort of product, or processing a follower in a social app. It seems like a simple thing. You just follow a user. But social apps are based on the idea of notifications. So when I follow a given user, the social app is going to want to tell the user that I'm following that I followed them. It'll also want to tell all of my followers that I'm following this user. And of course, it'll actually want to do the database operations to accomplish the follow. So there's a number of steps just in that. The app may also want to create a post that announces to the world that I followed someone. So all of these problems have in common that they have multiple steps, and they're not necessarily obviously related to a particular object. So the facade pattern provides a unified interface to a set of interfaces in a subsystem. In other words, our facade is going to work with a number of different objects and a number of different methods, but it's going to simplify that into a single object, and in our case, we'd like to have a single method. But by the definition, we just need to provide a single interface. And that single interface is what the application will work with. So that's the facade of it. As opposed to a typical building facade, which may actually make the building look bigger and more attractive, we're actually somewhat doing the opposite. We're taking a whole bunch of complex objects or operations and combining them into a facade that looks simplified and easy to the application. So the facade is going to define a higher level interface that makes everything easier to use, and it really cleans up the application code. Ideally, we're dealing with a single class or method for the application interface. And that single class or method will run multi-step operations and deal with multiple classes and methods. So it's going to take all the complexity out of the application code and put it into the facade. So for our social app following example, we have the following things that we need to do. The user is going to follow another user. So we need to process that in the database. And there may be more than just one single table write in order to process that. It depends. Then we need to notify the followee that they have been followed. Then we'd like to post that activity to a timeline or just to the general world. And then we also want to specifically notify all of our followers that we're following someone new, and maybe they would like to too. So to solve this problem, we're going to create a user class. And the user class is going to have some methods for following and posting and notifications. There'll also be a post class, which will handle the post operations, and a notification class, which will, of course, handle the notifications. And then we'll have our follower class, and that's going to be our facade class. And it will have a follow method, and that will do our multi-step process. So I'll add the user as a follower, do the notification to the followee, post the message to the timeline, and notify all of our followers of the new following activity. And here's the facade class diagram. And it's not really a very complicated diagram. On the right-hand side, you can see the multiple classes that we're working with in order to handle the following operations. And then the follower class is just very, very simple. It has a single method called follow. And that's actually the entire point, because the form over on the left deals only with the follower class. So it has that nice, simple facade that's covering up all of this other stuff that's to the right. So that's the idea behind the facade. It's actually fairly easy. So let's take a look at the facade pattern in code. Our application is going to run the process of following a user in a social app through use of the facade. So our application is in the form of Form 1, and it will call our facade class, called follower, which has a nice clean single method called follow. Follow is the facade, and it's going to call the user class, which has a number of different methods that are involved in actually doing the follow operation. The user class has a list of followers for that particular user, a property for its username, and then these methods for actually accomplishing the following. So the follow method does the database updates. So it handles writing the tables that handle the user following operations. Then we have follower added, and that notifies a given user that a follower has been added to their followers. Then we have a following text post, and that will post to our general social app timeline that a user is following a new user. And then finally, we have a method called notify followers, which will notify a given user's followers that they're indeed following someone else. In a social app, that's not like cheating on someone. That's a good thing. Everybody wants to know who's following who, so they may actually be interested in the same things and grow their social network. The user class uses the notification class in order to do the notifying of the various users of the following activities. And then the post class does our text post for the following activity. So here's what our user class does. We have our private list of followers, and of course our username. We then have a method called follow, and that would typically do updates to the database in order to insert followers for a user. Now for the purposes of this demonstration, we're just going to deal with the actual flow and relationships of the classes, and we're not going to do the details of actually writing to a database or doing notifications. However, one of the things the facade does is it hides all of that complication from the main application itself. So you can start to imagine how complex these code steps look and what would happen if they were actually in our main application code. So our follow method will handle all those database writes. And then follower added will notify a given user that they've added a follower. So we're going to use the notification class and call its notify user method. And then we'll let the user know that they have a new follower. We then have a following text post, and that will use a new post class, and on that class we'll call post text. And that will create a text post that notifies everyone that one user is now following another user. And then we have a method for notify followers, and it again uses the notification class. And for each one of our followers, we're going to send a notification by calling notify user that we're now following and the new user that we're following. And all along, of course, we're checking the result. And if it's bad, we're going to stop and just return that result. Now, I would like to make one point about returning Booleans out of all these methods. Of course, these methods deal with messaging and posting and database reads and writes. So there are things that can go wrong. And what we have is a true-false return. And we're returning true if things go right and false if things go wrong. Now, that doesn't actually provide the application any sort of information about what went wrong. So the application has no way of actually telling the user what went wrong. And it also has no way of knowing, well, was that really fatal, or should I roll back a transaction, or anything like that. So this is actually a really bad anti-pattern in terms of handling exceptions. And we'll be talking about exception handling when we get to best practices. So just returning a bool out of these methods is probably not a great practice. But again, we're trying to simplify this a bit for the example. Now the facade, of course, simplifies things for the application. So that's one more complication that would be in these classes that the facade is covering up for. We also have a post class, and very simply, it's going to make a text post. And it will be a post from a given user, and it'll have a message. And we're back to returning that true-false value for a result. And the notification class has a method called notify user, and it's a to user, and the message we're going to send to that user. So this notification class might be sending an SMS, it might be sending an email, using some sort of messaging that the internal app uses, and there are many other messaging services as well. So it might be using any of those, and you could think about the amount of code that that might take depending upon what kind of service it's using for the messaging. So we don't want the application to know anything in particular about this as well. Now we've already to some extent have covered that up a little bit in the user object. in that it's calling the notification class, and it's also calling the post class. But we still have all of this code in the user object, and we don't want to put all of those steps into our application code. So we create one more class called the follower, and this is basically our facade class. And it has a single method called follow. And we pass in a user who is the new follower and a user who is the new followee. And we have a Boolean for our result. So we're going to keep track of that as we go along through these various steps. So we'll first do the database follow by calling the follow method. And we'll check that result. And if it's bad, we'll just kick out of this process. We don't want to go any further. We certainly don't want to tell the rest of the world that we just followed somebody when the database doesn't actually know that we followed them. Assuming that the database write all went well, we'll notify that user that they have an added follower. So we'll call the follower added method. And of course, check the result. That was all good, so we're going to post to the world. That all went well. So we're going to post to the world that we have a new follower. And then if that goes well, we'll notify all of our followers that we're following someone new. So we'll call the notify followers method. So this is all that's going on in the follow method of our follower class, which is the facade. Now for our example purpose, this is still not an incredibly complex process, but it gives you an idea of the amount of code that could be involved. And this is the kind of code that we don't want in the application. So let's take a look at our application. We have a single button, so it's just going to say follow someone. So here's what we do on that button. We're going to create a new user, and that's going to be our current user. In a normal application, of course, this would be the logged in user, so we wouldn't be creating it at this time. So that code would go away. Then we have a user that we want to follow. And we probably wouldn't necessarily be creating this user either. In all likelihood, it would be involved in a database read, or it would already be passed to us. And then we create our facade object, and that's our follower class. And on that follower class, we simply call the follow method. We pass in the current user, and we pass in the user we want to follow. And we look at that return value. If the return value is good, we'll show a message that says you've successfully followed someone. Otherwise, we're going to show a highly informative error message that says, sorry, something went wrong. So the whole point of a facade is really right here. This one method covers up all of those steps and isolates them from the application, so the application doesn't have to know anything about them. It also isolates the applications from any changes in that process. For instance, if there are added steps, the application doesn't have to know that, just the facade class has to know that. So the facade simplifies the application code and also helps with maintenance of that code. Now let's take a look at the flyweight pattern. In boxing, a flyweight is actually a lighter weight class by a significant margin than a lightweight. I haven't been a flyweight since I was about 9 years old, and I'm not actually a big person. So a flyweight is really, really light. And that gives you the idea behind what we're going to try to do with our code. We're going to try to make it really lightweight. So the problem we're addressing is we need a lot of copies of an object. The object might be somewhat complex and might use a fair amount of memory or perhaps has some performance issues. And the more copies of that object we create, the more memory we use, and maybe we do a lot more database queries and we cause performance issues. So you could see this happening if you have some sort of web application that has a list of users, just lots and lots of users, thousands of users. And if we actually pulled them all up and created objects for each one of the users, that would be bad enough. But then, if we actually do that for every time the user is accessed, so we have multiple copies of the same user spread out all over the app, then we can have real problems in terms of memory and performance. The same sort of thing can apply to game objects. Lots of games have repetitive objects that might be obstacles to the game, and those objects are used time and time again. If the game was to actually create a new object every single time it used it, then it would have a whole lot of memory bloat and it would probably slow down. Or you could also think about posts in a social app. If you've taken a look at a Twitter timeline, it can be really lengthy, but Twitter only shows you what you need to see as you scroll along. But also, it's showing the same posts to a lot of different people. So it doesn't really want to reproduce that object for every single person who's looking at that post. it would like to use the same object in memory. So that's what the flyweight does. The flyweight is a shared object that can be used in multiple contexts simultaneously. So what that means is that instead of recreating instances every time someone wants to access an object, the instances are reused or shared. Now here's the side effect of that, of course. They're shared objects. So if there's an operation that makes a change to that object, it's changing the same object for all of the users that are sharing it. So in general, we're probably going to use the flyweight a lot for read-only objects, for like a timeline post, or for a user that we're displaying, or perhaps for that object in a game that doesn't actually change. And for our implementation, we're going to use a dictionary of objects. And we'll add the object to the dictionary if it's not already there. But if it is in the dictionary, we'll use the object that's already stored in the dictionary. So instead of having multiple creation steps, we're actually going to just pass around multiple references to the same object. So there are two areas, particularly if we're looking at database-driven applications, that this can help. If we're talking about a user that's stored in a database, every time we access the user, we don't want to do a database query to find the user. We want to effectively have cached that user. So we're going to pull the user out of the database, and we're going to do that once. And then we're going to put that user into the dictionary. And of course, store it in the dictionary keyed under a unique ID. And we'll pass that single reference to that user around into multiple instances of that application. So we're going to reuse that object throughout the application. We won't requery the database, and we also won't have multiple memory footprints for that user. Now again, the side effect for that is that everyone is sharing the same user, and also when we're talking about database-driven, if we're not requerying the user, if there are any changes to that user, then they're not necessarily seen if they were done under a non-shared object. So you may have to put in some sort of methodology for refreshing the cache. In taking a look at the flyweight pattern, a lot of times they say that it's not well used, and perhaps that's true in the strictest sense. But if you think about it in terms of caching, caching is obviously used quite a lot, and the flyweight pattern is very similar to that idea. So in our example, we're going to have a user list. Our application has lots of users. We're very popular. We have thousands of users, and the users are used throughout the application. So we don't have just one area of the application that we're using a user. We have it all over the place, in all sorts of pages and operations. So we have all sorts of things that use a user object. Of course, we would like to limit our memory footprint. More memory is more dollars, and it slows up the application. So we only want to create a user when it's used, and we don't want to recreate the user time and time again. So we have a normal user class. Everything's as you might expect. It has normal properties like username, password, first name, last name, and then it has one little additional thing, a follower list. And depending on how popular this user is, that could be very heavy. So this class has a bit of a heavy footprint. You might argue with the implementation and design of that, but that's what we have. We have a fairly heavy user class, and if we reproduce it, we're going to have some memory issues. So we then have a user factory class, and the purpose of the user factory is to supply users as needed to the application. The user factory is going to have that internal user dictionary that we talked about, and the user factory will have a single method, getUser. It'll check that dictionary, and if the user that we're looking for is in the dictionary, it'll return that instance of the user. So it'll only be returning that single reference. If the user's not in the dictionary yet, then it will create a new user, and it'll add that user to the dictionary for future reuse, and of course, return it for the getUser method. So there are two aspects to this. One is the reuse from the dictionary of that user object, and the second is the lazy loading of the user. We're not actually adding all of the users in the database into this dictionary, even though no one has ever asked for the users. We're only getting the user the first time it's necessary. Basically, we're doing it just in time and not quite too late. So we're only going to get the user when someone requests the user, and then after we get it, we're going to keep it for future use. And it's a really simple class diagram. we have our basic user class, which has some properties and that followers property that could be quite chunky. And then we have our user factory, and it has fields for users, which is going to be our dictionary of users, and then just an internal field for users count. And that's just to keep track of how many users we actually have in the dictionary at any time. That's not really required, it's more for demonstration purposes. And we have a single method called getUser. So that's what the Flyweight looks like. And the whole purpose of it is to just minimize the number of copies of an object that you have and to minimize the amount of times that you create that new object. The purpose of the Flyweight pattern is to lower our memory footprint and help us deal with performance issues. The idea is that our application may create a lot of objects that are of the same type and need multiple instances of that object. And we don't want to recreate all of those multiple instances if we don't have to. We would much prefer just to pass around references of that given instance. So in this demonstration, we have a user class, and our application is going to have a lot of users, and the application is going to use the user object, so it'll actually have a whole lot of copies of any given user in the application, and that's going to cause us some issues with memory. Our user object is fairly simple. It has a first name, last name, user ID, and username. No problems there. But it also has a followers list, which contains a list of other users. So that's going to get a little bit heavy. So if we have copy after copy of this, we could have some memory issues. Not to mention that if this user comes out of the database, every time we create it, we're actually going to be querying the database. So we'll create some more database traffic that we don't necessarily want either. Our user factory is what's going to help us work with that problem. And the user factory has a dictionary of users and, just for demonstration purposes, a users count. And that'll tell us how many users are actually in the users dictionary. And that has a single method that the application uses called getUser. So here's our user class. And again, it's pretty basic in that it has a user ID, username, first name, and last name, and then that nasty list of followers. It also has a static class for getting a user. And this is just used to get a user out of a database by passing in the user ID. And for our demo, we're just going to create a new user with a new unique identifier. And here's our user factory, and this is really the key to the Flyweight pattern. We have a dictionary with a key of type GUID, which is the user ID, and then we're going to store the users in the values. And we'll new up that dictionary. But note, we're at construction. We're not loading it up from the database for all the users at this time. It's an empty dictionary when we start. The user factory has a single method called getUser, and it's going to take a GUID parameter for the user ID. So the application is going to use this method to get a user object instead of creating the user object or asking for the user object directly. We'll go into the dictionary and we'll see if it contains the key for the user ID that was passed in. If it does, we'll just go into the users dictionary and return that user that corresponds to that user ID. So we won't create a new object. We'll be passing around a shared instance. If the user is not in the dictionary, then we'll turn around and we'll call getUser on the user object and pass in the user ID. And you remember that getUser probably pulls the user from the database. We'll take that new user object and we'll add it to our dictionary, using, of course, its user ID as the key. We'll increment our users count, and then we'll return that user object. So the gist of this is that we won't actually create or pull from the database a user object until it's actually being used, and it's not being used until this getUser method is called. Also, if we're looking for that same user object in another area of code, we don't recreate the object. We don't do another database call to get that object. We just go into our dictionary, check to see if we have that key, and then return that user. So we're passing around a reference of that user object as opposed to requerying the database or recreating a new user. So we're keeping our memory footprint as small as we can, and we're also not creating users that we're not using. We only create the user when we actually need it. So in that way, we're attempting to minimize the amount of queries to the database, and we're trying to minimize our memory footprint as well. Now, the side effect of that, of course, is twofold. One, we're passing around a reference to the user. So if anywhere we're passing the user object to makes a change to that user object, the user object is shared throughout the application, so that change is migrated throughout the application as well. That may actually be a good thing, but it may be something that you necessarily want to be aware of as well. The other thing is that because we're not requerying the object, if there were changes that were made to the object outside of this shared user, and we're not requerying the database, so the underlying database object is changed, but we didn't do the requery, so we don't actually have those changes in this dictionary. So there may be a little bit of age to this as well. So these are just a couple of issues to think about. So there's not a whole lot to visually demonstrate here. This is the user factory, which is going to be our key to our flyweight pattern. And all it does is create user objects for us and pass out references where it has them. And that's really the whole point of the flyweight. Our last structural pattern is the proxy pattern. So you have a process that's complex or really time-consuming, and you need the application to still be responsive, because of course, if it's non-responsive for any period of time, the user is going to think it's hung, and either leave your web page or perhaps reboot the application or even worse, their entire machine. Obviously not what you're looking for. So you need a stand-in for that application to be responsive, because your object is all tied up. So you need a stand-in object to be a proxy for that object. So you might be doing some sort of complex calculation, or there's a database on a remote server that takes some time to contact and run a query with, or you're accessing a web service that again is on a remote server and the connection time may not be great, or perhaps you're processing a payment, and that takes some time for the credit card to be approved, and again, you're talking to a remote web service. In all of these cases, you want the application to be responsive to the user, and a lot of times you want some sort of fill-in object just to hold the user at that place until the actual process is complete. So a proxy will provide a surrogate or a placeholder object for another object in order to control access to it, basically to replace it for that time frame. This allows you to postpone an operation until you need it, or it allows the application to be responsive during some sort of long-winded process, and the application can run while the proxy is running some sort of asynchronous task. A lot of times when we're talking about remote databases and remote web services, the tasks are actually asynchronous, meaning that we'll have a method that will start off the request from the service or from the database, and that method will return immediately. The request goes out on the wire, and then we'll get some sort of event or callback when the event is done, and that's an asynchronous task. So the application can be responsive after the task has been started, but it also has to know that the task has completed. And we use the async keyword to do that in .NET, among other techniques. And we'll talk about async when we get to best practices. So in our example, we'll take a look at payment processing. Our application will be used, of course, to order something. And we're going to use a third-party payment processor, which is the norm, and it will be an asynchronous web service call. So again, we're going to have a method that starts the call to the payment processor, and then we'll have to handle the return asynchronously at a later time with a different method. We would like to show some sort of processing message while we're calling the service. And when the process is complete, we want to show the confirmation code. And of course, we'd also like to show that they successfully paid for the product, or if there was a problem, that their credit card was rejected. So in our proxy pattern, we're going to have an iPayment receipt interface. And for our example, we'll have an order and a receipt property. And those are both simple storage objects. The order will include the order ID, order date, credit card information, and the user information. The receipt will include a confirmation number, the amount that was actually charged to the credit card, and the status of that receipt. We'll have a payment receipt class that implements iPayment receipt, and it will interface with the payment processor directly. and it will do the web service processing. So the payment receipt class is what is known sometimes as the real class, as opposed to the proxy class. Then we'll have a payment receipt proxy class, and that will also implement iPayment receipt, and it will have the payment receipt real class as a member. In the payment receipt proxy class, we're going to have a receipt property, and that will return the object. If the payment processing is not complete or has not been done, we'll call into our payment receipt object and we'll ask it to get the receipt. That will kick off the process of payment processing. In the meantime, we'll return a placeholder receipt, and that placeholder receipt will indicate that we're processing. Once we actually get the real receipt from the payment receipt class, we'll return the real receipt property as opposed to the placeholder. So here's our class diagram. We have iPayment receipt, and that's our interface that has the properties order and receipt. They're both classes. The payment receipt proxy has fields for payment processed, which is going to be a bool, and payment receipt, which will be a payment receipt class. It'll also have properties for the order and the receipt. And we'll have a method, which will be internal for get placeholder receipt. And then we have the order and receipt storage classes. And of course, we'll also have the real payment receipt class. So the whole purpose of a proxy is basically to present to the application a proxy class or a substitute class that will allow the application to still be responsive while the real class is doing a long-winded processing. So for our example, our application is going to be interfacing with the payment receipt proxy, and the payment receipt proxy has the real payment receipt class as a member, and that's the class that actually does the actual credit card processing. So the whole idea behind a proxy is basically to create a placeholder. So let's code ourselves a proxy pattern. In this application, we want to process a customer's purchase and approve their credit card. For the credit card approval, we're going to use a third-party web service, and that can take a little while, and we want our application to be responsive during that approval process. So we have our order class, and we're going to use that as an input to our credit card approving. And the order class is what you would expect. It has the amount of the order, credit card information, customer ID, and that sort of thing. What we want to return to our application is a receipt object, which gives us a confirmation number and the amount paid, the date paid, and the order ID is used as a reference. And we're going to use iPayment receipt as our interface. And this will be the interface that the application uses, and we're going to have two classes that implement this interface. This interface has two simple properties. One is the order, which is going to be a get and a set, and the second is the receipt, which is just a get. So the implication here is that when the receipt property is called for by the application, that it will get some sort of object for the receipt, and if a valid receipt is not available, it'll kick off the process of getting the credit card approval and get a valid receipt. To get that receipt, we have a class called payment receipt, and this is what's known as the real class, as opposed to the proxy class. It implements iPayment receipt, so we have an order property and a receipt property. We also have a method called getReceipt, and getReceipt is the method that's going to do the credit card processing, and this could take a while. So we don't want to call or use the payment receipt class from our application, because getReceipt might block up the application and make the user wonder what the heck is going on with their credit card processing, and you really don't want a user to wonder about that. So instead, the application is going to interface with the payment receipt proxy class. And of course, this is where the proxy pattern comes in. So the payment receipt proxy class also implements iPayment receipt. So we have the same properties, order and receipt. We also have some fields, and the first two, payment processed and payment processing, are flags to determine where we are in the payment processing process. We also have an internal member for payment receipt. So the proxy has an instance of the payment receipt class, or the real class in the proxy pattern. And then we also have a receipt object, and that's going to be the one that we want to return to the application. We'll also have an internal method called getPlaceholderReceipt, and that will be the receipt object that we're returning when the payment is being processed. So that will allow our application to be responsive because it will get this placeholder receipt or proxy receipt to work with until the actual real receipt comes through on the payment receipt class. So our order class, simple storage class, as is our receipt class. Our iPayment receipt interface just has the order property and the receipt property, and the receipt property is only a get. And then we have our payment receipt. And payment receipt implements iPayment receipt. It has the order property, and then it has the receipt property. When the receipt property is called for, we call getReceipt. And our getReceipt method can take a while. This is where we're actually going to contact the payment processor and try to get the credit card approval. So this may be a lengthy process. At the end of the process, we'll get the receipt information and return the receipt. And right here, we just have dummy data. In all likelihood, when we're using a third-party payment processor, it'll probably be an asynchronous operation, meaning that there'll be a method to make the request for approval, and then there'll be some sort of a callback mechanism that the payment processor will call when they actually approve or disapprove the credit card. So our initial method will actually return very quickly when we make the request, and then we'll have to look for the callback in order to process the request. Now, in the past, you would have an initial method to make the request, and you would actually have a separate event handler or delegate or method to handle the callback from the payment processor. And those two were a bit disconnected. And if you really wanted to wait and monitor what the status was, then you might have to do something like a monitoring or polling loop or a thread monitor arrangement. Now in .NET, we can use the async keyword in conjunction with the await keyword with an asynchronous method. So it'll actually effectively block the method, even though it's asynchronous. So we'll talk about async more in the best practices area. At this point in the example, this is something that you might end up using right in here. So our getReceipt method may take a while. So we don't want the application to call this thing directly. We want the application to use Payment Receipt Proxy, which implements iPayment Receipt. It has those two flags to keep track of where we are in the payment processing, and then it has the Payment Receipt object as well, and it'll have the receipt that it's going to return. And of course, it implements the iPayment Receipt interface, so it has the order property. And now we have the get on the receipt property. We first check to see if the payment was processed. If so, we've already gotten the receipt object and we just return that. So we return nice and quickly. Next, we check to see if the payment is processing. We don't have a payment processed yet, so we'll check to see if we're actually processing the payment. If we're not, that means that this is the first initial call here to get the receipt, and we haven't actually started the payment processing process yet. We'll say that the payment processing is equal to true. And then we'll kick off the payment processing by calling the payment receipt class, setting its order property, and then calling for the receipt on that class. When we call payment receipt.receipt, we're going to call getReceipt, and this is that long-running process. So we don't want to block this call at all. So this area probably should be on its own separate thread. So what will happen if we put it on another thread is that we'll go through this really quickly. We'll kick off the thread, and then we'll come down and we'll return the get placeholder receipt. So we're going to return a placeholder receipt while we're doing this processing. And get placeholder receipt simply creates a new receipt object, and the key is it sets the confirmation to processing. Now you might prefer to have a status flag or some sort of enumeration to show where it was in the process, but that's just a detail of that receipt object. The point of the proxy pattern is it's returning this placeholder receipt while it's running that long approval process for the credit card. So back to that separate thread we kicked off, we're waiting for that payment receipt object to return, and when it does, we'll have our receipt and we'll set our payment processing to false and our payment process to true. So now the next time to come through and ask for the receipt, we'll say, okay, the payment is processed, and we'll just return the receipt. So here's our application form. We have our button for processing the payment, and down in these text boxes, we'll just get the return information about the receipt. And then we have a refresh button. Because what's going to happen is when we hit this process payment initially, we're just going to get processing for our status. And then we're going to be able to refresh it to see when it actually comes through. We'll talk about that process in a little bit. So here's our form code. We have a member for iPayment receipt. And then when we click the Process Payment button, we'll create ourselves our new order, just with dummy data for now. And then we'll create a payment receipt proxy, because we want to talk to the proxy and not the payment receipt class directly. We'll set the proxy's order property to that order that we just created, and then we'll ask it for the receipt. This should return quickly, and that's the whole point of the proxy. So we'll display that receipt after it returns. And display receipt just sets up our text boxes with the receipt information. Then on the refresh button click, we'll again call into our proxy looking for that receipt, and we'll display the receipt information. So let's see that working. So when we initially click Process Payment, we get that it's processing. When we click on the refresh, it's processed and we actually get a proper confirmation. So here's the problem with this. The proxy pattern is fine in itself, but this requirement that we actually have to click a refresh button to constantly look to see if the receipt is actually done processing is really not great. So what would be ideal if the proxy would actually fire an event when this receipt was received from the payment receipt. So that's what we would really like to see, as opposed to kind of a polling arrangement that we have now with this form. In general, polling and looking at flags is not really what you want to do as a best practice. You really want to work more with events and delegates. But overall, this is what the proxy pattern is supposed to do. It's supposed to create the placeholder so that the application can move on while it's doing the other long process. The chain of responsibility pattern solves a somewhat specific problem, but a really commonly occurring problem. You have a multi-step request process, and you need these steps to be done in sequence, and you don't want the application to manage the process, because the steps actually have, or could, have some approval to them. So each one of the steps may pass on to another step some information, or the steps might short-circuit it and return and say, okay, we're all good, or it's all bad. The chain of responsibility pattern is used really commonly for approval processes. For instance, approving a purchase order, or reviewing documents, or human resource approvals for vacation or something like that. They're also used a lot in back office software. Back office software is the operational software as opposed to the consumer customer-facing software. And that's the software that deals with human resources and purchasing and manufacturing, the real nuts and bolts of a company. Back office software is also used in really large companies, and of course one of the major players in that is SAP. So we'll talk a little bit about how that approval works in a back office software, and that approval process can also be known as a workflow in that kind of environment. Chain of responsibility has a really long description in the Gang of Four. You want to avoid coupling the sender of request to its receiver by giving more than one object a chance to handle the request. And we want to chain the receiving objects and pass the request along the chain until an object handles it. Very simply, what this means is the application is going to initiate a request with essentially the first receiver or approval in the chain of command, and then we'll wait for an answer. Each receiver of that request will then pass along the request to the next receiver, or it may stop the chain and return to the application either that accept or deny, or whatever the appropriate response should be. So for our example, let's talk about a back office material approval. SAP has a very long and complex way of approving a new material for a company. There are a lot of things that go into that. For example, you need to make sure that all the part numbers and drawings and procurement sources are established for the material. You also need to make a make or buy decision. In other words, are we going to make this material in the factory, or are we going to buy it as a complete assembly from a vendor? So depending upon the company, this may involve a lot of departments. It may involve an engineering department, a manufacturing department, a finance department, a purchasing department, a lot of areas And what SAP does is it can take almost 40 approvals to get a material through that system. And there are a lot of other little steps just besides a yes/no answer on those approvals. So it's a really complex process, and it's handled with something called a workflow, which is essentially a chain of responsibility pattern. A workflow basically sends out a request to the first approver, and it can actually send out that first request to more than one if they can work in parallel. And then on the basis of them having completed whatever steps they need to do, the workflow will then be sent to the next one down the chain. And eventually, it will all hopefully meet at the end with a fully approved material. But it's a really complex process, and it lays out in the same way a chain of responsibility pattern would. So for our example, we're going to tighten that up a little bit, and we're going to request a new material be added to our system. And our process for approval won't be quite as lengthy as SAP, and we won't go through quite as many departments as SAP. We'll have an approver abstract class, and this is going to be essentially the central class of the chain of responsibility. In that approver class, we'll have an approve material method, which will return a true or false for the approval, and it'll have a reason parameter if they've returned false. It'll also have a set next approver method, and that will lay out the chain of command. And just by the way, who are those guys? Descending from that approver abstract class, we'll have an engineering approver, and their role will be to look for proper part numbers and drawing numbers. Then we'll have a purchasing approver, and the purchasing approver will be able to approve any material up to a certain budget limit, and they'll be able to disapprove material that's over a certain budget limit. And somewhere in between, they'll need to pass it along to finance. And then we'll have a finance approver, and they can approve a larger budget limit than the purchasing representative. And of course, they'll also disapprove something that's completely absurd. So we'll have our abstract class, and it'll have an internal member called next approver, and that will be set when the method setNextApprover is called. Basically, the flow for this from the application's point of view is it will create the various approvers that are necessary, and then it will call setNextApprover on each one of the appropriate approver classes to basically lay out who's first, who's second, who's third, along that chain of responsibility. Once that's done, the application will call the approveMaterial method on the first approver. In that first approver class, it'll do its work, and if it needs to call the next approver, it'll check to see if that exists by checking that internal member. And if the next approver does exist, it will subsequently call the approveMaterial method on that next approver. So we've got the three subclasses down here, and we're going to start off our chain of command with that engineering approver. Assuming that everything was good for part numbers and drawing numbers, the engineering approver is basically saying yes. He'll then look at his next approver member and see that it's the purchasing approver. So he'll call the purchasing approver and call the approveMaterial method on the purchasing approver, who will then do their thing, and if they have to, they'll call approveMaterial on the finance approver. So that's the way the chain of responsibility works. And essentially what we're just trying to do is to get things to work in sequence and take the burden off of the application in terms of following along all of this various approving sequence, and get that out of the application main code and put the responsibility on the approver classes. For our chain of responsibility example, we're going to have a company approve a material. The material class is pretty basic. There's a budget for the material, a drawing number, material ID, a name, and a part number. The real guts of the chain of responsibility pattern are in the approver class, and that's an abstract class, and it has two methods. One, approve material, and two, set next approver. So the approve material method for any of the inherited classes will ask, is this material approved or disapproved, and return a Boolean. And if it's disapproved, you can set a reason. The set next approver will set up, once you're done as an approver object, you want to call the next approver in the chain. And this next approver is what's set in this method. And we have an internal field member called next approver that stores that. In our example, we have three approvers. We have an engineering method in budget. And then we have a finance approver, and they're even more interested in budget. And all of these descend from our approver abstract class. A quick look at our material class. It's very simple. It's just a storage class with those properties to describe the material. Then we have our approver abstract class. It has our protected approver called next approver. And set next approver does indeed set that next approver member. And then we have the approve material method. It'll return a bool, which is true if the material is approved, false if it's not. We pass in the material object that we're looking for the approval for, and we pass in a reference to a string called reason. Typically, we're interested in the reason if it's disapproved, but you could also actually comment for this reason if it's approved as well. We start with our engineering approver, and the engineering approver overrides approved material, and we have a little bool called isValid. If the material drawing number is null or white space, then isValid is false, and we set the reason there is no drawing for this material. Likewise, if the part number is empty or white space, then we again set isValid equal to false and set the reason that there's no part number. So that's what engineering is interested in, the part number and the drawing number. If those both were valid, then engineering will look to see if there's a next approver object. If there is, engineering will call approve material on that next approver and pass in the material object and the reason. And it will return the result from the next approver approve material method call. Otherwise, engineering will return isValid. Now, isValid is going to be false if either one of these conditions is bad. There's no part number or drawing number. Otherwise, isValid could be true, and we could hit this line at the end if there was no next approver. And that would occur if the engineering approver was the end of the chain of responsibility. There would be no next approver. So engineering would effectively get the final word, yes or no, on the approval. Everyone else had done their approvals. In this case, engineering's first, and there is going to be a next approver, and we'll see how that gets set up in the form. But the next approver from engineering is purchasing. And purchasing also overrides approved material. And purchasing is interested in the budget. If the budget is under $10,000, purchasing can approve it, and they do. So they return true. They don't consider the next approver because they have final word on that budget. They can approve anything that's under $10,000, just as long as engineering has already approved it. But if the budget is greater than $10,000, then we have to go further. If it's less than $100,000, then purchasing can pass it along to the next approver, who is actually finance. So we'll check to see if the next approver is equal to null. If it's not, then we'll call next approver approve material, and we'll return that. If the next approver is actually null, then purchasing is actually the final approval, and they can return true off of this. If the budget is over $100,000, however, then this material is going to be disapproved, and the reason is that it's way too much. Find a different way. So next in line would be the finance approver. And if the budget's under $100,000, then it's going to return true. It will also check the next approver. In our example, this next approver is actually going to be null. But if there was someone else, say the VP of Rocket Science, then they would be the next approver, and they would have to call approve material. And we'd keep on going with approve material on the next approver until the chain was complete. For this example, I've just done the 3, and finance is the last, so there'll end up to be a return true for this. Otherwise, if the material budget is greater than $100,000, well, we're not getting any more relief out of finance. We're returning false. We actually shouldn't hit this branch at all. But the classes are independent, so the rules may change on purchasing, and they may skip that $100,000 and leave it up to finance for those big numbers. So you have to think of the classes as being independent, and you can't assume that another class is going to run the rules that you need to run in this class. So now we want to take a look at what we're doing at the application level. Our application has entry areas for the new material that we want approved. And when we're done making those entries, we click on Please Approve the New Material, and we'll get a result down here. It'll either be approved or disapproved with the reason. And our code for that button approval click. We create our new material based on the entries that the user made. And then we start creating approvers. Our first approver is going to be the engineering approver named Bob. Our next approver is the purchasing approver named Ted. And then we have our finance approver named Alice. So we've got the 3 approvers that we need. And now we go to the engineering approver who's going to be first in the chain. And we set the next approver on Bob, the engineering approver, to Ted, who is the purchasing approver. So once Bob is done, the material will be passed to Ted, the purchasing approver. Then we set on Ted's approver object, set next approver, and we set it to Alice in finance. So it'll go from purchasing to finance. So this is what the application has to know in terms of setting up the chain of responsibility. Now it wants to run the approval. So it creates the string reason that it's going to use for the reference, and it calls the first approver in the chain, Bob from engineering. And it will call the method approve material on Bob, pass in the material and the reference reason string. And that's all the application has to do. Because once Bob is called, Bob will pass it to the next approver if it goes, and they will go to Ted. And if Ted needs to pass it to Alice, Ted will pass it to Alice. If it gets disapproved anywhere along the line, this will return false. If it gets through all the approvals that it needs, it will return true. So the application only had to initiate it. It didn't have to know anything about chasing down whether Ted approved it or Alice approved it and anyone else in that chain of responsibility. It just laid out what the chain was and then initiated the approval by calling approve material just on the first approver. So when we get the return value, if the material's been approved, we set our string up to be approved plus the reason. Otherwise, if it's disapproved, we set our string up to disapproved and the reason. And in our result text, we set up that reason. So we'll give her a run. And we have our pre-populated material. It has a part number, it has a drawing number, and the budget's only $25. We ask for approval, and we're approved. Let's increase that budget to $25K. Now previously, purchasing could approve anything under $10K, so this will force finance to actually take a look at it. And they approved it, so we're good there. And when we go to $250, we're disapproved because that's over the $100K limit. So let's back off on that. Now engineering had to check part numbers. So we'll get rid of the part number. And it's disapproved because there's no part number. Great, that works. And we'll take out the drawing number. And again, disapproved because there's no drawing number. And now we've got everything back, we can get it approved again. So that all works exactly as expected. The key to the chain of responsibility is setting up the classes for each link in the chain, and then telling each link which is the next link that they should go to. And then you simply initiate the chain, and it takes care of itself. And that isolates a lot of the complication of the chain from the application code. The command pattern is fairly simple and really commonly used, so it's a nice one to get used to. So our problem is we want to decouple our method calls from our application. So in the command pattern, our method is basically going to be equal to a command. And we want to use an invoker class to call the command rather than the application code having to call the command. And our command is not going to have any parameters, and that will allow the invoker to invoke many different types of commands without having to worry about understanding the parameters. It'll treat them all the same way. This pattern is often used for menus. For instance, if you have a file menu, you have save and open, and the invoker will just call an open or a save command, and it's up to the command to actually do it. But the application doesn't have to know the specifics about opening a file or saving a file. That's left to the command. And the invoker doesn't have to know the specifics about any parameters that are being passed. The application, if it wants to save a file, can pass in the file name as a property of the command rather than setting it as a parameter to the command. And we'll see that in the example. It's also used in messaging and queues. So for a queue, we can just add a command object to the queue, and then an invoker within the queue will invoke the commands. And we can add a multitude of different commands to the queue because they have no parameters, and the invoker will invoke them all the same. They only have to implement the same interface for that to work. So the gang of four says a command pattern encapsulates a request as an object, thereby letting you parameterize clients with different requests, queue or log requests, and support undoable operations. And what all that means is that the commands implement a common interface. So I can parameterize clients with different requests, but I'm using the same common interface to do so. So I can send a lot of different requests to a client by sending in different types of commands. But the invoker is dealing with a single common interface. The undo operation doesn't imply that there's anything in this pattern that implicitly gives you an undo. It just means that there can be an undo command. It's up to the actual command to figure out how to do the undo. And of course, the invoker will execute the command by calling the interface method on the command. And there's only going to be one method that the invoker is going to call. So a common use of the command pattern is to update a user interface. This is actually used in Windows Presentation Foundation, that newfangled thing they did a while ago to replace WinForms. In our example, we're going to do the same thing, but we're going to do it with old school WinForms. So we'll have an iCommand interface, which is the norm. And for our update for WinForms, we're going to have a command that updates the color. So we'll have a control property, and that's going to be the Windows Forms control that we're going to update the color of. Now, a form descends from Windows Forms control, so we can apply this to controls like buttons or labels or text boxes, but we can also apply it to the form itself. Then we'll have a color property, and then we'll have an update color method. So I'll have a couple of different commands. One will be update back color, and one will be update forecolor. And I think it should be fairly obvious what the intent of those two commands should be. So when the update color method is called on the update back color command, it should hopefully update the back color of its UI property. Update forecolor should do the like, except it should update the forecolor of that UI element. We'll have a color invoker class, and that's going to call the update color method on the commands. And the color invoker doesn't have anything to do with the UI or color properties. The application that's going to create the commands sets those properties. So the decoupling is at the invoke level. The application can set the properties, and then it can pass the command to something else, like a message queue. So the invoke, or the actual method execution, is decoupled from the application. The actual properties are not, because the application does have to, in some way, say what command it actually wants to run. And if there are any parameters associated with that, it does actually have to specify those parameters. And it specifies them in the form of properties. So here's our class diagram, and it's pretty simple. We have an iCommand interface. It has the properties, color, and UI, and it has that one method that we're going to be invoking called update color. We have our update forecolor and update backcolor classes that implement iCommand. Then we also have our color invoker class, and it has a very simple method called invoke, and invoke will take an iCommand parameter type. In our form application code, the flow will be to create the actual command, like an update forecolor command, set its color property and its UI property, and then create a color invoker. And then the invoke method on the color invoker can be called. So if we were going to do something like a queue, the application form would still create the command and set its properties, and then it might do something like queue.add command. Then the queue, as it was looping through the items in its queue, would have its own invoker, and it would have to pass in the command into the invoke method on the invoker. So the queue would actually handle invoking the command, and the application would be done with it. It wouldn't even necessarily know the timing of that invoke. So that's where the decoupling of the command from the application code is. For our command pattern example, we're going to be doing a little bit of coloring. Windows Presentation Foundation uses commands to some extent to update UI. I thought I would apply that idea in a fairly simple way to an old school Windows form. So I have an interface called iCommand. It has two properties, color and UI. The color is simply a system.drawingColor, and the UI is a Windows form control. A form descends from Windows form control, so this is a nice interface that I can use. I can use that on controls as well as forms. Then I have a method called updateColor, and that's effectively the command method. I have two classes that are going to implement iCommand. update forecolor, and update backcolor. And hopefully from the names of those classes, you can tell what they're going to do. I then have a color invoker class with an invoke method, and that's going to invoke the command. So a pretty simple class diagram. iCommand is not complex either. Again, we have the Windows Forms control called UI, a system.drawing.color, and the method for update color. Note that update color has no parameters. That's one of the rules we have in the command pattern, is that the command doesn't carry parameters with it. That allows the invoker to treat all commands in a generic way. And you can see how if you are working with a messaging system or a queuing system, that you would want it that way so the message or queue didn't have to understand parameter types and how many there were or any of that. It would just call the command. So the command uses properties as opposed to method parameters. Update backcolor, of course, implements iCommand, and it has our UI control and our color property. And then in our update color method, it calls our UI control, sets its backcolor to the color property. So pretty simple code right there. ForColor does just about the same thing, except of course it sets the ForColor property on the UI control. And then we get the color invoker, and the invoke method is passed an iCommand called command. And when it's invoked, we'll call update color on that command object. So that's our color invoker. Again, none of this is very difficult. We're just demonstrating the structure of the pattern. So our form design, we have two buttons, one to set the background color and one to set the foreground color. I did have a little bit of fun and gave a color dialog, so we get to choose the color instead of it being hard-coded. So when we click on the Set Background Color button, we show the color dialog and check to see if the dialog result is okay. That was the amount of fun we had with that. So now we create an Update Backcolor command. We'll just call that Update Backcolor. We set the UI equal to this form, and the color equal to the color we got from the color dialog. Then we create our color invoker, and we call invoke on the invoker, passing in the Update Backcolor command. And that's all there is to it. If this invoker was a queue, we might do something like queue.add update backcolor, and then the queue would handle invoking it. Set foreground color, again, is extremely similar. We show the color dialog, and if that's good, we create an update forecolor command. Again, saying the properties of the UI and the color, creating our color invoker, and calling invoke, passing in the update forecolor command. Okay, let's see some colors. We'll go for a cheery yellow for the background, and bright blue for the foreground. So you can see the foreground color change there. So our invokes work, and our commands work. And the basic idea is not that this is a difficult or complex pattern, because it's not really. The idea is that we can use these commands in some other object that will allow us to invoke them indirectly. A queue is a really common example of that. So all we'd have to do is add the command to the queue, and then the queue would call invoke on it. And then the queue would move on to the next command and invoke that. And the queue wouldn't have to know anything about the commands whatsoever. It would just simply have to know what that common interface is to call the command and have it do its thing. The object that was creating the command would be the thing that would have to know what properties to set on it. So that's the example and the basic idea behind a command pattern. The interpreter pattern is not used a lot, and it's a little difficult to get a handle on sometimes. So we'll take a look at this, and hopefully you won't have to use it really often. For the interpreter pattern, the problem is you need to translate an input into a different output type. A classic is language translation. In fact, if you look for samples, you'll see a number of samples that convert Roman numerals into our normal numerals of today. Now, how useful that is at this point, I'm not so sure. But the translation is not a simple cast or a convert. It's more complex than that, and it's hierarchical, meaning that we can have a tree of expressions that go together. And in the pattern, we set out the rules of the translation. So it's not as simple as just a cast or a convert. Now, language translation is often used as an example of the interpreter, but a more practical use would be string command parsing. So for instance, you're taking a look at some sort of rather cryptic command that comes into your application. It may come over a wire where bandwidth is limited, or it may come from a database where the field width is limited, but it's somewhat cryptic and you have to convert that over into something else. Also, of course, just parsing code or SQL requires an interpreter pattern, or an interpreter pattern could be used on that kind of parsing as well. So given a language, define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language. In other words, we're going to define the grammar for what we're going to interpret, the rules basically, for how we're going to interpret the input to the output. And you can see that the Gang of Four talks about this in terms of grammar and language. It very much is focused on the idea of text translation. You could expand upon that idea in general, however, and say, if I think about it as a pattern, and I'm basically saying these are the rules to convert some input into another output, you can expand that idea away from just simple strings or complex strings and get into perhaps hierarchy of objects. But then you start to get fairly complex, and maybe there are other patterns that would do the job for you. So we'll stick with the classics at this point. So as part of the pattern, you have to define the grammar or translation instructions. And those are done in expressions. And you have a hierarchy of expressions. And there are two types. There's a terminal expression, which is standalone. In other words, it's just by itself, for instance, just a word. And a word just gets simply translated to another word, but there aren't any children words associated with that word. A non-terminal expression contains other expressions. So for instance, a sentence. A sentence would contain words. So let's just talk about something that gets slightly away from language. We want to parse a simple logic string. It basically just has and or operators and some string or numeric literals. And we want the output to essentially tell us true or false. And of course, we're talking about not just simply a single or and operator. We'd like to have a hierarchy of them. So we've got multiple operators, and the logic of them can work in combination. So in order to create an interpreter pattern for this problem, we're going to have an expression abstract class, and it'll have a single method called interpret. Descending from that abstract expression class, we'll have a value expression, and that's going to be a terminal type expression. So that's going to take a string or numeric as an input, and it's going to return a Boolean based on the value of that string or numeric. So for instance, if the numeric is not equal to 0, it'll return true, otherwise it will return false. If the string is not empty, it will return true, otherwise it will return false. Then we'll have an AND expression, and that will AND together two expressions. Now it might just be two value expressions. So we might have a value expression that evaluates to true and the value expression that evaluates to false, and obviously that will return false. But we could also have the AND expression and together two expressions that actually have expressions. So an AND expression could AND together two other AND expressions. Or our next expression is an OR expression. So we can use these in all sorts of different combinations, and you can think about how we start building a tree of all of those expressions. So the OR expression does the same thing as the AND expression, except it ORs together the two expressions. And then we have a parser class, and that parser class is going to go through our input string and build up all of these expressions for us. Once the hierarchy of expressions is built up, at that point, we'll call interpret on the root expression, and it will end up calling interpret throughout the hierarchy. So our class diagram is misleadingly simple. We have our expression abstract class, which simply has a single nice interpret method. And then we have the AND, OR, and value expressions, and those descend from that abstract class. And then we have the parser, also deceptively simple. It has a public parse method, and then it has a getNextExpression method, which is a private. And of course, the parser is actually, as you'll see, where most of the code is. And although there's not a lot of code there, it calls getNextExpression recursively. So there's a lot of logic there in terms of calling that and dealing with the actual string parsing. So string parsing is actually a little bit of a complex thing in itself and prone to error. And this pattern doesn't really fully address that. We're really using a parser to break ourselves up into expressions. The expressions are nice in that the application just has to call the interpret method on the root expression, as opposed to attempting to parse it and figure it all out itself. So that's the benefit of it. So that's the interpreter class, and we'll take a look at an example of that, and hopefully that will clear things up as to how it works. For our example of the interpreter pattern, we're going to take a crack at parsing some logic. Our class diagram is actually fairly easy, but most of the guts in it is in the parser. So we have our abstract expression class, and it has a single method called interpret. And then we descend from that expression class with an AND expression, an OR expression, and a value expression. So we're going to be parsing a string that has numeric or string values separated by AND or OR keywords. So a very rudimentary start at a SQL parser. Then we have a parser class, and its public method is called parse, and that's what our application will call. And then internally we have a getNext expression that we're going to call recursively. So here's our abstract class, and of course it's very simple, just with the one method called interpret. And then we have our value expression, and it descends from expression, and in the constructor we'll get a parameter called context, and that's going to be the input string to our value. So we'll store that in our context member, and then when the interpret method is called, we'll take a look at that context string value. We'll first try to parse it into a numeric, and if that works, we'll return whether the value is 0 or not. So any other value besides 0 is going to return true, 0 is going to return false. It's the old C++ version of a Boolean. If it doesn't parse into a numeric value, we're going to take a look at the string. And if that string is null or empty, then we'll return false. If the string is anything besides an empty string, then we'll return true. Then we have our OR expression. And the OR expression is going to take two inputs, essentially the left and the right side of the OR. And those are going to be expression types, and they don't have to be value expressions. They can actually be any expression that we'll call interpret. So on the constructor, we get the two expressions and we store them. And then in interpret, we interpret each expression and then OR those values together. So in this way, we can handle a more complex string than just a simple 8 or 5. The AND expression is structured exactly the same way. The only difference is down here, the two expressions are ANDed together instead of ORed. So this is actually the interpreter pattern, is to use these expressions. Now we're going to have a helper class called the parser, and it's going to return an overall expression because the interpreter allows for a tree or a hierarchy of expressions. So it's not simply a single expression and we interpret things. We can go through a string or any kind of input and start building up expressions and sub-expressions. So that's what this parser is going to do. So on the public parse method, we'll get a string input called context. And we'll first break that context up into pieces or parts, and we'll split that string on spaces. If we don't have 3 parts, we're just going to return the value expression of that context. So basically, if it's an empty string, we'll return false. Otherwise, it's going to return true. If there are at least 3 parts, then we're going to get the first expression. And it's going to be a value expression because one of our rules for this is going to be that we're going to start with a string as opposed to a keyword. So we'll get that value expression and we'll remove that part from the collection. And then we'll start going into getNext expression, and we'll pass in our string list and our first expression. So this first time we're calling it, we're going to pass in a value expression that has a number string. And we'll also pass in the rest of the parts of the input string. In getNext expression, we'll first check to make sure that we have at least 2 parts. Otherwise, we're just going to return the first expression. We're done. That's the end of the string. If we do have the 2 parts, we're going to get the second expression because we expect a value in the second part. So we'll get a value expression out of that parts collection, taking a look at the second string. And then we'll take a look at the first string. And that should be one of our keywords, either AND or OR. And then we'll clear those 2 parts out of the string collection. Then we'll take a look at that first part, determine whether it was an AND or an OR, and we'll create either an OR expression or an AND expression, and pass in our first expression, that's our parameter, and then we'll call ourselves recursively with getNext expression with this second expression that we just found. So in this way, we're going to build up the expressions. So we can have multiple keyword sections. So we can have 5 or Bob and Tom or 7 and just keep on going like that. And this will build up all of those expressions and aggregate them together for us. When it finally unwinds, it'll be because the parts count is less than 2. And then the parse method will return that overall expression that may indeed contain a lot of other expressions. So that's the parser, and you might want to step through that code. It's a little bit nasty, although it's not a lot of code, it just does a lot. In our design, all we have is the input text, a button to interpret that text, and the result. So this is the kind of string we're going to try to interpret. Just a basic logic string, so we have 0 or 5 and 0 or 0. By my calculation, that should give me a false. And looking at the button click event, we get our input string, we create our parser, and then we pass that input string into the parser and call the parse method. And that will give us our expression. And then our expression is a complex tree of expressions, or it can be. So then we'll call expression.interpret to string. In the process of calling that expression.interpret, we'll call all of the expressions in that overall global expression. So we'll build up and figure it all out. And then we'll just set our label to the result. So let's see if we got this logic right. So I believe this should be false. And it is, 1 for 1. Now I'm going to put in a 1 right at the start, so I believe this should tell me true. And it does. So at the end here, I'm going to put in 1, and I think that should also be true. And it is. And we'll just make sure it says false again. Okay, great. And then this middle section, and we'll interpret that text, and I think I'm going to be true here. Now let's see if I interpreted strings correctly. And again, we get a true. And if I just type in a space there, I get a false. So that's exactly what I was looking for. So the interpreter is used to translate some sort of input into another output. The most common analogy, of course, is language translation. And to some extent, that's actually what we just did. We just interpreted our poorly formed, logical, semi-SQL language into Booleans. So you can think about it that way, and that's a little bit more rigid than it has to be. You can also use the interpreter for other things, like building up objects from command strings. For instance, if you've gotten a command string that's somewhat cryptic because of the length of the string that was allowable, perhaps you're trying to interpret Twitter feeds. And then you take the 140 characters and you're looking for particular things, and then you interpret those 140 characters into some other objects or information that your application is actually looking for. So the idea that it's just purely a translator is a little bit limited. It can be more than that. The iterator pattern is something that I'm sure you've actually seen before. There are a number of .NET framework collections that in some way implement an iterator pattern, or at least they present to you the iterator. So let's take a look at what the iterator pattern consists of. So the problem, very simply, is that you have a collection of objects you need to access. Now you only want to provide sequential access. You don't want to provide random access so that the application can get element 12 and then element 5 and bounce around. And you also don't want to provide any access to the inner collection that's being iterated over. So it's a sequential read-only collection that you're providing here. The iterator limits the access quite a lot. Now, in talking about the problems previously, we've always talked about specific problem types. The iterator is used just about everywhere, and you've seen it before. So the official definition is that the iterator provides a way to access the elements of an aggregate object sequentially without exposing its underlying representation. So the aggregate object contains the collection that we're iterating over, and that collection could be a raw array or list, and obviously it can be read and write. Certainly a read-only collection isn't useful. The aggregate also provides the iterator, so it's the thing that creates the iterator and provides that to the application interface. The iterator provides the access operations into the aggregate collection. For our example, we're going to have a basic collection of users. In this example, we're going to have an iAggregate interface, and that will have a getIterator method. which will provide the Iterator interface that we're going to be using in the application to access the collection. iAggregate will also provide the interface for the raw collection itself, because we do need to be able to populate that collection. Then we'll have the aggregate class, and it will implement iAggregate. So the aggregate provides two things. It provides the raw collection that we can read and write to randomly and create in general, and it provides the iterator into that collection, which provides the much more controlled access. We have the iIterator interface, and we have a first property, and that will set our array index or collection index to the start of the collection, and it will return the first item in that collection. And we have the current property, and it will return whatever the item is at the index currently. We have the next property, and that increments the index and returns that next item from that collection. And then we have isDone, and that will indicate whether we've hit the end of the collection. Now there's no random access here. So the typical way that this is used is the first property is called, which basically sets the index at start, and then in a loop, next is called. And then at any time you can stop and get the current property, but sometimes they don't even have the current property on the interface. So it's just first and next. And of course you need to check the output. Sometimes the next property returns you a null, which indicates you're at the end of the array. And sometimes you need to check the isDone property, if there is one. So our iterator class implements the iIterator interface, and it has internal members for the aggregate, which provides us our raw collection, and the index, which provides us the index into that aggregate collection. And here's our class diagram. So we have that iAggregate interface, and it has properties for count and this. And this is an index property, so it will return the item that corresponds to the index in the collection that the aggregate holds. And then we have the getIterator method, which will return the iterator into this aggregate collection. The class will have an internal member for our values, and that's our collection. And then we have the properties that we talked about before. iIterator has the methods that we talked about, first, current, next, and isDone. And the iterator class implements those, and it has internal fields containing the aggregate and the index. And then in our example, we're just going to use a user class, and it's a very simple class, just has a name and a user ID. So that's the inner workings in the iterator, and I'm sure you're familiar with the concept, so it's just nice to be able to see how it looks on the inside. So the code might give you a little bit of a deeper dive on that. The iterator is a pattern that I'm sure you've all worked with before when you're using .NET Framework objects and collections. But in this example, we're going to take you into the inner workings of how an iterator pattern works. The inner part of the iterator is the iAggregate interface. And that interface provides us properties for count and this, and we'll talk about this in a little bit, and getIterator as a method. And the getIterator provides the iterator to this aggregate object. The aggregate class that implements iAggregate contains a member called values, which has the collection of all the items. So that's our inner raw collection. And then we have properties for count and this. This allows us access to the values collection, and we can do that simply by indexing with an array. And then we have our getIterator method, and that's what we're going to present as our interface for the application into this collection. That getIterator will give us an iIterator interface, and that has properties for current, first, isDone, and next. And the iterator class that implements that interface has an internal field for the aggregate and an internal field for the index, and then the same group of properties for the implementation of the interface, and of course a constructor. When the application first accesses the iterator, it should call first, and that will set the index property, which is the index into the aggregate values collection, to the first element in that collection, and it will return that first element. Then next, we'll increment or iterate the index and return the next item in the collection. And you can keep on doing that until isDone is true. Current won't iterate the index. It'll just give you the current item that the index is pointing to. And then for this example, we're just using a collection of users, and the user class is really simple, just has a user ID and a name. And there it is, a simple storage class, nothing special to it, and the iterator pattern can iterate any sorts of objects that you want to store in a collection. So here's our I aggregate, and it simply has a getIterator interface method, a this property, which returns a user object, and you can access that through an index, and then the count property, which gives you the count of the number of objects in the collection. And here's the implementation of that collection. We have an internal member, a list of users called values, and in our constructor, we construct a new list. And then we get into the I aggregate members. For getIterator, we create a new iterator class and return that. And we pass in ourselves for the parameter, and that allows the iterator to iterate on this class and the collection that this class contains. Our this implementation with our index just simply accesses our collection by that index with a little bit of checking. If our index is out of bounds, we're returning null. You might want to throw an exception here, depending upon your implementation and what you want to do. And on our set, we're just going to add to the values collection. And then, of course, the count property returns the count of the number of items in the collection. Our iIterator interface has the properties first, next, current, and is done. Let's take a look at those implementations. So we have an internal member of type iAggregate, and we also have an internal index, and it starts off at 0. When we create the iterator class, we get an iAggregate as a parameter, and we set our member to that. On the interface, when the first method is called, it returns a user object. It sets our index to 0 at the beginning of the collection and calls into the aggregate with that index. Note that it does set that index to 0 because we're going to be using that index continuously. And in our next method is where we're going to be using it. So with next, we increment our index, and then we check to see if isDone is true or not. If isDone is not true, then we do indeed still have items in the collection that we can return. So we'll return the next item out of that collection, going into the aggregate, passing in the index. Otherwise, we'll return a null. In this case, we probably do want to return a null, as you'll see in the form code, because often we're using a while loop and we're checking to see if the return is null. Our current property simply returns the aggregate at the current index. And isDone checks to see if the index is greater than or equal to the count. If it is, that means we've iterated all through all of the items. Now note, we don't have any random access through the iterator into our aggregate. We can only call first, next, and current. And we do not have access to this index property from the outside world. So this is a sequential access into the collection that is stored in the aggregate. If you need a random access, the iterator pattern is not for you. We have a Go button, and we're going to iterate through a list of users and list them out. So when we click Go, we're going to create ourselves a new aggregate, and then we're going to fill up that aggregate with some users. And then we'll get our iterator from the aggregate by calling the getIterator method. And note that we're typing it as an iIterator. Now that we have that iterator, the only thing that we can do that's actually particularly useful is call first on it. So we'll call iterator.first, and that will give us the first user that's in that aggregate. And we'll set our string equal to that name of that first item. And then we'll start looping. So we'll want to check while the iterator is not done, and then we'll get the user object from the iterator's next property. And this is where that null check comes in. If that user was null, then we've run out of items. If it's not null, then we'll add the username to our string, and eventually we'll display it in that label. So I'm sure you're familiar with this kind of code because you've used it before when you've dealt with .NET collections. But now you've actually seen what it looks like underneath the wraps. So we'll just give it a run and make sure that it actually does iterate. And there we go. Bob, Bill, Tom, Rob, and Dan. And right in order. So that was exactly what we were looking for. So that's the iterator pattern. And as you can see, these are pretty non-specific. The only thing that was specific was the user that was stored within the aggregate. But you could store any kind of object within that aggregate. And in fact, instead of making this specific to users, you could also use a template so you could store absolutely anything you wanted to and type it dynamically. The mediator pattern helps us in isolating communication between objects so that the objects don't need to have references to all of the other objects that they might be communicating with. So you've got a group of objects that communicate with each other. Sometimes they need to communicate to multiple objects, and you don't want those objects to have to hold references of all the other objects, and then those objects to hold references of all the other objects that they communicate with, and so on and so on and so on, and you can just imagine the spaghetti that would happen with that. Particularly if you imagine a messaging application, which has a lot of users in it, and a lot of users that can talk to a lot of other users, and all of the combinations that you might have. You might have each user having to have 100 references to other users. It's definitely not the kind of structure that you want to support long term. Now, the mediator pattern is often talked about in terms of messaging and chat and that kind of communication because it's very easy to imagine it that way. But you can go a little bit further and you can think about it in terms of command response. Commands and responses could be looked at just basically as messages. So if you start thinking about a message queue, which isn't necessarily used for messaging per se, at least not human messaging, then you can start to get an idea of how a command response might fit into this pattern as well. So we've got a nice long definition from the Gang of Four. The mediator pattern defines an object that encapsulates how a set of objects interact. The mediator promotes loose coupling by keeping objects from referring to each other explicitly, and it lets you vary their interaction independently. So basically, the mediator is keeping individual objects that are going to be communicating with each other from knowing anything about each other. It's the one that keeps the collection of all the objects, and it mediates the communication between those objects. So the mediator is going to have a list of objects called colleagues. And the colleagues don't necessarily know anything about the other colleagues. Colleagues just communicate directly with the mediator. They don't communicate directly with each other. So the classic example, of course, is messaging. And you have a group of colleagues, and they just want to pass simple string messages to each other, maybe like Twitter. So we have an iMediator interface, and it's going to have a register method. Each colleague needs to register with the mediator to add itself to the collection of colleagues that the mediator stores. And then there's a post message method. And the post message will be handled by the mediator and passed along to all of the colleagues in the collection of the mediator. The mediator class implements iMediator, of course, and it holds that list of colleagues. In the colleague class, we're going to give them a name property, and we're going to have a send message method which has iMediator as a parameter. So a colleague could actually have multiple mediators that they talk to, and they can send a message on a particular mediator. So for instance, if you're talking about group messaging, and someone belongs to a couple of different subgroups, they could have a mediator for each one of the subgroups and send a message just to the first subgroup or just to the second subgroup. And they do that by passing in the iMediator parameter because that refers to a mediator class that actually holds the list of colleagues in that group. And the colleague class also has a receive message method. And the send message goes to a mediator, and the receive message comes from a mediator. None of these are called by another colleague class. So we have that iMediator interface with its property for the list of colleagues and its methods for registering a colleague and posting a message. And then we have the mediator class, which implements iMediator. It has its colleague list for internal storage of all the colleagues property, and then it implements the two messages, register and post message. And then we have the colleague class, and it has its name and the send message and receive message methods. So the flow of this in our application or in our form is that we will create a number of colleagues, and we'll simply create them with their names, and then we'll create a mediator or two, and we will register colleagues with the mediator. And then if we want a colleague to send a message, we can call send message on the colleague object, passing in the mediator as a parameter. That message will go to the mediator post message. The mediator will handle in the post message calling receive message on all of the colleagues in the colleague list. So that's how the mediator will manage sending out a message from one colleague to all of the colleagues that it has in its collection. So that's the idea of the mediator pattern. To demonstrate the mediator pattern, we're going to do a very simple messaging app. It's a really common use for the mediator pattern, so it seems appropriate. But the mediator pattern doesn't have to be specifically to messaging or chat. If you replace these objects with some other more generic objects, change our message strings to something else, I think you can see that the possibilities expand. So we have an iMediator interface, and it's going to have a property called colleagues, which is going to be a collection of colleagues that use the mediator interface to message each other with. Then we have a method called register, and that will register the colleague with the mediator. And we have a method called postMessage, which obviously will post the message to all the colleagues in the mediator group. We have our mediator class, simply implements all of those things. And then we have our colleague class, and a colleague has a name property. It has a send message method and a receive message method. So these all are pretty obvious as to what they should do. Go into our colleague class, and we have that name property. And in our constructor, we're passed in a name parameter, and that's going to be the name of this particular colleague. And then we have send message. And send message takes iMediator as a parameter. So we're going to use the mediator to actually send this message. And then we have the string message that we're going to be sending. In order to send the message, we're going to call mediator postMessage, pass this in, which is this particular colleague, and the string of the message. Then on the receive message method, we're going to be called from the mediator, and the mediator will pass us in the message that we're receiving and the name of the sender. Note that we're not passing in the sender as a colleague object, because one of the points of the mediator is to isolate colleagues from each other. And then on this receive message, we're just going to write the line to the console of who received it, that they got a message from the sender, and what the message was. Our iMediator interface has our list of colleagues, our postMessage method, and our register method. Register method registers the colleague on the mediator, so it takes a colleague parameter, and postMessage takes a colleague parameter, which is the sender, and a string message. Note that it doesn't have a receiver colleague because we're doing posts to the entire group within the mediator. And the implementation of that. We have our internal member, which is a list of colleagues called colleague list, and we populate that with a public property called colleagues. On the register method, we add the colleague parameter to our colleague list. And on postMessage, we take the sender colleague and a string message. Then for each colleague that is in our colleague list, as long as it's not the sender, we call receive message on that colleague and pass them the message and the sender's name. So it may seem a little strange that postMessage on the mediator actually calls receive message on the colleague, but that's actually the point. The flow of this is that a colleague will call a send message, and they'll be talking to the mediator when they try to post the message. The mediator's managing who receives the posts. So instead of calling a more global send message or post message on the actual rest of the colleagues are the ones who are receiving the message. So we call the receive message method on those colleagues, each one of them in the collection except for the sender, who has already seen the message because they sent it. So although it may be a little counterintuitive immediately, it makes sense when you think about it a bit. Our form, again, is really complicated. We have a Go button because we're going to do console writes, and we're just going to hard code some colleagues and messages. So here we have our hard-coded stuff. We have 4 colleagues, Bob, Sue, Chris, and Donna, and we created one mediator, an iMediator interface, and then we register 3 of our colleagues, Bob, Sue, and Chris, to that first mediator. And then Bob sends a message on that mediator that says, "Hi, folks." We should see that Sue and Chris receive a message from Bob saying, "Hi, folks." Donna, because she's not in this mediator group, did not register with this mediator, should not receive the message, and Bob shouldn't receive the message because he's the sender. We have a second mediator, and just Sue and Donna registered for it. And then Sue sends a message, and it's a more private message, because the only one who should actually receive it is Donna, because she's the only one left in the second mediator group. Okay, so let's give this a run. I'm going to open up that output window a bit so we can see it. And when I tap on Go, we should see those console writes. And there they are. First, we see Sue, a message from Bob, "Hi, folks," and Chris, a message from Bob, "Hi, folks." So that's the first mediator group getting that "Hi, folks" message from Bob. Then the third line, we have Donna, a message from Sue, and it's a more private message. So that's what we were looking for, and that's what we expect. So that's the idea behind the mediator. And you can see that what I did here was I sent string messages. And if we go back to that area where it receives the message, all we did was a console write line. We could actually do anything we really wanted to in this receive message. So if we start opening up our thought process, this doesn't have to be about chat and string messages and such. We could be passing in data, or we could be passing in commands to some objects. So the mediator doesn't have to be specifically about messaging. It's really more about communication and trying to isolate each object that's being communicated to so that they don't have to worry about having references to each other. So let's just talk a little bit about that in terms of a UI. I may want some sort of event that I receive from a UI element to be communicated to other UI elements on that page or form. But I don't want one UI element to keep an internal collection of all the other UI elements on the form. That's where a mediator might come in, and I can send command objects from one UI element to a group of UI elements without the first UI element knowing anything about the other ones. So this is where you start getting into the basis of some other UI patterns. So the mediator, although often you see examples like this that are based on chat and messaging, can be used for a lot more. Let's take a look at the Memento pattern. Often there are times where our users make mistakes and they want to undo them. There are also often times that we make mistakes and want to undo them as well. The Memento pattern helps us do that. If you want to be able to restore an object to a previous state, but you also want to follow good object-oriented practices, which means that there is no outside access to the internal state of your object, this pattern may be for you. It's good for undo operations and transaction rollbacks. So the idea behind it is that I can go along with an object and make changes to that object, but I can use the Memento to change back to a previous version of that object. So I can take a snapshot of that object and restore myself back to that, despite all of the edits or changes that may have occurred afterwards. So the Gang of Four says, without violating encapsulation, capture and externalize an object's internal state so that the object can be restored to this state later. So what they're saying is for encapsulation purposes, we're not supposed to expose the internal state of an object to the outside world. So the object itself is going to have to capture its internal state and externalize that. It does that by creating a Memento object. So it externalizes that internal state, and that gets stored in another class so that we can use it for a restore operation or an undo operation later on. So we have the Memento class, and it's going to store the state of the object. Then we have the Originator class, which is the class that we're using in our application, but it's also the class that we're going to want saved because we may want to restore it or undo it later on. In order to do that, we need a couple of methods. We need a method that will create the Memento, and we need a method to restore the class from the Memento. Then the third class we need in this pattern is called the Caretaker, and it very simply just holds the Memento. So that's the externalization of that object's internal state. The storage class is the Memento itself, which stores the state, and then the Caretaker is the class that holds that state externally. So one of the classic examples is an edit undo example. So we're going to edit a user object. And our user class, which is also known as the Originator class in the Memento pattern, has a user ID, name, username, password, those kinds of properties. The standard properties you might see on a user class. Then it has two additional methods, save state and restore state. We then have a user Memento class, and it reproduces those properties, user ID, name, username, and password. Now, it doesn't have to reproduce faithfully the public interface of the object we're trying to restore. What it has to save is the state of the class necessary to restore that object. So that may not mean that we're actually storing all of the user properties or the public interface. It may mean that we're storing internal variables to reproduce that object. So there's a subtle distinction there that you might want to take note of. The Memento class has a constructor that has parameters that are used to recreate the state of the class. So it has individual items for each property or each member that's required to restore the class. Then the caretaker class has a memento as a property, and that's all it really does, just storage for that. So the memento pattern is really pretty simple. There are only the three classes, and there's not tons of interrelationships or complications between them. The user class, or the originator class, is something that we would have anyway. We just have to add a couple of methods to it: restore state and save state. The user memento is very similar to the originator class, in this case the user class, and has a very similar interface depending on what variation of internal and external members we're storing. And it just has a constructor. It doesn't have any other complicated members. It's primarily a storage class. And then we have the caretaker class, and all it has is the memento, and that's all it does. It just stores it. There's nothing else there. So this is a pretty easy pattern to implement. The drawback, of course, is that you're doubling up on storage because you have a memento and a user class. So that may or may not be a good thing, depending upon what your architecture is doing. So there is a cost to providing an undo operation for a user, and there is a cost of providing a rollback on a transaction if you're going to use this pattern. But it is really simple to implement if you do have that requirement. Let's use the memento pattern to do an undo operation for just editing a simple user object. In our class diagram, we have a user class. It has standard properties: name, password, username, user ID. It also has two methods, one called save state and one called restore state. And those are going to use the memento object. Our user memento class has the same properties, name, password, user ID, and username, as the user class. It has a constructor that will take those properties as parameters. We can use a memento class to save all of the properties like we are here, or to save some internal variables that are not available on the public interface, or combinations thereof. Whatever we need to save in terms of the state of the object to restore the object is what we need to save in the memento. And we have a caretaker class, and all it does is stores the memento. So it has an internal field for that and a public property for it. Taking a look at the user memento class, we simply have storage objects for user ID, name, username, and password. Then we have a constructor passing in those parameters, and we store them in our public properties. Now we get to the user class, which in the pattern is known as the originator. And this is the class that the application is actually going to work with, make edits to, undo where necessary, restore, save. It's actually the working class that the application is using. So it has its public interface with user ID, name, username, and password. And then it has two other things that you don't normally find in this kind of class. It has a method called restore state, which passes in a user memento. Very simply, restore state goes into that memento and pulls out all of the members of the memento and restores its own state. There's also a method called save state, and save state does the opposite. It creates a user memento, passing in the current properties and parameters necessary to save the state of the object, and it returns that memento. Our caretaker is the object that manages and stores the memento. So it has a private member for the user memento and a public property for it. And that's all there is to that caretaker. So let's see what we're going to try to do. We've got a form, and we want to be able to make entries to a user object. We have fields for user ID, name, username, and password. When we click on Edit, we want the object to be edited. When we click on Undo, we want it to return to the previous state before the last edit. So a fairly common idea for an application to do. So when we create our form, we're going to create our first instance of the user object, and we'll just load it up with some dummy data. And then we'll call displayUser to display that user object in our text fields. And that method is down here. We're just reading each individual property off of that user object and displaying it into text. We have private members for the user object and for the caretaker. Now we get to the edit. When the edit button is clicked, we call the caretaker and set its user memento object equal to user save state. Going back to that save state method, it takes its current state and creates a memento object with it. So we're going to take a snapshot of that user object and store it in the caretaker. Then we'll go ahead and make the edits to the current user object. So we'll get the user ID, make sure that it's actually an integer value, set the user ID property, the name, username, and password properties from the user input in the text boxes. So now our current user object that our class has been changed. Now if the user clicks the undo button on that user object, we'll call restore state, and we'll pass in the memento that the caretaker is storing for us. Going back to restore state, it takes that memento and restores the properties of the user object. So we restore the user object and then display the user. So that's all we have to do for this undo. So let's give it a run, make sure it works. And you can see I've started with user ID 1, name Keith, username KDub, and password Moose. I'm just going to quickly type some 5s on the back of each one of those entries. Click on Edit. So now my object has been edited. When I undo it, it goes back to the original. Let's just check to see if it really works. So I'm going to click on Edit, and I'm going to make another edit. So I clicked on Edit to store that edit, and now if I undo, it undoes one step. So that's what we wanted it to do. We just wanted it to restore back to the previous version, not necessarily all the way back to the original version. So that's the code for the memento. Now you might say, well, that's really easy and I'd like to use that all the time. And that's true, but there is one drawback, of course, to it. Our user object does have to have this complication with regards to having methods for restore state and save state. And if your object is fairly complex, these methods can be fairly complex. The other drawback is that the caretaker stores a memento object. And that memento object is storing all of those values all over again. So by having undos on all of your objects, you're increasing your memory footprint by quite a bit. But otherwise, the memento is a nice pattern for rolling back transactions and doing undo operations. The observer is a pattern that allows us to manage notifications from an object. We're interested in seeing any changes in that object's properties. So you have code that you want to be able to see changes in an object, and you have multiple interested objects throughout your application. And of course, you want those notifications to be handled automatically. You'd also like to not burden your object too heavily with managing, notifying all of those observers. You don't want to have to know anything about those particular objects in order to be able to tell them that something changed. You might use this for a data change notification for the user interface. And this is something that Microsoft uses in Windows Presentation Foundation, or WPF. So for instance, if there's some change in an underlying data source that feeds a number of controls on a visual form, you'd like to be able to get that change broadcast to all of those individual controls so they can update their display depending upon any property changes to that object or data source. You might also be building a price watcher application. So obviously it's a price watcher and you want to be able to notify all those objects or people who are watching the price anytime the price changes. And this basic idea applies to any kind of monitoring app. Anything that you're monitoring would like to actually have those changes fed to them automatically. So the definition is define a one-to-many dependency between objects so that when one object changes state, all of its dependents are notified and updated automatically. That's actually one of the more clear definitions of a pattern that I've seen. So we're going to have a subject class, and this is the class that's going to be observed. It contains the data that we're interested in seeing that there are any changes to. It also contains and manages and notifies the observers. So it's going to have a collection of observer classes, and it's going to manage registering and unregistering those observers and also notifying those observers. We typically want to put that in a base class so that we don't have to have it in our concrete implementation classes. Then we have an observer class, and this provides the method to call on notifications. So this is essentially the buffer in between the object or the subject class and all of the other interested classes that want to know about the changes. So for an example, we have a price watcher. We have a price object, and we want to see any of the changes in price. So we'll have a price abstract class, and it'll have the product price property that we're interested in monitoring changes. It also has a subscribe and unsubscribe method, and those methods are to manage observers. So if an observer wants to see product price changes, they will call the subscribe method and pass themselves in. If they no longer want to see those changes, they call the unsubscribe method. And then the price abstract class will have the notify method, and in that notify method, it will call the observers method to do an update to whatever classes are interested in the price change. Then we have a price observer abstract class, and it will have an update method. The notify method of the price abstract class will loop through a collection of observers that descend from the price observer class, and it will call the update method on each one of those price observers whenever there's a product price change. And then we'll have our price watcher class, and that will descend from price observer, so it will be a concrete implementation of that class. And in the update method, we'll call a price changed event to notify our particular client of a price change. So visually, here's what these classes look like. On the right, we have our price abstract class, and it has a private member for a list of observers. It also has an internal member for product price and a corresponding property for product price. Then we have the notify method, which will notify all of the observers of a product price change. We have the subscribe method, which will simply add an observer to the observers collection, and unsubscribe, which will remove that observer from the observers collection. We have a big store price, which is just a concrete implementation of the price abstract class. All of the observer-related code is actually in the abstract class, so the big store price class is not burdened with it. The only thing it has is just the product price property. Then on the left-hand side, we have our price observer, and that's our abstract class, and it only has an update method. And that update method is what's going to be called when the notify method is called in the price class. And in the price class, that collection of observers is of type price observer, so it's of the type abstract class as opposed to concrete observer classes. Then when we get to our concrete observer class, called price watcher, we have fields for our name, which we also have a property for, and an internal member for price. And we have a method for update, and of course that implements the abstract class method. And that's the thing that's going to be called when the price does a notify. And in that update method, we're going to fire off a price changed event. And our form will handle that price changed event. So we have this separation of the actual observer and the price class. And that's really what we're looking for, is to kind of break that coupling so that we don't have a whole lot of weight on the price class to deal with the observers. We do have some weight in that we have the subscribe and unsubscribe and notify, but we don't have a lot of weight to it. The price watcher itself is the thing that's actually going to deal with the events and managing whatever needs to do upon update. For our observer pattern example, we're going to do a price tracker. What we would like to have happen is that when a given price changes, that we're notified of any price changes. So for our classes, we have a price object. This is an abstract class, and it will contain a member of observer objects. So each one of these observers will be notified of any price changes. We also have a member for the product price and a property for that price. And then we have methods. We have a method for notify, and when a price changes, it will call notify and notify all of the observers of the price change. And then we have subscribe and unsubscribe methods, and those are for the observers to subscribe to notifications and to unsubscribe to those notifications. In a concrete implementation, we have our big store price class, and it just implements the things that are in that abstract class. Then over on the observer side, we have an abstract class for price observer, and it just has one method called update. Notify on the price class is going to end up calling update on an observer class. Then the concrete price observer class will have members for name and price and a property for the name. Then we'll have a method for update, of course, and then we're going to have an event for price changed. So the application will get an event fired out from this observer. So here's that abstract price class. It has a list of price observers, and note that we're using the abstract class for observer as opposed to the concrete class. And we also have a private member for the product price. The subscribe method, we add an observer to our observers collection. Unsubscribe simply removes the observer. And the notify method will notify each observer in our observers collection that the price has changed. So we'll call the update method on the observer and pass ourselves in. And note that we do have a public property for the product price, and that's really what the observer is interested in. If this price class was a bit more complex, the observer would have access to all the properties. So that's a decent thing to do. You could likewise just pass the price in this update method. The choice is yours as to what your application needs. So when the set is called, if the product price has changed, we'll of course update it. If it hasn't, we won't bother. And then we'll call notify. And notify will notify all of the observers in our collection. For our concrete implementation, there's not a lot to do. It's all done in the abstract class. And we have our observer abstract class, and it just defines the update method. And note that the update method has a price called price to watch, and that's the abstract class for price. And we have our concrete observer, and I've called it price watcher. It descends from price observer. We have members for name and price. And then we also have an event called price changed. In our constructor, we just get the name. It's just going to be the name of the observer. The name is for use of any application or form or object that is calling the observer, just as a reference for that object. So we have a property called name that's available to any object that uses this observer. And then we get to the real meat of it. We get to the update method. And the update method is what's called by the price object when the product price changes. And then the price object passes itself in as a parameter. When the update method is called, we'll get the product price from the price object, and we'll store that in our price member. And then we'll call the price changed event if anyone has subscribed to the event. And we'll pass in the price value. Here's our form design. And we're just going to have an area that we can change the price on, and we can set the new price when the button is clicked. And then we'll have a couple of observers, and we'll show that those observers actually see this price change. So in our code, we have a member for Big Store Price. And you'll note that that's the concrete price object as opposed to the abstract, because of course we can't instantiate an abstract class. In our constructor, we do instantiate the Big Store Price, and we just initialize its product price with the value in that numeric control on the form. Then we create a couple of price watchers. So we have price watcher called observer1, and we create him and give him the name observer1. Then on our price object, we call subscribe and pass in observer1. And then we handle the event for observer1 price changed. We follow the same pattern for observer2. We construct it, pass in the name, and then add it as a subscriber to the price. And we also hook its price changed event. When the user clicks the Set New Price button, all we do is take the value from that numeric up-down control and set the price's product price to that value. So that creates a price change. And then in the observer event handlers, we're just looking at the price watcher, which is the sender, and we take its name, and then the argument E is actually the price. So this will tell us which observer and what the price is changed to. And we do exactly the same thing for the second observer. We just set the second label. So let's see this one in action. My initial price is set at $5.25. If I click on the button, I don't get any events from the observer because that price didn't actually change. So let's put in a change, and there my observers both work and get the price change. If I click on the button again, you can't see that we didn't have an event. If I go back down, it picks up that event change. So in this way, I can have a number of different objects observe a change to another object. This pattern in general is used fairly often, particularly with dynamic or bound lists, in order to observe a collection and any changes to the collection. In fact, there's a class called Observable Object for just this kind of idea. But this is how we can create our own observers and our own pattern within our applications in case the framework objects don't quite suit what we want to do. If you're familiar with the concept of a state machine, The state pattern will make perfect sense to you. A state machine is basically the idea that an application is in a certain state, and depending on conditions or user inputs, that state will change, and it can change to different states depending upon the inputs that were provided or the conditions that occur. The state pattern helps us work with that concept. So you have an object and you want its behavior to change depending on some outside condition or a user input. It's also dependent upon the state that that particular object is in at that time. So this is the idea of a state machine. And we don't want to burden the object with a really large if-then sort of logic that says, oh, I'm in this state and I'm looking at all of these different variables and the users input all of these things. And if I have this, I'll go over to this state. And if I have that, I'll go over to that state. And it can be very burdensome and complicated logic. So we don't want to put that into our classes. This kind of idea, of course, is perfect for navigation because an application often has to decide what page or screens it's going to show depending upon other conditions, like what the user has input to us, what we might read in some other data, and where the application is in general. And all of those things go into where we want to navigate in terms of what pages or screens we show to the user. Same idea behind logic flow. Again, if we have some sort of input with data and we need to work on massage that data and decide whether we're doing updates or inserts or perhaps a validation error, we need to have different states that provide us that logic flow. And as I just mentioned, there's validation. Basically an if-then. If it's valid, then we go to here. If it's not valid, then we display something that says it's not valid. And all the branches off of that, depending on what kind of validity we're talking about, we may have different errors and different actions that we take. If it is valid, then there may be all sorts of different branches depending upon the actual values of the data or user inputs that we want to take. So all of those deal with the different state and the conditions outside of that state. So the state pattern allows an object to alter its behavior when its internal state changes. The object will appear to change its class. It doesn't really, however, so that's one of the keys to it. So we typically have a context, which is going to be the application interface that contains the state object. So this is the application or environment that our object is working in. Then we'll have the state, which will be an abstract class, and it'll have the interface that will be provided for any of the behavior changes. And that's going to be the part that would appear to be dynamic depending upon our state changes. And then we'll have different concrete state classes for each possible state. So for example, we're going to talk about app navigation. Our state will determine which page we're going to go to. And we're talking about, in this case, the state of the user, whether they're logged in, logged out, or a premium user. So we have a user class that reflects those different states, either logged out, standard, or premium. And then we have a state abstract class with methods for login, log out, and upgrade. And then we have the next page property. And that's really what we want to get at when we're doing the navigation. And then we have the different concrete state classes. So we have a logged out state class, and its next page is going to be the login page, because we can't go anywhere else besides the login page when we're in a logged out state. And then we'll have a standard state class, and its next page will be the main page, because that's the only place that we go when we're in a standard state. And then a premium state class would be showing a better main page, which is called our premium page. So we have these different versions of state, and they all descend from the abstract state class. So let's put this together. We have our state abstract class over to the left, and we have some internal members to keep track of the level that we're at, the next page that we need to go to, and our user object. Then we have properties for the user object and the next page. And then we have the methods that we have to implement for the abstract class. And then we have our concrete states. And they all implement the login, logout, and upgrade methods. And they also implement something called state change check. And that's going to do the work to determine what state we're currently in and what state we should be going to. And then our user class, along with the normal kinds of properties that you would normally see in a user class, like name, address, city, state, phone number, username, password, those kinds of things. We've also added a state object, and that's the abstract class that we're calling out in the user so we can switch in the various different states. And then we also have a next page property for the user. And that next page property is simply going to reflect the next page property of whatever state we have as a member for our class. So if we're in the logged out state, its next page property tells us we're going to go to the login page. So the user's next page property will reflect that we should be going to the login page. And then the states will handle it from there as to where we go depending upon the conditions. And they'll calculate that or figure that out in their state change check method. And the user class will also have methods for login, logout, and upgrade. And those are the methods that the application will call. And the user will implement those methods, and they'll pass it along to the state object. So for instance, when login is called, obviously we'd like to validate the username and password when the user logs in. And if that passes, we're going to call into our state object and call the login method. That will switch out our logout state and switch it into a standard state or a premium state depending upon what kind of user we are. So that's how we can work with state and have the state objects work on deciding where we go next and what state we should go to, and we keep that code out of our user class. And that's how we can implement a state machine using the state pattern. I'd like to use the state pattern to help me with my screen navigation. I have an application that requires a user to log in. There are also two types of users, a standard user and a premium user, and depending on which kind of user they are, they get taken to a different main page. So I'd like to use the state pattern to figure out the state of the user, whether they're logged in or not, and the user type, in order to tell me which page they should go to. So I have a state abstract class, and it has internal members for level, next page, and user. The level is the level of the user, whether they be a logged out non-user, a standard user, or a premium user. This also allows us to expand if we end up with super premium or super premium universal users. Just as an aside, I once worked for a place that sold site licenses and enterprise licenses, and then they had a customer who was so big that they sold them a universal license. The only place they had to go, they thought, was a Galaxy license from there. So we have properties for next page and user. And the next page is going to be the name of the page that we should navigate to for this particular user. Then we have methods on the user for login, logout, and upgrade. So if we have a standard user, they can upgrade to a premium user. Descending from this abstract state class, we have the logged out state, and it implements login, logout, and upgrade. It also has a private method for state change check. And that will work into figuring out which state we're at and what we should go to. We also have a standard state and a premium state, and they implement the same methods. And then finally, we have our user class. And of course, there's a name for the user, and we're not doing any other properties just to simplify this example, and a state property. So this keeps the state of the user. And we have properties for next page and state. And we have methods for login, logout, and upgrade. And of course, the constructor for the user. Looking at the user class code, it's relatively simple. We have our private members for state and name, our constructor passing in a name, and we also initialize the state to logged out state. So if we're creating a new user, we're initializing them to be logged out. They're going to have to go through our login form in order to be a logged in user. And we have a string for next page, and that will return from the state the next page for this user. We have our state property, and then our methods for login, logout, and upgrade. And note that they just pass right through to the state. The user doesn't actually do anything with these methods. So you might say, if we have the state property available on this interface, the application could call this on state. And that's true, but then we would lose some of that encapsulation. So we actually just want the application to only know about the user. And here's our state abstract class. We have protected members for the user and the next page string, and a protected int for level. Then we have a property for user and a property for next page. And then we've defined the signature of the three methods for login, logout, and upgrade. Taking a look at the logged out state class, this is a concrete implementation of our abstract state. In our constructor, we're passed in a state object. This is likely the previous state from the user. Our next page, because we're logged out, is defined as login page. And we also set our user equal to the user that comes from the state parameter. And then we initialize ourselves. And initialize, we're just setting ourselves to level 0 because we're logged out, so that's going to be equal to a level 0. We also have a second constructor that passes in a user object rather than a state object. And again, we set our next page equal to login page, we set our user member, and we initialize. We have our login method, and when the user has logged in, we'll go to level 1. And this is another reason why the user object has a login method that's available for the application. We don't want the state to have to actually do any kind of login logic. That should be the responsibility of the user to determine, for instance, if the username and password match. So that shouldn't be in a state object. So there is a separation of those, but it's just not as obvious in a simplified example. So once the user is logged in, the level will change to 1, and then we'll call state change check. And we're going to do that for all three of these methods: log in, log out, and upgrade. We'll change the level, and then we'll do a state change check. So log out, we'll go back to level 0, and an upgrade will go to level 2. State change check runs a switch on the level, and if it's case 0, which means it's a logged out user, well, that's our current state, so we just leave it this way. For case 1, that means it's a logged in standard user, so we need to set the user state to the standard state, and we pass in ourselves into the constructor in the standard state, which has a very similar constructor to this state. So going back to that, we get the user object from the state object. We're not doing anything else with the state object, so I could conceivably pass in a user object and simplify this to only have the single constructor. But we could also keep ourselves a little bit of a history for a back button in this way, so that we know the previous state. So if it's case 1, we go to the standard user state. If the level is at 2, we go to the premium user state. And the standard state looks essentially the same. It only has the one constructor for state because we don't call it directly from the application. We're only call it from a logged out state. And our next page is the main page. And other than that, the code is essentially the same, as is the premium state. So we've got a simple form design, just 3 buttons, one for login, one for upgrade user, and one for logout, and we'll display here what the next page to show is based on the state. So here's our form. We have a private member of type user, and I'll just create a new user called KW. When the login button is clicked, I'll call login on the user, and then I'll set my next page text equal to the user's object next page property. And I'll do basically the same thing for each one of the buttons. For the upgrade button, I'll call the upgrade method on the user, and then again display the next page. And likewise for the logout button, I'll call the logout method, and then display the next page. So this is where we could handle our navigation instead of actually just taking the text and saying what the next page is. Instead of passing in a string object for the next page, we might actually have the proper page objects and actually call some code to navigate to the page objects or the form objects, depending on what technology you're using. So let's see it in action. And when I tap on login, I'm taken to the main page, which is correct. And if I upgrade the user, I'm taken to the premium page, which is correct. And if I log out, I'm back to the login page. Now, one quirk here is that I can also upgrade my user even though I never logged in, and I'm taken to the premium page. Obviously, we need a little bit of work in enabling or disabling buttons and or handling that logic in the state objects to make sure that I can't go from one state to another state and violate some sort of rule, like going from a logged out state straight to a premium page. But perhaps that's okay as long as I've gone through some sort of login procedure. But this is the basic idea behind the state pattern. So I can use states outside of the individual object, like it's outside of our user object here, and I can have the states handle the state of the user in separate classes so that I don't break encapsulation on the actual object that I'm working with. The strategy pattern is an interesting pattern, and it's not used a lot. It's one of the lesser used patterns, but we'll go through it, and perhaps you'll find some uses for it in your future applications. The idea is you'd like to be able to choose an algorithm or a set of steps to run, but not necessarily always the same from your particular object. Now, you could have these various algorithms buried into your object, but then you'd have a lot of things that are coded into your objects that you don't necessarily use all the time. So you'd like that algorithm to have a common interface so that you can choose among them. So for example, if you're going to do some sorting and you want to be able to choose the sorting type, for instance, you can have a strategy pattern that will choose the sorting type, and you'll have different algorithm classes to handle the sorts. There may be different calculations that you have to do based on different conditions. So the object can choose what set of calculations to do depending upon that strategy or the conditions that happen to be occurring at that time. It may also be in some sort of transaction process, so that as you go along during that transaction, you can choose whatever algorithms you need to do for the state of the transaction. So we want to define a family of algorithms, encapsulate each one, and make them interchangeable. So they're going to share a common interface. Strategy lets the algorithm vary independently from the clients that use it. So in other words, I have strategy classes, and then I have client classes that use the strategies. And I can switch the strategy classes in and out of the client, so the client can choose whatever strategy it wants to at runtime. So I'll have a strategy abstract class, and it will define the algorithm interface. And then we'll have a concrete strategy class, and it will implement the appropriate algorithm. And of course, it's most likely that you'll have multiple concrete strategy classes. So let's take a look at a discount strategy. We want to be able to apply different discounts to our customers depending upon their loyalty or status. So we're going to have a discount strategy class. We'll start with our customer class, and it will contain a discount strategy, and that will be a discount strategy member that we'll end up calling when we want to apply a discount. So our customer class will contain a discount strategy abstract class, and that discount strategy abstract class has an apply discount method. So when we want to apply the discount, we'll call into our strategy class and call apply discount on that class. And then we'll have various implementations. So these will all descend from our discount strategy class, and we'll have a no discount strategy, which will apply, of course, no discount. We'll have a student discount strategy, which will apply 25%, a loyalty discount strategy class, which will apply 15%, and then we wanted to have a loyal student discount strategy class. But we noticed that if we added up 15 and 25%, that, 40% is getting a bit high, so we gave them 33% instead. And this is what it looks like in a class diagram. So we have our overall discount strategy abstract class. We'll have a discount percentage property that all of the descending classes will apply, and a apply discount method. And the concrete discount classes are actually just going to set the discount percentage property. The apply discount is actually a common method to all of them. That's not necessarily the case. In fact, a lot of times in a strategy pattern, it will be the exact opposite. The apply discount method, or the strategy method, will be the thing that really varies from class to class. But in this case, we have the same math, it's just the value that changes. So then we have our customer class, and it's going to have a discount strategy private field, and it will have a method for setting that discount strategy, and then a method for apply the discount. So our client, or our form in this case, is going to create a customer class, and it will create a discount class, or at the time of applying the discount, it will create a discount class. And it will be some concrete instance, depending upon the situation, whether it be a student or someone with no discount or a loyal customer, whatever is appropriate. It'll get the appropriate discount class, and it will call set discount strategy on the customer object. And then when it actually wants to apply the discount, it'll call the apply discount method. And in our example, as you'll see in the code example, that apply discount method will take an input parameter of the sales total, it'll apply the discount, and return the discounted price. So that's the general idea behind the strategy pattern. Customers love discounts, so let's see if we can use the strategy pattern to give them some. We're going to have a customer class, and it'll be a normal customer class, although we haven't filled out any of the properties that you might normally see. But for our example, we're going to have a private member called Discount Strategy, and we'll have a method called Set Discount Strategy, and that will set that member. And then we'll have a method called Apply Discount. And the basic idea is that we're going to take that customer object, give them a sale, and then pass in that sale amount to apply discount. And depending on what discount strategy we have for this particular customer, a different discount or no discount will be applied. The work will actually be done in the discount strategy object. So we have a discount strategy abstract class, and it'll have a property called discount percentage and a method for apply discount. And then we're going to have various discounts that descend from discount strategy. We'll have a no discount class, a loyalty discount class, a student discount class, and a loyal student discount class. So let's take a look at the abstract discount strategy class. It very simply has a property for discount percentage, and then a method for apply discount, which takes the sale amount as an input parameter and returns the discounted sale amount. Now you could also have it return the discount amount, whatever's appropriate for your application. Here we're being a little hard. This is our no discount class, which means we have a discount percentage of 0. And when we apply the discount, we do a lot of math that we don't actually need to do in this particular class, but it's the same generic math throughout. So we apply the discount, do the calculation, and return the discounted price, which in this case is going to be the same as the sales price. We have a student discount, and we're going to have a 25% discount. So when apply discount is called, we'll take 100 minus the 25, giving us 75%. We multiply that times the sales price. And of course, because we were dealing with percentages, we divide it by 100. We have our loyalty discount, which the discount percentage is 15%. We're trying to hook young students as opposed to keep our old customers. So our discount percentage for loyal customers is 15%, and we run that through apply discount. And it's the same math as we had before. And our last discount is loyal student discount. Because we added it up and said, wow, the loyalty discount is 15% and the student discount is 25%, that's a full 40%. We're actually losing money on this deal. That's not where we want to be. We came up with a different strategy for loyal students. So their discount percentage is just 33%. They don't get the full discount for both. And we run it through the same apply discount method. For our customer object, this would look like a normal customer. For instance, I might have customer name, address, user ID, that sort of stuff. We've stripped those out for this example, and we have a private member for discount strategy. And we have a method for setting the discount strategy, which sets that private member. And then we have an apply discount method, which passes in the sales value, the same way we do so with the discount strategy, and it will return the discounted price. And to do that, the customer object just has to call the apply discount method on the discount strategy. So the customer object doesn't have to know anything about applying discounts and the different discounts that would be involved. If we didn't use the strategy pattern, this would be a much longer method with all sorts of switches involved and parameters involved to figure out what discount should be applied to what customer. And we don't want to clutter up our customer code in that way. So that's why we're using the strategy pattern to separate that idea of applying different discounts depending on different conditions, but keeping the customer object the same, because it doesn't change with regards to the conditions that are changing. It's the discount that does, and the strategy we use for calculating the discount. So that's really what the strategy pattern is about. So here's our little sample form, and we have checkboxes for student discount and loyalty discount, and we have a sale amount, and a button for applying the discount, and then we display the final price. In looking at that form code, when we click the Apply Discounts button, we'll create our customer object, and then we'll go through and check the various checkboxes. and depending on the combinations of the checkboxes, we'll set the appropriate discount strategy on the customer. So if we have both of the checkboxes checked for loyalty and student, then we'll call the customer method setDiscountStrategy with the loyal student discount. Likewise, if it's just loyalty checked, we'll set the discount strategy to loyalty discount. Student checked, student discount. And then finally, if they don't have anything checked, no discount for them. Then after we've done that, we call the customer object and call the apply discount method on that customer object, passing in our total sale value. And we get in return the discounted price. And then finally, we'll just display that in our final price label. So let's get some discounts. So we have a total sale of $19.99. And if I don't check anyone and I apply the discounts, I should hit no discount. And I do indeed have a $19.99 non-discounted price. If I put in the student discount, that was about 25%. And it comes down to $14.99, or a discount of $5, which is about 25%. If I do the loyalty discount, that was going to be 15%. And indeed, we come up with $3 off of the $19.99 price, and that's about correct. And if we apply both discounts, it was a 33% discount, and you can do the math on that one, and that looks about right as well. We remove them, and we're back to the non-discounted price. Our discount strategy works, and the strategy pattern works. The template pattern is probably the simplest pattern we've got, and I'm sure that you already have used it, even though you might not have called it a template. For the template pattern, basically you want to create a starting place for classes to inherit from. Does that sound familiar? That's basically an abstract class, and it's one of the bases of inheritance. And of course, that's one of the main object-oriented principles. So the template pattern isn't anything new in object-oriented programming, but it is one of the bases of object-oriented programming, and it's also one of the bases of all the patterns that we've gone through. You can see we've used a lot of abstract classes in order to create a template to work with. So their definition of a template is define the skeleton of an algorithm in an operation, deferring some steps to subclasses. The template method lets subclasses redefine certain steps of an algorithm without changing the algorithm structure. So essentially what we're saying is that our template pattern can create the basic skeleton. It doesn't have to implement all of the methods that we expect to have, but it can implement some of them. And any of the classes that inherit from the base template pattern can override some of the properties or methods that are in the template. So essentially we're talking about an abstract class which defines a public interface. And then it may provide some of the implementation. It could actually attempt to provide all of the implementation for that interface or just parts of it. Any classes that inherit from that abstract class, of course, have to finish the implementation and then alter the implementation as they need. And of course, you use the keyword override for that alteration. So let's talk about a data logger example. We'd like to create a data logger class, and we want to, of course, log any application info. Anything that happens along the way in the application, we'd like to log it. But we're not exactly sure where we're going to log it to. We might log it to a file, we might log it to the Windows event log, or we might end up at a later date logging it to a database, or who knows, sending it out on a message trail. We want to keep our options open, but right immediately, we definitely know that we want to log it to file and the Windows event viewer. So we'll create ourselves a data logger abstract class, and it will have a log data method because we know the application is going to need that method. Then we'll inherit from the data logger class and create a file data logger. In the log data method, we'll simply log the information to a text file and just start appending lines as we go. We'll also create a Windows event logger that inherits from our data logger abstract class, and it will log to the Windows event log every time the log data method is called. So for both of those classes, we're overriding the log data method. And in fact, the log data method in the abstract class doesn't have any implementation at all. It's just a virtual, so we haven't implemented anything for that because we know that every type of data logger is going to implement it differently. And here's our class diagram. It's exactly what you would expect. We have an abstract class called data logger with that log data method, and then we have our two descending classes, file data logger and Windows event logger. and both of them implement log data. On the file data logger, we do have a text field called log file, and that's the file name that we're going to log to. In the Windows event logger, we have a thing called log source, and that will be the name under which we log to the Windows event log. And of course, the log data methods in both of those classes are going to have completely different implementation. But to our application class, we're just looking at a data logger type, and all the application has to do is pass in whatever message it wants to log into the log data method. And from there, it doesn't know anything about files or Windows events. So we have that kind of abstraction away from our application. So our application doesn't have to know anything about data logging implementation. And that's the basic idea behind the template pattern, and of course, object-oriented inheritance. The template pattern is probably the simplest and most obvious pattern we have. In fact, you probably use it often without even necessarily knowing its name, or you call it something else, inheritance. So in our example, we're simply going to use a template for a data logger. Let me zoom this up a little bit so you can see it. So we're going to create an abstract class or a template for our data logger. It'll have a single method called logData. And we can use this template in order to implement concrete classes. And that's what we're doing. We're going to create a file data logger, which will log information to a text file, and a Windows event logger, which will log information to the Windows event log. Now, the implementation of these is obviously different, and we have some members that are a little bit different as well. The file data logger has a log file field, whereas the Windows event logger has a log source field. And those are because, of course, logging to a file requires different information than logging to the Windows event viewer. But they both implement log data. So our abstract class, in this case, just lays out the template of what we want the descending classes to do. So we have an abstract method called logData, and we pass in a string of data. Now, this abstract class could also have some concrete implementation as well that would be included in our template, and essentially descending classes would get that for free. But in this case, we just have the single abstract method. The file data logger has a constant string called logFile, so we're going to log to this log.text all of the time. And then we override the logData method. And this is where our implementation is. So we're just using the template essentially to create this structure, but it's up to this class to actually implement the method. So we'll create a string path by getting the directory name of our currently executing assembly. In other words, we're looking for where this application is running. And then we'll combine that with the log file. So we're actually going to just put log.text right in the same path as the exe. We'll open up a stream writer with that path, and true, meaning that we're going to append to the file. Then we'll write a line to the file, just the date time now, and a colon, and the data. So each time we write to the log, we'll have another line that will be time tagged. And then we'll close the stream writer, and that will do the write to the file. On the Windows event logger, we have a constant string called log source, and we'll call this template pattern after the name of the application. And this is what will be visible in the Windows event viewer. The Windows event logger will also override the logData method, and it will first check with the event log to make sure the source exists, and that's our template pattern log source. If that source doesn't exist, we'll create the event source, and we're going to call it an application event that we're logging. I should also point out that we need to use the system diagnostics namespace for our event log. So now that we've created the event source, or we found that it already exists, we'll format our message. Again, the same format, a date time string, which is really kind of unnecessary for a Windows event log, but I wanted to keep the same message style just for the example. And then we call write entry on the event log, passing in our log source, our message, and the entry type. In this case, it's just information. We could put in an error or a warning as well. Our form design is really simple. We just have an area for the user to enter a message and a write to log. And when write to log is clicked, we're going to call a file logger logData with the message and the Windows logger logData with the message. And we're creating the file logger and the Windows logger at creation of the class and keeping them open throughout. In all likelihood, we'll want them throughout the lifetime of the application. Okay, let's see our logging. We probably didn't do a Hello World application in this class, So let's do a fake one right now, and we'll log hello world. And I'll write to the log. Check the file log first. And here's my log.txt. And there's my date, time, and hello world. Okay, so we're good there. Now let's check Event Viewer. We'll come up to the action and refresh. And here's our information event. And it does indeed say hello world. So both of those logs worked. Of course, the real point of this is that we're using the data logger abstract class as our template class. And we can descend as many classes as we want from this abstract class or template to follow. We can also make this abstract class or template as complicated or simple as we like. And we can put implementation into it, or we can just leave it as a framework. So that's the idea behind the template pattern, and I'm sure you've already used it many times. The visitor pattern is one of our more interesting patterns, and it continues on the theme of trying to simplify our objects by breaking out functionality from the storage object. For the visitor pattern, our object is to add functions to an object dynamically. So we're going to separate the object from the operation. And we're going to do this in the case where we have an object that may have a lot of different functions, and it doesn't necessarily use them all. They're effectively options. And we don't want to clutter up our object with a bunch of functions that we may or may not use and make the object really long and really complex. Also, we don't want to weigh the object down in terms of its memory footprint with a lot of things that it's not going to use in any particular run. So we want to be able to add the functions as they're needed and to limit the clutter of the object itself. So in that way, it should be more maintainable, and it also carry a lighter footprint. The other area about maintainability is the individual feature classes can be maintained separately from the actual base object itself. So here's a couple of scenarios that we might use it in if we want to add different output formats. For instance, we have an export function, and we want to be able to export it to Word docs and maybe Excel spreadsheets or PDFs, and all of a sudden we start adding all of these different functions, probably only one of which is going to be used within our instance of the app. So we don't want to load up our class with all of these functions, and of course they're really different. Some of them can be fairly complex, and we don't want to clutter up the code with that either. So we can use the visitor pattern to allow us to add different output formats to the object dynamically while the application is running. Same idea behind business objects and just adding functions to the business objects. The formal Gang of Four definition is the visitor pattern will represent an operation to be performed on the elements of an object structure. The visitor lets you define a new operation without changing the classes of the elements on which it operates. And that's the separation that's key. The visitor lets us create new classes without ever changing the old class. So that's the key to the maintainability bit. So we have two main components of a visitor pattern. We have the element class, which is our client object, and the element class is the same class that you would normally write for, say, a business object, except you would add one area that accepts visitors. Then we have an iVisitor interface, and it usually only has a visit method, and that's the method that will actually apply the function. So in concrete terms, let's say we have a user object, and this object is in a game perhaps, or even maybe some sort of loyalty program where we apply credits and expiration dates to those credits. So we want to be able to update the credits and change the expiration dates. And in the future, we may add other things. For instance, if it's a game, there may be all sorts of different types of credits that you want to add as the game goes on. And of course, they would all have different expiration dates. And depending upon the level you're in the game, some credits would apply and be available, and others would not be available until you get to much higher levels. So you'd like to use a visitor to add those credits and functions as the game goes on. So we'll have our user class, and it will have a name property, credits, and an expiration date property. And then it will have an accept method, and that will take an iVisitor parameter. The iVisitor interface will have the visit method, and it will have a user parameter. So we'll implement concretely a credits visitor, which will update the credits. So when our user accepts a credits visitor, the visit method on the credits visitor will be called, and it will pass in a user parameter. And the credits visitor will update the amount of credits on the user object that we passed in as its parameter. Same logic applies to the expiration visitor class. We'll update the expiration date when the visit method is called on that expiration visitor class. And that visit method has the user parameter, so we'll be updating the expiration date on that particular user. And here's our class diagram, and of course it's not very tightly coupled, which is a good thing. Over on the left side, we have our element, which is our abstract class, and it only has the single method called accept. Basically, we have a base class that will accept visitors. Descending from that element class, we have our user class, and it'll have properties for credits, an expiration date, and the name of the user, and it'll have methods for accept, and of course a constructor for the user. And the accept method, as we've talked about, will accept an iVisitor. Then for our example, we're going to have a collection of users, and we're going to put them into a users class. Internally, there'll actually be a list of user objects, and we'll also have an accept method, an attach, and a detach method. This users class doesn't descend from element, so that accept method is different, but it actually does effectively the same thing. When the accept method is called, it will simply go through each one of the users in its list and call the accept method on those users. So that accept method in the users class also takes an iVisitor as a parameter. The attach method will add a user to the user list, and detach will remove it. And then we have the iVisitor interface, and it has a visit method, and that will take a user parameter. And then we have the credits visitor and expiration visitor that we talked about. And again, they just implement that visit method and do whatever they need in terms of updating credits or expiration date on the user parameter that's passed into that visit method. So you can see we're nicely decoupled, and we can work on these visitor classes and add more of them if we need without ever touching the base element classes. So that makes the code a lot simpler in each one of the individual classes, and it makes the overall code a lot more maintainable and expandable. Let's use the visitor pattern to manage credits on our user objects. In this example, we're going to have an abstract class called element, and that will simply have a single method called accept, and that will accept our visitor. Inheriting from that abstract class, we have our user class. And the user class will have properties for credits, expiration date, and the username. And of course, we'll implement the accept method. We'll also have a class of users, which will have a users list, which will be a list of our user objects. And then also methods for accept, attach, and detach. So we'll be able to add users and remove users, and also accept visitors for all of the users as a collection. And then we get into our actual visitor interface, and it simply has a single method called visit. And we're going to have two classes that implement that interface, a credits visitor and an expiration visitor. And of course, they implement the visit method. So what will happen is we're going to create some users, and we're going to add them to our users class. And we'll do that by the attach method. And then we're going to want to make adjustments to their credits. So we'll create ourselves a credits visitor and call the user's accept method with that credits visitor. Each user will then in turn accept the credits visitor, which turns around and calls the visit method, which will make adjustments to the credits. We'll also have an expiration visitor, which will follow the same pattern, but apply to the expiration date. So in this way, these functions are separated from the actual user class that they're implemented on. So let's get into the details a bit. Here's our abstract element class, which simply has that accept method. And the accept method takes a parameter of iVisitor type. Our iVisitor interface is also very simple. It has a visit method, which takes an element type. And here's our user class that descends from our element. We have a constructor that passes in the name, the expiration date, and the credits, and we set those appropriate properties. And then we have the accept method that we're overriding from our abstract element class. And when the accept method is called, we're passed in an iVisitor, and we call visit on the visitor method with this as an object. So this allows the visitor class to run whatever functionality it needs to on this particular instance of the user. Our users class has a list of users, the attach method, which adds a user to our list, the detach method, which removes a user, and accept. The accept method, like our user accept method, takes an iVisitor parameter, and we simply loop through every user in the users list and call accept on that user. And of course, when we call accept on the user, the visit method is called on the visitor. So this is essentially all framework at this point. There's not a lot of work done yet. So let's get into our credits visitor. Our credits visitor implements iVisitor, which means we implement the visit method. All we're doing in this visit method is we're taking our element, which we believe is a user type, and then we're going to add 50 credits to its credits property. Now we could do anything in this visit, and obviously the expiration visitor is going to do something else. What this has done is it essentially has separated this functionality from our user structure. The user itself is really just a storage object with the exception of this accept method. And this accept method can accept any kind of visitor that implements the iVisitor interface. So we can actually add functionality dynamically. Instead of adding a lot of functions to the user class itself that may or may not get used, we can pick and choose what functions we want to use on the user class at runtime. So we can add them dynamically by accepting a visitor. Going back to our credits visitor, that's what's going on here. When we call accept and pass in this visitor, the user credits will be incremented by 50. In a completely different function, we have our expiration visitor. And when visit is called on the expiration visitor, we add a year to our expiration date. It implements the same interface, so we can pass it in to that accept method on the user object. So that's how we can dynamically add these kind of functions to a single object. In our form, we have an Add Credits button and an Update Expiration button. And we have two labels down here because we're going to have two users, one named Greg and one named Richard. And we'll display their status after we've clicked Add Credits or Update Expiration to make sure that our visitor actually worked properly. In our form, we have a users class, and we have a user named Greg and a user named Richard that we initialize with these properties. So Greg's expiration date is right now, and Richard expired 6 months ago. And Greg has 25 credits, while Richard has 42. And that's at start. In our constructor, we'll attach Greg and Richard to our users object, so they get added to the collection. And we'll update the status so we can see what we're looking at right from start. On button Add Credits click, we call users, accept, and pass in a new credits visitor. And this will update the credits for all of the users in this class. And then we'll update the status to update the display. When the Update Expiration button is clicked, we'll do the same thing. We'll call users accept, but we'll pass in an expiration visitor instead of a credits visitor, and we'll update the status. And update status simply updates the two labels with the name, the number of credits, and the expiration dates of those credits. So once all the structure is laid out, the code itself is really short and simple, which is a nice maintainability feature. And now we'll make sure that it runs, which is also a good maintainability feature. So we start with Greg having 25 credits, expiring today, and Richard has 42 credits, expiring 6 months ago. So let's add them some credits. And you can see we added 50. And then we update the expiration date, and it did indeed increment a year. So that was exactly what we were looking for. And of course, if I add some more credits, it keeps on going up, as does the expiration date. So the visitor doesn't necessarily have to be a one-shot thing. You can repeat the visits. Now, these are pretty simple functions that we're putting in the visitor, but it gives you an idea of the structure and the reason why we're separating essentially the data and properties of our class from the actual features that we're applying dynamically. If you've gone through all the Gang of 4 design pattern lessons and seen the 23 patterns, you may be wondering, what happened to the MVC pattern? Well, the MVC pattern is extremely well used, but it's actually not a Gang of 4 pattern. But it is really important, so we're going to spend a number of lessons working on it. MVC stands for Model View Controller, and it's a design pattern actually created in the 70s by Xerox, so it actually predates the Gang of 4. And it's used in ASP.NET since 2007, and it's extremely well used today. It's actually more of an architectural pattern as opposed to a design pattern. We typically think of design patterns as smaller portions of an application describing interrelationships between classes. MVC actually describes the entire architecture of the application, and it breaks it up into those three pieces: model, view, and controller. The model is essentially equal to the data, and that data can come from anywhere. It can come from a database, which is often the case. a business layer, which may also talk to a database, but the business layer itself would be the model in the MVC pattern, or just a simple view data. Perhaps it comes from an XML file, or just a text file, or it's just an object that is created. The view is the user interface, and the controller processes requests, operates on the model, and renders views. So it's basically taking user input, working on the model or the data, and sending that model to the views so the views can be updated and their display can be updated to reflect any changes that happen in the data model. Here's the classic diagram of an MVC design pattern. We have the user down bottom, and starting with a user action, the user is going to provide some sort of input that will go into the controller, and that's where that user uses the controller. In response, the controller will manipulate the model in some way. It may call for a new model worth of data, in other words, a query, or it may update the model. Either way, it's going to have to do something with the model in response to that user action. When the model is updated, it'll be sent to the view, and the view will update its user interface elements. And then the user, of course, will see that update. So you get that complete loop. It says, okay, the user is going to create an action. It'll go through the controller, which talks to the model, which talks to the view, and gives the user some visual feedback. That's the classic pattern. The MVC pattern is used well outside of ASP.NET, but we're going to be using it specifically in ASP.NET for a while. So the model works a little bit differently, and there's some details that ASP.NET adds to it. So in our ASP.NET pattern, we have our user out to the left creating a URL request. Anything the user does, whether it be click on a button, enter text into a text area, or click on a link, creates some sort of URL request, whether it be in background or for a page reload. That URL request goes into our view object, and our view object translates that request into a URL for routing. ASP.NET has the idea of routing, so we don't specifically call out page URLs, we call out more often folders. The routing will route into our controller class, and our controller can have responses to a number of different actions that the routing provides. It can be the initial view of the page itself, but it can also be in response to different button actions within that page, and also AJAX requests. So the controller can have a number of routing interfaces. The controller will then talk to the model, which may indeed talk to a database. It doesn't have to be hooked to a database, but it commonly is. And it will do any queries, updates, inserts, deletes, whatever is the appropriate response to the user input. The model will then send any updates to the controller, and the controller will pass those model updates to the view, and the view will send out the response. In fact, often the controller is passing an instance of the model to the view, so it's a little bit of a pipe through on the output side. So why do we have a model view controller anyway? What good does it do? And it seems like maybe it's nice that things are separated, but does it add any complexity? Well, that's the really important part, is there's a separation of concerns. So the data is handled completely in the model classes, actions are handled completely in controllers, and user interface is completely handled in the views. So I have that separation, which means that I can have a data model and a controller, and they can handle different types of user interfaces, which is really important when we're talking about mobile versus desktop platforms in today's world. So that separation is really important. It adds discipline to our code and also adds maintainability. That separation also adds a bit of simplicity to the code. For the same kind of reasons that you've seen when we go through the Gang of Four pattern, we're often trying to create a separation between our application code and other features or functionality. And we create separate classes to do that. And it helps our code become more maintainable because we have smaller code modules and they're not coupled as tightly to each other. The MVC pattern does that as well. The model, controller, and view are not very tightly coupled at all. So changes within the data model typically won't hurt anything upstream in the controllers or the views. So that really helps the maintainability of our code. It also simplifies our code a little bit because, of course, we're not doing the three functions in one big lumpy application code that possibly turns into spaghetti. So let's talk about the pieces. We have the model, which is our data storage class. And the source of the data doesn't matter. It can come from a database. It can be a business layer. It can be responses from a web service. It can be file reads, or it can just be data that's created in memory on the fly. Doesn't matter what the source is. In terms of use in the model view controller, the model isn't particularly active. It doesn't do a lot, whereas the controller is the thing that actually does things. So in ASP.NET, the controller inherits from system.web.mvc.controller, and it will contain public action methods. And those methods may be for the initial page load, or they may be in response to any sort of user input on that page. There are associated configurable URLs associated with the controller, and the routing system will point and translate URL requests into those URLs, which will in turn call controller action methods. And we'll see how this works when we get to actual code examples. Those action methods will process and then return a view object, which typically is a data model. Our view primarily presents the user interface, and that's really its only job. The early MVC versions actually used ASP.NET Web Forms, ASPXs, for the view. In MVC 3, Razor was introduced, and what Razor does is it allows code within HTML. This is sort of like the old server-side calls in ASPX. So as you'll see, we can actually do for loops within a data collection in order to generate HTML. So if you remember the old ASPX repeater control, that's extremely easy to replicate in Razor without actually having to do a control. So that's the basic idea behind the model view controller pattern and the way we're going to be looking at it in ASP.NET. There's some terminology and technology that we also want to take a look at, and we'll be doing that in future lessons. Before we dive into the code, let's take a look at some of the common terminology and syntaxes used in MVC projects. They're not specific to MVC actually. They're more .NET technologies, but they're used an awful lot in the samples that you'll see in MVC. First is the way objects are initialized. Rather than creating a customer object and calling out new customer and closing the statement, and then setting each property by calling customer.companyname.owner-name, often we create new objects and then within curly braces initialize the properties. There's not really any difference in the way the code runs. It's just a little bit of a different and more simplified syntax. So you can see in the example, we're creating a customer object and we're setting the company name and owner name properties, sort of during the construction of that object. It's not technically during the construction, however, because the constructor in this case has 0 parameters. And you can tell that because we're using a curly brace there. If it had parameters, we'd have regular parentheses with the parameters inside the parentheses. This is just creating the new customer and then turning around and setting that company name and owner name property. Below it, you can see how we're initializing a list of strings. This may be a little bit more familiar to you. It's the same way you would initialize an array. And we can do dictionaries basically the same way by putting the key value pairs in curly braces and then putting the curly braces in an overall set of curly braces for the dictionary. So you can see in this example, we're creating a new dictionary, which is a templated dictionary, which has a string key and an integer value type. And then we have for our first key value pair, the string key and the value 5. And then the second one has the string key 2 and the value 25. The var keyword is also used a lot. In this case, we're doing that same kind of constructor that we did before for the new customer, except instead of typing customer as customer, we're just putting in var. Now, some people seem to think that this means that it's untyped. That's not true. There's an automatic type inference, and that inference is at compile time. It is not at runtime. So that if you actually attempt to assign this to a different type of object, you will get a compile time error. So the var is understood in this case that it is a customer object. So it's not untyped, and the compiler understands it. So you won't have those kind of errors in terms of type mismatches. If you're thinking, sort of like the old untyped VB, that's not what it is. Now, I'm not a big fan of var myself, because if I actually know the type, I'd prefer to just see it. But you'll see it a lot in MVC examples. We also have anonymous types, and this is where var is actually handy. So in this case, we're creating a customer. However, we're not giving our object a type. We're basically creating this type on the fly. So it creates a little small storage class, and it will handle whatever types we put into those properties. So if I had another property there, for instance, for customer ID, and I put in the value 5, it would understand that that was an integer. So we can actually type the properties as well, but there just isn't really any kind of class name associated with it. This isn't something that you're going to want to pass around your application. It's really more of a temporary thing, and it's often used in response to JSON requests. So in response to an action, and I'm sending out JSON, I can create this little object and send it down in JSON. And the JSON won't really care about the type. It only really cares about the properties and the property values. So again, this is still strongly typed in its own way, and so I can't assign it to a different type of object. So it is still strongly typed at compile time. We also use lambda expressions a ton in MVC, and we use them both in the views in Razor and also in the controllers when we're working with data models. And the lambda expression is in that area of the where clause. So in this case, we're looping through our customers that we're getting from a data context, which is actually going to be our model in our model view controller. And we're working with a where clause. So we're looking to filter our customers where the state is equal to Massachusetts. So on the left side of the arrow operator, you can see the letter C, which is the variable name that matches our customer C. So that C is a customer object. And that's our input into the lambda expression. The rest of it on the right-hand side is the actual expression itself. So we're looking for the state property on the customer object C, and we're looking for it to equal MA. And we can use and or operations and all sorts of other operators in parentheses and make relatively complex statements if we want to. So you'll see these a lot, and you'll see them often in conjunction with link. Now link, or linQ, is called Language Integrated Query. My understanding is that the formal pronunciation is actually linQ. I don't seem to be able to bring myself to pronounce it that way, so you'll hear me say link most of the time. So here's a link statement, and I'm creating a product list, and it's basically a select statement. So I'm looking to select from my product table, or my data context, which is my model, my products collection, and I'm going to create a new select list item. And I'm going to do that by setting my text property for my select list item equal to the product name and the value of the select list item equal to the product ID. So what you can see is that this is semi-SQL within code. And you can also see it's a little bit backwards because it starts with the from clause as opposed to the select. So just going through it a little bit, we're going from products, and that's just going to be the collection name in data context.products. And then from that, we're going to select and create a new select list item, and we're going to set its text and value properties using the properties on the products collection. So if there are 5 products in that data context products table or model, we're going to end up with 5 select list items. So in this way, we can query within code. And this doesn't have to apply specifically to databases. We can query any sort of object that supports the iQueryable interface. So we'll also work on domain objects, not just data-related objects. Now, this technique can be somewhat controversial because it actually encourages you to put the rough equivalent of SQL within code, which in properly separated concerns is not necessarily a good idea. But you will see it very often in controller code, but not really to operate the database directly. It's really just to do more fine querying on the actual data model itself. So your mileage may vary as to whether you want to use this kind of technique or actually just offload it into some sort of business layer. And your business layer could run link as well. The first time I ever saw it, I didn't care for it for just that reason. I didn't like the SQL in the code. But things change and times evolve, and now I'm much more comfortable with it than I was. But again, it should be in its own place as opposed to becoming more of that kind of spaghetti where you've got link spread all over the application. It should be isolated into business layers or data context layers as opposed to being spread heavily all over your controllers. So that's a little bit of the terminology and syntax that you're going to be seeing a lot in the MVC examples. So now we can actually get in there and code a bit. Now that we've talked about MVC in theory, let's take a look at how to build an ASP.NET MVC project and then take a little bit of a tour of the different components of the MVC pattern. We're going to be working in Visual Studio Express 2013 for web for this project. You can also use 2012, and of course when 2015 comes out, you'll be able to use that as well for this project type. So we'll start by creating ourselves a new project. And for our choices, we want to choose under the Web selection, ASP.NET Web Application. Now don't worry that you haven't seen anything about MVC yet. You will. So we'll just leave this at defaults and say OK. And now I'm going to select an empty project. There's also an MVC project, and that will put in the MVC framework, but it'll also create a lot of other classes and such that we don't really want at this point. So I'm going to create an empty project, but I'm going to select the MVC checkbox. Note that you could check Web Forms, which would be the old ASP.NET Web Form kind of project, or Web API, so there are other options that you can check as well. But we wanted to talk specifically about MVC. When I say OK to that, it'll build up some default folders for me. So it's given me a folder for Models, Views, and Controllers, MVC. Also in the View folder, it's given me a web config. There's also an app start folder, and that has a route config class that we're going to be using as well. So the first thing I want to do is I want to add a model. Conveniently, I've actually already created one, so I'm going to add that into the project. And here's my customer model. And if you remember, the model portion of MVC is basically the data storage. So in this case, that's all this class is, a simple customer class, and it has properties that you might expect for the customer object. So there's nothing particularly magical about this particular class. So let's move on and get to the controller. So I right-click on the controllers folder, and I can add a controller. And I have some choices as to what kind of controller I want. I can just add an MVC controller empty, which gives me an empty class. I can also add an MVC controller with read-write actions, which will populate some code for me for doing reads and writes and deletes, but it will not populate any views. I can also have a controller with views using the entity framework. That would require that our model actually use the entity framework, and then it would create not only the controller, but also views and hook up some code for us. And then we get into Web API choices. So I'm going to put in an MVC5 controller with read-write actions. And click Add. And it'll ask for a name, and I'll just call that my home controller. And when I add that, I get a home controller file and class that you can see here. I also got a home folder in the views. Okay, so now let's take a tour of this. And this is sort of like one of those cooking shows where they create something and then they pull the actual one out of the oven after 2 minutes. So let me pull something out of the oven. We'll go to the same basic class, but it's pre-made. So we have the same customer model, and we have our controller. You'll note that the controller descends from controller, which is system.web.mvc controller. And that has to happen for the controller to work. And then we have these public methods, and they typically return an action result. So I have an action result for index, details, create again, except an HTTP post, edit, and again, it's an HTTP post, and delete, and the post for delete. So this lays out our basic read-write operations within our controller. So what have I added to it? I've added a little private method to create us a list of customers, just demonstration customers, and it just creates the customer objects with demo data. So I get my list of customers, and then I return a view with the customers in it. What this does is it provides our view this data model. You'll note that I do the same kind of thing with details, and we'll talk about that in a little bit. So note that the name of this first method is called index. And that reflects the name of our view as well. There's a relationship between the names in the controllers and the names of the view. It doesn't have to be that way. There's a thing called route config that we can use as well. But if we do this, we get it for free. So we have in our views, under home, which corresponds to our home controller, a view called index.cshtml. And this is a razor view. So we have our declaration of our model type up at the top, and it's an IEnumerable customer objects. So it's looking for a list of customers. We have something called a view bag. And note the @ symbols here. This is razor language as well. So we have @model, and that declares that model. And then we have @ in parentheses, and that declares that the code inside those curly braces is going to be razor code. So we're saying that the view bag title is equal to index. And we have some straight HTML. And then we have a paragraph with an action link. And again, it's got the @ symbol in front of it. So that's razor again. So that action link, and we'll talk about that in the future, will allow us to link back to a controller. And then we have a table, and we're going to have headers, and we'll use add.html.displayName4 and each one of the items in the model. So we're going to display a first name, last name, address, etc. Don't worry if I'm going fairly fast through this, because we're going to spend an entire lesson just discussing views. So this view is going to display a table with, of course, the header row showing the display name. And then the next row will actually go through and call out html.display4 and the model for first name, last name. So this is going to display the data. And you'll note we have a for each loop. And again, this is razor doing a for each and then creating HTML by using razor statements. And then in our last cell, we're going to have some action links. So we'll have a link for edit, details, and delete. And we have methods in our controller for each one of those actions. So we have an edit method, a details method, and a delete method. And you'll note we get passed in a parameter called ID for each one of those. So going back to the controller, we'll take a quick look at that. Here's our details method with the ID passed in. We get our list of demo customers, and then we do a little bit of link and call singular default. So we query by customer ID equal to the ID we were passed to get a single customer. And we pass that single customer back to the view. So what view are we passing it back to? We're actually passing it back to the details view. So we have another view in our home folder called details. And here it is. And the model this time is a single customer object rather than a list. And we have some razor that looks somewhat familiar, a display name 4 and a display 4. So for each property, we're creating a line that shows the name of the property and then the actual property value. Going back to our home controller, that's our details method. We have a create method, which will pass back an empty view because it's going to be a totally new model, and a post. And this will happen when the create view is submitted, and we'll get this. And I haven't put anything in to actually create a customer. And here's our edit view, passing in a parameter same way. And it also has a post version, and that happens when that edit view submits. And it will pass us in not only the ID, but also a collection of objects from the form. So that's the general idea. Let's just give it a run so you can actually see it. So here's our index view. And you can see it's simply a table with the field names up at the top, and then 2 rows for the data that we had with the actual data filled in. We have a link for create new, and links for edit, details, and delete. So I should also point out, we're at the home page of the site, and you can see even though we called home index, you don't see any of that in our URL. So now let's go to the details. And you can see my URL changed to home/details/1, and that /1 is the actual ID of the customer that I wanted to get. So it's a little bit different than what you might have expected if you had been working with web forms. So our details simply give us the column heading and the data as we go along. And if I go back to the list, I can also do an edit to that. And it's the same kind of form, it's just we have text boxes instead of labels, so it's editable. So that's our first little tour of ASP.NET MVC. In our next few lessons, we're going to build a little bit of a data-driven application so you can get your feet wet on at least touching something one more step real. We're going to start building a data-driven MVC sample. In this lesson, we're going to work with the model. And of course, we actually want to hook it to a database model. So I've created the project just as an empty MVC project. So it did give me my folders for controllers, models, and views, but I don't have anything beyond that at this point. I do, however, have a SQL Server database called Northwind. The Northwind database is a well-known sample database that Microsoft provides. There's a backup of the database in your work files, and that's what we'll be using in this lesson and one in the future. And if you're familiar with Northwind, there won't be any surprises here. We have a customers table, employees, orders, order details, products. It's Northwind. So I would like to model this database. Now I could go through and create classes for customers and employees and orders and create all of those properties for each one of the fields in the tables. But we have tools for that these days. And one tool is called the Entity Framework. So we're going to build our data model using the Entity Framework. So back to our project, I'll right-click on the project and add a new item. And I'll select Data and ADO.NET Entity Data Model. And this will create us an Entity Framework model. And I'll give that a name of Northwind Model and add it. And now I have some choices. I can do an EF Designer from the database. I can do Code First from the database. And these two are somewhat opposite. Essentially, what an EF Designer from the database does is it takes an existing database and it models the code after that database. Code First from the database hooks the connection to the database, but instead of reading the database and creating the code, you create the code in Visual Studio, and then you can essentially create the database tables from the code models. So we already have the database, so we're going to use EF Designer from database. And we're going to create ourselves a new connection string because we don't have any available in this project. And localhost, and we'll use Windows authentication. And of course, you should do what's ever appropriate for your SQL Server installation here. And I'm going to choose the Northwind database. I'll test the connection, and it succeeds as expected. And we'll say OK to that. So now I have a connection. And I'm going to save those connection settings in WebConfig as Northwind entities. I do need that connection as I go along throughout this process. I'm going to use the latest version of the Entity Framework. And now it would ask what database objects would I want to include in my model. And as you can see, I can include tables, views, and stored procedures and functions. And I can selectively choose whatever tables I want to see, or views, or stored procedures. So for our sample, I'm just going to model the tables, and I'll model all of them. And then there are choices for pluralizing or singularize the object names, including foreign keys in the model, and importing selected stored procedures and functions into the entity model. And model namespace is going to be Northwind Model. So we're good with all those selections. It will read the database, and it will build up our class diagram. So now we have a model diagram. And you can see that I have a customer table, an order table, order details, and it understands the relationships. It also has properties for each one of the fields in the table. And then we have a little bit of a bonus here. We actually have properties for the other tables that we're related to. So I have a property for orders in my customer table, which will relate to all orders for a given customer. It also creates references for the entity framework. And we'll build this, and that build succeeded. And now I have my model. The EDMX is the diagram that we're looking at, but underneath it, there's a number of code files. So let's start off with this Northwind model context.cs. This is our Northwind entities class, and we're going to be using this throughout our MVC project, particularly on our controllers, because this is where we're actually going to be able to get to our data. It descends from DB context, and that allows us, when we query, for instance, to query through to the database. And when we do updates, we'll do updates through to the database, but we can use these objects to do so. In the Northwind model.tt, we have the classes for the various tables. So if I take a look at the customer class, you can see there's a constructor which creates defaults for the orders and customer demographics, which get filled in as you do queries. And then we have properties for each one of the fields in the database table. And then we have the collections for the related tables. So these collections follow the foreign keys to our customer table. And as you can see, we have classes for each one of the tables in Northwind. You can also see the TT class, which is not something you would typically want to mess with. And we'll close these other code files and get them out of the way. Okay, so back to our diagram. So let's say we make a change to our database schema in some way. What happens then? Do I have to hand code it and try to get it to work? The answer is no. We can do an update. If I right-click, there is a choice for Update Model from Database. And this allows me to pick up any changes that come in from the database. It will read the database and let me know if there are any additional tables, which there weren't, so the tables are empty. But it also knows that I didn't bring in the views. So it'll show me the available views. Likewise, it knows about the procedures as well. So it's telling me there are objects within the database that I haven't added. So it'll allow me the opportunity to add them. If I've just changed fields within tables, or perhaps definition of views, I can go to the Refresh tab, and it will allow me to refresh the definition of any tables or views or procedures that I have. And it, of course, knows what tables I have. So I can select those and refresh those. I can also choose to delete things. And when I click Finish, it'll run through, update my model based on the changes that I made and the updates to the database, and refresh the model. After the model's refreshed, you want to rebuild again before you can actually use it in the rest of your MVC code. So that's how we can use the entity framework to easily build a data model that we'll be using in MVC. Where we last left off, we have this great data model in our MVC project. And this model is hooked to a SQL Server database, and we have all sorts of classes that model the tables of the database. So we have customer classes and order classes, order details, regions, employees, all of the tables that we chose in the Northwind database. So now we want to move on and work with controllers. So I've built this project, and it builds just fine. And I want to close the diagram and get it out of the way at this point. And now I want to create my controller. So I select the Controllers folder, right-click on that, and add a controller. I could add an empty controller, which would simply give me an empty controller C# class. I could create a controller with read-write actions, and that would give me some dummy code for reading and writing to the model. And then I can create a controller with views using the entity framework. And that will give me my MVC5 controller. It'll give me the views associated with an index, create, edit, and delete, and details. And it'll also create some code to actually work with the data and the views. So that's a lot of stuff for free. So let's do that. And we choose our model class. A lot of people choose customer, but I'm interested in orders. I want to see what our customers have actually ordered. In our data context class, and that's going to be our Northwind entities. And then I want to generate views, and we'll reference the script libraries. I don't have a shared layout page at this point, so we'll take that one off. And my controller name is orders controller, and that seems fair. So I'll add that. It's creating what's called a scaffolding, and the scaffolding is in the views, and it creates our orders folder, and then the view CS.html files. And we'll get to those. But what we're interested in right now is it also created in our controllers folder the orders controller file. So let's take a look at this. You can see one of the things that we have is it uses system data, systemdata.entity, link, net, web, webMVC, and our data application.models directory. Our .models directory is where our Northwind model resides. So now in our orders controller, I have a private member for Northwind entities, and it's called DB. And now we have a method that returns an action result, and it's called index. And this method is associated with our index view. So it's going to be the main view of this orders controller. And what we want to do is we want to return a collection of orders to the view so that the view can display it in a grid. So in order to do that, we go into Northwind entities, DB, the orders class, and include all of our customers. So that includes the customer table that we get because of the foreign key relationship between orders and customers. We also include employees and shippers. So essentially, we get to see all of the related tables to orders. And we return the orders to list. And this will show us all of the orders. It's completely unfiltered. I could put a where clause into this link statement. And because we're only displaying an actual grid of the order information, we may or may not need to link the customer and the employee and the shipper. If we want to display customer name and employee name as opposed to customer ID, which is the field in the order table, we would do the include of the foreign key table. So that will display our index. Our index view has links for details, edit, create, and delete. So let's take a look at those. We have methods for each one of those. Our first method is the details method, and that's going to be associated with the details view under the orders folder in views. And the details method also has a parameter for ID, and this is going to be the order ID. If our ID is null, you've asked for a null order, so we're going to return a bad request, and bad things will happen from there. Obviously, we'd prefer to put in a little bit more elegant error handling if we're going to ship this in production. If the ID is not null, then we call into Northwind Entities DB, into orders, and we find ID. We can call the find in link by passing in the primary key value. And we get an order object. If the order is equal to null, well, then we have a problem. We'll return that we didn't find anything. Otherwise, we'll pass in that order to the view. Now, when we're passing in parameters to the view on the return of an action result, what this does is it provides the view a data model to display. So on our index, we're passing in all of the orders as a list, and the index view wants a list of orders. In this case, for details, the view is looking for a single order for its data model, so we return a single order model. We also have a create method, and we have a couple of things going on here. First of all, we return a view with no parameters, because we don't have a data model because we're going to be creating a new order. The other thing is that we have this thing called a view bag, and the view bag is data that we can associate with a view and basically pass to the view. And what these will do in this case is populate the items in a drop-down. So we're going to have a drop-down in the create view for customer ID, and it will be populated by this new select list of all the customers in the Northwind Entities DB. The value will be the customer ID, and the actual display member in the drop-down will be the company name. Likewise, we'll have drop-downs for employee ID and ship via. So we're not asking our user to enter in a customer ID, we're letting them choose from a list. You don't have to use this technique. You can actually add these lists to the model and create your own kind of model class so that the list is populated out of the model. But you can also do it with the view bag, and that's what the wizard gave us for free. When the create form is submitted, it will call this HTTP post create method. And there'll be a binding which tells us the fields that are passed in from the view. And they're all the fields we need to create an order. We'll check that the model state is valid. And if it is, we'll just add the order object that we're passed to the orders context. And we'll save the changes, and we'll redirect back to the index view. And that's what redirect to action does. It's very similar to the redirect that you see in old web forms. If it wasn't valid, then we want to go back to that create, and we need to repopulate our view bag for our lists. The edit kind of combines the detail and the create. We get an ID parameter, so we get the order for that particular ID. We also populate our list for customers, employee ID, and ship via, and we return our order. We also have a very similar HTTP post. We'll get an order object as a parameter, and we'll save changes of that order object. For the delete, we're going to show a form that basically shows the details of the order. So this is very similar to details. And then when we get it submitted, we'll get this post. And we'll be passed in the ID of the order to delete. We'll find that order, and then we'll call into the context and remove that order and save the changes and redirect back to the index. So those are your basic create, read, update, and delete methods. Good old CRUD. And that's how we can do it in an MVC controller. Next, we'll take a look at what the views look like And we'll take a little bit of time to look at Razor. So far, we've looked at our model and our controller in our ASP.NET MVC sample. Now let's take a look at the views. If you remember, we were focusing on the orders table. And in the views directory, we have a folder called orders, which was created when we created our controller. And of course, we're all hooked to the entity framework. And the controller had an action called index, and we also have a corresponding view called index. You'll note the naming convention that the controller action method is typically the same as the view name. That's not necessarily all the case. There is some routing that we can do to change that, and I'll show you that later. If we take a look at our index, we start up at the top and we have an @ model. The @ symbol indicates that this is going to be a Razor statement. And what this particular statement says is that the views model is going to be of type IEnumerable, data application, models, order. So we're going to take our order model, and we'll be using that to fill up a table. We also have a Razor statement within some curly braces, and that @ curly brace would indicate that all of the statements in the curly braces are Razor statements. And it's just saying that our layout is null. If we were to do a shared layout, which is similar to a web form master page, we might give that name here. And then further into our CSHTML, we get into an HTML area, and it's just standard HTML for our header and our title. And then we get into our body tag. And now we embed some Razor statements within HTML. So we have a paragraph, and then we have an @html.action link, create new, and create. What the action link will do is we'll create a link in the page with the text create new, and it will call the controller method create. Then we'll get into our table, and we'll have a header row, and we'll again have a Razor statement, this time @html.displayName for model, and of course we have a link here, model order date. So this is going to display the display name for order date, which if we haven't set any attributes in the model, is just going to be order date. And we're going to do that for every field in the orders table. And then we'll have a Razor for each statement. And we're going to look at each item in the model, so I'll have a row for every item in the orders table. And we'll call for each one of those cells @html.display for model item and the actual value of the order date, required date, etc. So this will fill in the actual values for the field in the table data. And we'll just loop through every item in the order. Finally, in our last table cell, we'll have some more action links. One for edit, one for details, and one for delete. And in each case, we're going to pass in a parameter named ID, and we'll be passing in the item's order ID. So that's fairly simple and clear, I believe. So let's take a look at another one. Let's go look at the create. So in this case, our model is a single order. It's not a list or an IEnumerable. So we just have a single order that we're going to be creating. We have the same layout equal to null, a header, and then some body scripts, and then a little bit of a new Razor statement @using HTML begin form. So we're basically creating a form tag here because we're going to be posting back whatever the user entries are in order to create the order. And we have an HTML anti-forgery token, which is a bit more advanced in terms of MVC. And then we get into our HTML, and we'll have an HTML validation summary, and that will summarize any validation errors that come along. We have a label for the customer ID field, and you can see that we can also apply HTML attributes. So we've created a class attribute, and it will render just what you would expect in terms of rendering a class statement. And then we get down to the drop-down list. If you remember, we put our drop-down list items in the view bag, and we called that view bag customer ID. So we have a drop-down list named customer ID, and it will look in the customer ID view bag. And again, we have more HTML attributes for the class name. And then finally, we have an HTML validation message, again, for customer ID. And this also gets into the attributes that are applied in the model. There are attributes for validation in the model, and the controller also handles validation. So if there are any validation errors, we'll get a validation message and a validation summary. The model doesn't give you the validation attributes for free. You have to add those. So for each one of these fields, we have this approach. And we have the same idea for employee ID. And then for order date, instead of a drop-down list, we have an editor for. But it also uses the model order date. And then we have all the rest of the fields in the order. And down bottom, we have a standard HTML input of type submit, and it just says create as the text on the button. And when this submit button is clicked, then we'll call a form post with the name create, and that will be the action method that we call in the controller. And at the bottom of it, we have an action link for getting back to our list, and it will take us to the index method of the controller. If we take a look at the edit, it's very similar to the create, of course. The model is in order. We have the same kind of begin form approach, validation summaries, a hidden field for the order ID because we're not creating, so we actually have an existing order, and we need to be able to pass that back in the post. And then the same fields, drop-down lists, and validation messages for each one of the fields in the order. And on the bottom, the same submit. This time, the name is save instead of create. So it's a very similar pattern in terms of creating and editing, and that's what you would expect. On the details, again, we have a single order as a model, and then display names and display fors for each field in the model. So we have order date, required date. So this is similar to what we have in our grid because we have the display name for and the display for in the grid rows. And down bottom, we have action links for edit and back to the list that takes us to the controller index. And the edit takes us to the edit method of the controller, and it passes in the order ID as the ID parameter. And finally, the delete view basically shows the details. So it looks very similar to a detail form with the display name and display for. And at the bottom, we have a begin form and a submit button for delete. And that will take us to our delete action. And we also have our action link back to the list. So there's all the different views that we have, and they all, of course, relate back to controller methods. So let's see what this looks like now. We have a bad request. Well, that's not great. There's one thing that we haven't done yet, and that's our route config. You'll note that this is in the orders directory, and there's no default.aspx or index.html in this site. So in terms of a default page, we don't have one. The route config provides us some path information, and we can stop debugging now. So by default, it tells us the name of our default controller is simply home and goes to an index page, but we don't have one of those. So we'll comment that out and uncomment this which I previously entered. And in this case, our default will go to the orders page and the index action method. So here's the format. It'll give us the URL in the form of controller/action/ID, and that's the ID parameter, which in this case, we're going to declare as optional. Our controller is going to be the orders controller, and our action method is going to be our index method. And if you remember, in that controller method and the index method, what we do is we create our list of orders, and we return that to the view. And this will end up calling index.cshtml in the orders subdirectory. So now that this is here, let's give it a run. Okay, that's much better. So here's our table, and obviously it's not beautiful. There's no styling in it whatsoever. And it does have our links over on the right-hand side. And if I take a look at details, I do get the details of that particular order. And if I click on Edit down here, I do have the Edit page, and here's our drop-downs. So I can select a different customer ID. And if I save that, it'll be saved, and it will go back to my index view. And the company name was indeed changed to Save-A-Lot Markets. If I go to my delete page, it again just shows the details with a delete button at the bottom. And of course, create new will go to that same layout that we saw in edit, except nothing will be entered, except for the drop-downs that will use the first item as a default. So that's a basic overview of the ASP.NET MVC pattern. There's a lot more that's involved in MVC, obviously, than this really basic example. And we do have a course that gives you all those details. But there's really too many things to do in the course of a design pattern course. So if you're interested in ASP.NET MVC, I encourage you to take a look at that course as well. And there's a lot going on there. And it'll talk about styles as well as routing in much more detail in terms of controllers, models, and views. But this should give you an idea of the general format of an MVC pattern and how it's applied in ASP.NET. Congratulations on finishing the course. It's always great to finish something, isn't it? It's really a rare occurrence in software development, unfortunately. So, good job. This course was about helping you write better code, how to create better structure in terms of the relationships of our classes, and how our architecture can be better structured as well. With the design patterns and the solid principles, we really focused about simplifying code, making it more readable and more maintainable. And of course, we went through the Gang of Four's 23 design patterns, and we have examples for all of them. We also took a look at ASP.NET and the Model View Controller pattern. And of course, the Model View Controller is a pattern that doesn't necessarily have to be used in ASP.NET. It can be, and is frequently used for many other applications, as well as just ASP.NET web forms. So let's give you some more resources to go forward. The first resource is the Basic Design Pattern book. It's a classic, not necessarily great beach reading, although I actually did read some chapters on the beach, but still a classic text, and I think you might get a lot out of it, particularly having gone through the course. Now you can actually appreciate the subtleties that are in the book as well. And of course, Amazon carries it, as do other retail outlets. Microsoft, of course, has a lot of documentation, a lot of resources online. A couple of specific ones that apply to this course are coding conventions. We do have a lesson on coding conventions, but Microsoft has their own guidelines if you ever need to defend your opinion as to why you should do something the way Microsoft does it. Microsoft also has .NET guidelines and best practices, and there's a ton of documentation there. Microsoft, of course, has a number of other areas and basically any kind of document that you want for .NET. I'd also suggest Stack Overflow just as a general resource to ask questions at and to see answers. And of course, you have my contact information, and I'm happy to answer any questions you might have about the course as well. And I'd love to hear about any projects that you're working on. I find it very interesting to find out what people are doing. Congratulations, and thank you for taking the course.